Welcome back, tech enthusiasts. Today we are diving into the fascinating world of artificial intelligence and unveiling the ultimate pathway to becoming an AI engineer. If you have ever wondered how AI is transforming industries or dreamt of creating intelligent systems, you are in the right place. Join us as we explore the comprehensive AI engineer course that will take your skills to the next level. Before we dive into the course details, let's talk about the sheer power of AI. From self driving cars to virtual assistants, AI is revolutionizing the way we live and work. As an AI engineer, you will be at the forefront of this revolution, crafting smart algorithms and unlocking the potential of AI to solve complex problems. Now, let's uncover the exciting details of the AI engineer course. This comprehensive program is designed to equip you with the necessary skills to thrive in the AI industry. From machine learning fundamentals to deep neural networks, you will master the tools and techniques that drive cutting edge AI applications. Theory alone won't cut it. That's why this course emphasizes hands on learning. You will work on real world projects, building AI models, and honing your problem solving abilities. By the end of this course, you will have an impressive portfolio showcasing your AI prowess. Our team of industry expert instructors is second to none. They will guide you every step of the way, sharing their practical experiences and industry insights. Learning from the best will propel your AI journey to new heights. Whether you are a seasoned programmer or a curious beginner, this AI engineer course is tailored to fit your needs. Unleash your potential, join the AI revolution, and turn your passion for technology into a career that shapes the future. Now, over to our training experts.
It's a weekend, and John decided to watch the latest movie recommended by Netflix at his friend's place. Before heading out, he asked Siri about the weather and realized it would rain. So he decided to take his Tesla for the long journey and switch to autopilot on the highway. After coming home from the eventful day, he started wondering how technology has made his life easy. He did some research on the internet and found out that Netflix, Siri, and Tesla are all using AI. So, what is AI? AI, or artificial intelligence, is nothing but making computers-based machines think and act like humans. Artificial intelligence is not a new term. John McCarthy, a computer scientist, coined the term artificial intelligence back in 1956, but it took time to evolve as it demanded heavy computing power. Artificial intelligence is not confined to just movie recommendations and virtual assistants. Broadly classifying, there are three types of AI. Artificial narrow intelligence, also called weak AI, is the stage where machines can perform a specific task. Netflix, Siri, chatbots, facial recommendation systems are all examples of artificial narrow intelligence. Next up, we have artificial general intelligence, referred to as an intelligent agent's capacity to comprehend or pick up any intellectual skill that a human can. We are halfway into successfully implementing this phase. IBM's Watson supercomputer and GPT-3 fall under this category. And lastly, artificial superintelligence. It is the stage where machines surpass human intelligence. You might have seen this in movies and imagined how the world would be if machines occupy it. Fascinated by this, John did more research and found out that machine learning, deep learning, and natural language processing are all connected with artificial intelligence. Machine learning, a subset of AI, is the process of automating and enhancing how computers learn from their experiences without human help. Machine learning can be used in email spam detection, medical diagnosis, etc. Deep learning can be considered a subset of machine learning. It is a field that is based on learning and improving on its own by examining computer algorithms. While machine learning uses simpler concepts, deep learning works with artificial neural networks, which are designed to imitate the human brain. This technology can be applied in face recognition, speech recognition, and many more applications. Natural language processing, popularly known as NLP, can be defined as the ability of machines to learn human language and translate it. Chatbots fall under this category. Artificial intelligence is advancing in every crucial field like healthcare, education, robotics, banking, e-commerce, and the list goes on. Like in healthcare, AI is used to identify diseases, helping healthcare service providers and their patients make better treatment and lifestyle decisions. Coming to the education sector, AI is helping teachers automate grading, organizing, and facilitating parent-guardian conversations. In robotics, AI-powered robots employ real-time updates to detect obstructions in their path and instantaneously design their routes. Artificial intelligence provides advanced data analytics that is transforming banking by reducing fraud and enhancing compliance. With this growing demand for AI, more and more industries are looking for AI engineers who can help them develop intelligent systems and offer them lucrative salaries going north of $120,000. The future of AI looks promising, with the AI market expected to reach $190 billion.
Artificial intelligence is reshaping industries and transforming the way we live and work. It encompasses a wide range of technologies including machine learning, deep learning, natural language processing, computer vision, and many more. With its ability to analyze vast amount of data and make intelligent decisions, AI has become a game changer across various domains. Hi everyone, welcome to Simplylearn's YouTube channel. This AI roadmap guides you in navigating the path towards building a successful career in artificial intelligence. The ultimate goal of artificial intelligence is to create intelligent machines that can perform complex tasks, exhibit human-like intelligence, and contribute positivity to society. AI presents exciting career opportunity in various industries and sectors. Roles like AI engineer, data scientist, NLP engineers, computer vision engineers, AI research scientists, robotic engineers, and many more offer exciting prospects for working with cutting-edge technologies and making an impact through artificial intelligence innovation. According to Glassdoor, the average reported salary of an AI engineer in the United States is around $105,000 per year. However, in India, it is 10 lakh per annum. Leading companies worldwide are fully aware of the immense value of AI and are actively pursuing skilled AI engineers to contribute to their research, development, and implementations of AI technology. Among these top companies are Google, Microsoft, Amazon, Goldman Sachs, Apple, and JP Morgan Chase. Therefore, top companies hiring AI engineers provide excellent opportunity for aspiring professionals. On that note, elevate your career with our AI and ML course developed in partnership with Purdue University and IBM. Gain expertise in high-demand skills such as machine learning, deep learning, NLP, computer vision, reinforcement learning, ChatGPT, generative AI, explainable AI, and more. Unleash your potential and unlock exciting opportunity in the world of AI and ML. This course covers tools like Python, TensorFlow, Keras, ChatGPT, OpenAI Gem, Matplotlib, and many more. So hurry up and find the course link in the description box for more details. Our learners have experienced huge success in their careers. Listen to their experience. Find the Simplylearn course review link in the description box. Without any further delay, let's dive into the topic now. If you desire to become an AI engineer, here are the steps you can follow to achieve your goal. Firstly, obtain a strong foundation in mathematics and programming. Gain a strong foundation in creating mathematical concepts like linear algebra, calculus, and probability theory. In addition to that, it is crucial to acquire mastery of programming languages like Python, commonly used in AI, and become proficient in coding. Then, earn a degree in a relevant field. That means, earn a bachelor's or master's degree in computer science, data science, AI, or a related field to gain a comprehensive understanding of AI principles and techniques. Next, gain knowledge in machine learning and deep learning. To become an AI engineer, develop familiarity with ML algorithms, neural networks, and deep learning frameworks, example TensorFlow, PyTorch, to train and optimize models using real-world dataset. Followed by that, work on practical projects. Gain hands-on experience and showcase your skills by working on AI projects. Moreover, build a portfolio of projects demonstrating your ability to solve AI problems, impressing potential employers. Then, stay updated with the latest advancements. Stay updated with the latest trends and research in AI, a rapidly evolving field, and expanding your knowledge by reading research papers, participating in online courses and workshops, and joining AI communities. Next, collaborate and network. Engage with AI communities, attend conferences, participate in online forums to connect with professionals in this field. Collaborating with others can enhance your learning experience and open new opportunities. Later, seek internships or entry-level positions. Gain practical experience through AI internships or entry-level roles in industry or research institutions. This provides valuable exposures and help develop your skills. Finally, continuously learn and adapt. In the rapidly evolving field of AI, stay updated on new developments, explore specialized areas, and embrace emerging technologies and tools to pursue a career as an AI engineer. Now that we have covered the essential steps to become an AI engineer, let's explore the necessary programming languages and algorithms for aspiring AI engineers. So, mastering programming languages like Python, R, Java, and C++ is vital for acquiring proficiency in AI. These languages enables you to construct and deploy models effectively. Additionally, it would help if you gain a thorough understanding of machine learning algorithms such as linear regressions, k-nearest neighbors, naive-bayes, and support vector machines. These languages and algorithms are fundamental tools in the field of AI. They will enable you to develop and implement effective artificial intelligence models.
Hello everyone and welcome to our video on skills required for an AI engineer. With the advent of artificial intelligence and its superior abilities to improve human life, the need and demand for expert AI professionals is at an all-time high. This expanding demand has led to a lot of people applying for AI jobs and upskilling themselves in the field of AI. But doing this is just like playing a game but not knowing its rules. For someone to become an AI professional and land a job like an AI engineer, they first have to understand the demand from this role and what skills are expected of an AI engineer. So if you are someone who wishes to become an AI engineer, or if you wish to upgrade your skills in AI and get promoted as an AI engineer, then make sure you watch this amazing video till the very end. In this video, we will be breaking down in complete detail each and every skill that you would need in order to crack an AI engineer job interview.
But why should you consider a career in AI? AI is not just a passing trend. It's a seismic shift that is reshaping our world and creating new avenues for innovation and discovery. By embracing a career in AI, you become a part of a dynamic field that thrives on solving complex problems, pushing boundaries, and making a profound impact on society. The demand for AI professionals is skyrocketing across industries, from healthcare and finance to entertainment and transportation. Organizations are actively seeking talented individuals who can harness the power of AI to drive their business forward. But what skills does it take to become an AI engineer? How can you embark on the thrilling journey? We have answered to all of your questions. Also, accelerate your career in AI and ML with our comprehensive postgraduate program in AI and machine learning. Gain expertise in machine learning, deep learning, NLP, computer vision, and reinforcement learning. You will receive a prestigious certificate, exclusive alumni membership, and Ask Me Anything session by IBM, with 3 capstone projects and 25 plus industry projects using real dataset from Twitter, Uber, and many more. You will gain practical experience. Masterclasses by Caltech faculty and IBM expert ensure top-notch education. Simplylearn Job Assist help you to get noticed by leading companies. This program covers statistics, Python, supervised and unsupervised learning, NLP, neural network, computer vision, GANs, Keras, TensorFlow, and many more skills. So enroll now and unlock exciting AI and ML opportunities. The link is in the description box below. So without any further delay, let's get started. Some steps are crucial to master in the field of AI and becoming an AI engineer. Let's go through them real quick. First, establish a strong foundation in mathematics and programming. Start by gaining a solid understanding of critical concepts like linear algebra, calculus, and probability theory. Additionally, it is crucial to become proficient in programming language like Python, which is commonly used in AI, and develop coding skills. And the next one is pursue a degree in relevant field. Earn a bachelor or master degree in computer science, data science, or AI, or related discipline to acquire comprehensive understanding of AI principles and techniques. Then, acquire knowledge in machine learning and deep learning. Familiarize yourself with ML algorithms, neural networks, and deep learning frameworks, that is, TensorFlow and PyTorch, to train and optimize models using real-world datasets. Afterward, engage in practical projects, gain hands-on experience, and demonstrate your skills by working on AI projects. Building a portfolio of projects that showcase your ability to solve AI problems can make a strong impression on potential employers. And the fifth one is collaborate and network. Engage with communities, attend conferences, and participate in the online forums to connect with the professionals in the field. Collaborating with others can enhance your learning experience and open up new opportunities. And the sixth one is seek internship or entry-level positions. Gain practical experience through AI internship or entry-level roles in industries or research institutions. This will provide valuable exposure and help you further develop your skill. And at the last, continuously learning and adapt. In the fast-paced world of AI, it is crucial to stay updated on new developments, explore specialized areas, and embrace emerging technologies and tools. Continuous learning and adaptability are essential for pursuing a successful career as an AI engineer. So, now that you are familiar with the steps involved in the journey of AI engineer, let's have a look at the salary of an AI engineer. So, according to Glassdoor, the average reported salary of an AI engineer in the United States is $105,000 per year. However, in India, it is 10 lakh per annum. So, these figures are way better than the average salary figures of any job role. So, let's discuss the skills you need to become an AI engineer. You should have a strong background in data science and machine learning. Here is a breakdown of your skills. Number one, strong programming abilities. They typically refers to expertise in one or more programming languages commonly used in data science and machine learning, such as Python and R. Proficiency in programming allows you to write efficient and scalable code for data analysis, modeling, and algorithm implementation. And the second one is knowledge of machine learning algorithms. This involves understanding and familiarity with a wide range of machine learning algorithms, including both supervised and unsupervised learning. You should be able to select and apply appropriate algorithm for a specific problem as well as evaluate and optimize their performance. And the third one is proficiency in statistics and mathematics. Sound knowledge of statistics and mathematics is fundamental for data analysis and machine learning. You should be comfortable with statistical concepts, hypothesis testing, regression analysis, probability theory, linear algebra, and calculus. And the fourth one is familiarity with deep learning frameworks. Deep learning has gained significant popularity in recent years, and familiarity with deep learning frameworks like TensorFlow, PyTorch, or Keras is valuable. These frameworks provide tools and libraries for building, training, and deploying deep neural networks for tasks such as image recognition, natural language processing, and time series analysis. And the fifth one is experience with big data technologies. Dealing with large scale dataset requires knowledge of big data technologies such as Apache Hadoop or Apache Spark or distributed computing frameworks. Understanding how to process, store, and analyze data efficiently in distributed environments. And the sixth one is excellent problem solving and analytical skills. These skills enable you to break down complex problems, identify key factors, and develop effective solutions. You should be adept at critical thinking, troubleshooting, and debugging to handle real world challenges in the data science and machine learning. Remember to stay updated with the latest advancement in the field and continue learning to stay at the forefront of data science and machine learning.
First, let's understand what really is artificial intelligence. Artificial intelligence is the science of building intelligent machines from vast volumes of data. This data can be structured, semi-structured, or unstructured in nature. AI systems learn from past experiences and perform human-like tasks. Artificial intelligence enhances the speed, precision, and effectiveness of human efforts. AI uses sophisticated algorithms and methods to build machines that can make decisions on their own. Deep learning and machine learning are the two subsets of artificial intelligence. So, you need both machine learning algorithms and deep learning networks to build intelligent systems. AI is now being widely used in almost every sector of business, such as transportation, healthcare, banking, retail, entertainment, and e-commerce. Now, let's look at the different types of artificial intelligence. So AI can be classified based on capabilities and functionalities. Under capabilities, there are three types of artificial intelligence. They are narrow AI, general AI, and super AI. Under functionalities, we have four types of artificial intelligence: reactive machine, limited memory, theory of mind, and self-awareness. Let's look at them one by one. First, we will look at the different types of artificial intelligence based on capabilities. So what is narrow AI? Narrow AI, also known as weak AI, focuses on one narrow task and cannot perform beyond its limitations. It aims at a single subset of cognitive abilities and advances in that spectrum. Applications of narrow AI are becoming increasingly common in our day-to-day lives as machine learning and deep learning methods continue to evolve. Apple's Siri is a simple example of a narrow AI that operates with a limited predefined range of functions. Siri often has challenges with tasks outside its range of abilities. IBM Watson supercomputer is another example of narrow AI, which applies cognitive computing, machine learning, and natural language processing to process information and answer your questions. IBM Watson once outperformed human contestant Ken Jenkins to become the champion on the popular game show Jeopardy! Other examples of narrow AI include Google Translate, image recognition software, recommendation systems, spam filtering, and Google's page ranking algorithm. Next, we have General Artificial Intelligence or General AI. General AI, also known as Strong AI, has the ability to understand and learn any intellectual task that a human can. General Artificial Intelligence has received a $1 billion investment from Microsoft through OpenAI. It allows the machine to apply knowledge and skills in different contexts. AI researchers and scientists have not achieved strong AI so far. To succeed, they would need to find a way to make machines conscious, programming a full set of cognitive abilities. Fujitsu built the K computer, which is one of the fastest computers in the world. It is one of the most notable attempts at achieving strong AI. It took 40 minutes to simulate a single second of neural activity, so it is difficult to determine whether or not strong AI will be achieved in the near future. Tianhe 2 is a supercomputer created by China's National University of Defense Technology. It currently holds the record for CPS at 33.86 petaflops. Although it sounds exciting, the human brain is estimated to be capable of 1 exaflop. Now CPS means characters per second that a system can process. Third in the list of AI that is based on capabilities, we have Super AI. Super AI exceeds human intelligence and can perform any task better than a human. The concept of artificial superintelligence sees AI evolve to be so akin to human emotions and experiences that it doesn't just understand them, it evokes emotions, needs, beliefs, and desires of its own. Its existence is still hypothetical. Some of the key characteristics of Super AI include the ability to think, solve puzzles, make judgments, and decisions on its own. Now, if you have enjoyed watching this video so far, please make sure to subscribe to our YouTube channel and hit the bell icon to stay updated with all the latest technologies. Also, if you have any questions related to this video, please put it in the chat section. Our team of experts will help you address your questions. Moving ahead, now we will see the different types of artificial intelligence based on functionalities. In this category, first we have reactive machine. A reactive machine is the basic form of AI that does not store memories or use past experiences to determine future actions. It works only with present data. They simply perceive the world and react to it. Reactive machines are given certain tasks and don't have capabilities beyond those duties. IBM's Deep Blue, which defeated chess grandmaster Garry Kasparov, is a reactive machine that sees the pieces on a chessboard and reacts to them. It cannot refer to any of its prior experiences and cannot improve with practice. Deep Blue can identify the pieces on a chessboard and know how each moves. It can make predictions about what moves might be next for it and its opponent. It can choose the most optimal moves from among the possibilities. Deep Blue ignores everything before the present moment. All it does is look at the pieces on the chessboard as it stands right now and choose from possible next moves. Up next, we have limited memory. Limited memory AI learns from past data to make decisions. The memory of such systems is short-lived. While they can use this data for a specific period of time, they cannot add it to a library of their experiences. This kind of technology is used for self-driving vehicles. They observe how other vehicles are moving around them in the present and as time passes. That ongoing collected data gets added to the static data within the AI machine, such as lane markers and traffic lights. They are included when the vehicle decides to change lanes to avoid cutting off another driver or being hit by a nearby vehicle. Mitsubishi Electric is a company that has been figuring out how to improve such technology for applications like self-driving cars. Then we have theory of mind. Theory of mind represents a very advanced class of technology and exists as a concept. This kind of AI requires a thorough understanding that the people and the things within an environment can alter feelings and behaviors. It should be able to understand people's emotions, sentiment, and thoughts. Even though a lot of improvements are there in this field, this kind of AI is not complete yet. One real-world example of theory of mind AI is Kismet, a robot head made in the late 90s by a Massachusetts Institute of Technology researcher. Kismet can mimic human emotions and recognize them. Both abilities are key advancements in theory of mind AI, but Kismet can't follow gazes or convey attention to humans. Sophia from Hanson Robotics is another example where the theory of mind AI was implemented. Cameras within Sophia's eyes combined with computer algorithms allow her to see. She can follow faces, sustain eye contact, and recognize individuals. She is able to process speech and have conversations using natural language subsystem. Finally, we have self-awareness. Self-awareness AI only exists hypothetically. Such systems understand their internal traits, states, and conditions and perceive human emotions. These machines will be smarter than the human mind. This type of AI will not only be able to understand and evoke emotions in those it interacts with, but also have emotions, needs, and beliefs of its own. While we are probably far away from creating machines that are self-aware, we should focus our efforts towards understanding memory, learning, and the ability to base decisions on past experiences. Let's look at the definition of each of these learning techniques. Supervised learning uses labeled data to train machine learning models. Labeled data means that the output is already known to you. The model just needs to map the inputs to the outputs. An example of supervised learning can be to train a machine that identifies the image of an animal. Below you can see we have our trained model that identifies the picture of a cat. Unsupervised learning uses unlabeled data to train machines. Unlabeled data means there is no fixed output variable. The model learns from the data, discovers patterns and features in the data, and returns the output. Here is an example of an unsupervised learning technique that uses the images of vehicles to classify if it's a bus or a truck. So the model learns by identifying the parts of a vehicle, such as the length and width of the vehicle, the front and rear end covers, roof hoods, the types of wheels used, etc. Based on these features, the model classifies if the vehicle is a bus or a truck. Reinforcement learning trains a machine to take suitable actions and maximize reward in a particular situation. It uses an agent and an environment to produce actions and rewards. The agent has a start and an end state, but there might be different paths for reaching the end state, like a maze. In this learning technique, there is no predefined target variable. An example of reinforcement learning is to train a machine that can identify the shape of an object given a list of different objects such as square, triangle, rectangle, or a circle. In the example shown, the model tries to predict the shape of the object, which is a square here. Now, let's look at the different machine learning algorithms that come under these learning techniques. Some of the commonly used supervised learning algorithms are linear regression, logistic regression, support vector machines, k-nearest neighbors, decision tree, random forest, and naive Bayes. Examples of unsupervised learning algorithms are k-means clustering, hierarchical clustering, db-scan, principal component analysis, and others. Choosing the right algorithm depends on the type of problem you are trying to solve. Some of the important reinforcement learning algorithms are Q-learning, Monte Carlo, SARSA, and Deep Q network. Now let's look at the approach in which these machine learning techniques work. So supervised learning takes labeled inputs and maps it to known outputs, which means you already know the target variable. Unsupervised learning finds patterns and understands the trends in the data to discover the output. So the model tries to label the data based on the features of the input data. While reinforcement learning follows trial and error method to get the desired solution. After accomplishing a task, the agent receives an award. An example could be to train a dog to catch the ball. If the dog learns to catch a ball, you give it a reward such as a biscuit. Now, let's discuss the training process for each of these learning methods. So supervised learning methods need external supervision to train machine learning models, and hence the name supervised. They need guidance and additional information to return the result. Unsupervised learning techniques do not need any supervision to train models. They learn on their own and predict the output. Similarly, reinforcement learning methods do not need any supervision to train machine learning models. And with that, let's focus on the types of problems that can be solved using these three types of machine learning techniques. So supervised learning is generally used for classification and regression problems. We'll see the examples in the next slide. And unsupervised learning is used for clustering and association problems, while reinforcement learning is reward based. So for every task or for every step completed, there will be a reward received by the agent. And if the task is not achieved correctly, there will be some penalty used. Now, let's look at a few applications of supervised, unsupervised, and reinforcement learning. As we saw earlier, supervised learning are used to solve classification and regression problems. For example, you can predict the weather for a particular day based on humidity, precipitation, wind speed, and pressure values. You can use supervised learning algorithms to forecast sales for the next month or the next quarter for different products. Similarly, you can use it for stock price analysis or identifying if a cancer cell is malignant or benign. Now, talking about the applications of unsupervised learning, we have customer segmentation. So based on customer behavior, likes, dislikes, and interests, you can segment and cluster similar customers into a group. Another example where unsupervised learning algorithms are used is customer churn analysis. Now, let's see what applications we have in reinforcement learning. So reinforcement learning algorithms are widely used in the gaming industries to build games. It is also used to train robots to perform human tasks.
Profit estimation of a company. If I was going to invest in a company, I would like to know how much money I could expect to make. So we'll take a look at a venture capitalist firm and try to understand which companies they should invest in. So we'll take the idea that we need to decide the companies to invest in. We need to predict the profit the company makes, and we're going to do it based on the company's expenses, and even just a specific expense. In this case, we have our company, we have the different expenses, so we have our R&D, which is your research and development, we have our marketing, we might have the location, we might have what kind of administration it's going through. Based on all this different information, we would like to calculate the profit. Now, in actuality, there's usually about 23 to 27 different markers that they look at if they're a heavy-duty investor. We're only going to take a look at one basic one. We're going to come in, and for simplicity, let's consider a single variable R&D and find out which companies to invest in based on that. So when we take our R&D and we're plotting the profit based on the R&D expenditure, how much money they put into the research and development, and then we look at the profit that goes with that. We can predict a line to estimate the profit. So we can draw a line right through the data. And when you look at that, you can see how much they invest in the R&D is a good marker as to how much profit they're going to have. We can also note that companies spending more on R&D make good profit. So let's invest in the ones that spend a higher rate in their R&D. What's in it for you? First, we'll have an introduction to machine learning, followed by machine learning algorithms. These will be specific to linear regression and where it fits into the larger model. Then we'll take a look at applications of linear regression, understanding linear regression, and multiple linear regression. Finally, we'll roll up our sleeves and do a little programming in use case profit estimation of companies. Let's go ahead and jump in. Let's start with our introduction to machine learning, along with some machine learning algorithms and where that fits in with linear regression. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example Let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far, where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there, like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model, and that's why it'd be multiple linear regression. And finally, we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where a regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle. A good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from. It's called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1 plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values based on the model we created. The distance between the actual and predicted values is known as residuals or errors. the best fit line should have the least sum of squares of these errors, also known as e-square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e-square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. And we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumberPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplot library and then Seaborn sits on top of it. And we'll take a look at what that looks like You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplot library inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000 companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplylearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/simplylearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row. That's what the colon, the first colon is, comma, except for the last column. That's what the second part is, where we have a colon -1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any two of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in two steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. And we have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the third row. And in there we're going to take the label coder and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train test split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit, because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train test split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn.linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do X train and Y train, because we're using the training data, X being the data in and Y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy X equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a y_predict variable, and we're going to put in the x test. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have y_predict equals regressor.predict x test going in, and this gives us y_predict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print y_predict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print y_predict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works, and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. We're looking at the error. So, in the R2 score, we take our Y test versus our Y predict. Y test is the actual values we're testing. That was the one that was given to us, so we know are true. The Y predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R-squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression. Why linear regression? Now that we have come this far, I'm planning to take a closer look at our cells so that we can estimate cells in the future. How about we hire a data scientist? You can see our two corporate individuals. It looks more like they should be agents or secret agents someplace, discussing how to better forward their company. And so they're going to come in and ask the data scientist to come in. Good idea. This will help us to keep a constant track of our cells. So why do we need linear regression? Let's assume that we need to predict the number of skiers based on snowfall. So this happens to be, we've kind of jumped one business to the next. So we're looking at the skiing business, very popular in a lot of areas. And it's based on snowfall a lot of times. You figure you don't have snow, you don't have skiers. But can we actually use something more specific instead of, look, it's snowing? And instead of saying, hey, look, it's snowing, we can actually start drawing graphs. And the graph shows that with an increase in snowfall, the frequency of skiers also increases. So, and there's a pretty direct correlation. If you've ever been up to ski areas, when there's a lot of snowfalls, the skiers all show up because they know it's going to be better skiing right afterward. So it's kind of easy to see why skiers and snowfall would go together. And it usually draws a nice straight line. And you can easily predict how many skiers, and that way you can also predict how many people you need to service them, how many lifts to have up and running, and all the stuff that goes with running a ski area. Thus, we see that the number of skiers are directly proportional to the amount of snowfall. Regression models a relation between a dependent y and an independent x variable. This is real important to understand regression, because when we talk about linear regression, it's the basis of almost all our machine learning algorithms out there, and it's usually an underlying part of the math in our deep learning. So it all starts here with linear regression. And when we talk about a dependent y and an independent x variable, these are numbers. We're usually talking about floats. So we want to have an actual number value coming out. And that's different than something that's categorical, where we want to know yes or no, true, false. So regression means we're looking for a number. The independent variable is known as predictor variable, and dependent variable is known as the response variable. So we have one predictor variable, the amount of snowfall, and one response variable, how many skiers are going to show up. And then we can take this relationship, and it can be expressed as y equals beta. We're going to use the Greek letter beta, and we have beta naught plus beta 1 x1. And if you continue out, it'd be plus beta 2, x2, and so on till the nth degree. In this case, snowfall is an independent variable, and skiers is a dependent variable. So we kind of had a little quick overview. Let's go ahead and talk a little bit more about what is linear regression. So we're going to go from y, predicting a number of skiers for snowfall, and we looked at the formula a little bit, but let's look a little bit closer at what exactly is going on with linear regression. And the question is going to come up in an interview. What is linear regression? Linear regression is a type of statistical analysis that attempts to show the relationship between two variables. Linear regression creates a predictive model on any data showing trends in data. The model is found by using the least square method. There are other methods. The least square method happens to be the most commonly used out there. And we usually start with the least square method since it's the most common and usually works the best on most models. And we're already looking at how linear regression works, but let's dig deeper into it and let's take a closer look. How linear regression works. I will provide you with a data set which has rent, area, other information in it. It looks like our secret agents have put on their casual wear for this one. You need to predict rent accordingly. We are given area and rent here. So you can do linear regression with more variables, but we're just going to look at the area and then from that try to figure out what the rent should be. We plot the graph. And if you look at it here, you can see that the graph is kind of a linear pattern with a little dip in it. So the rent seems to be based on the area. In most of our work as data scientists, we usually try to start with a physical graph if we can. So we can actually look at it and say, hey, does what I'm fitting to this graph look right? You can solve a lot of problems that arise by looking at the graph and saying, no, that doesn't look right at all. Or, oh, I should be looking over here for this. Then we find the mean of area and rent. So the mean just means average. And if you take 1, 2, 3, 4, 5 and add them all together and divide by, in this case, there's 5 areas, you get 3. And the rent is 2, 4, 6, 5, and 8. If you add them all together and divide by 5, you get 5. And we plot the mean on the graph. So you can see right here, here's the mean of the rent and the area. It's kind of a very central point, which is what we're looking for, the average of everything in there. The best fit line passes through the mean. This is real important. When you're eyeballing it, as humans, we can do this fairly easy if it's a straight line through a bunch of data. It gets more complicated mathematically when you start adding multiple variables and instead of a line you have a curve. But for basic linear regression, we're going to draw a line through the data and the line should go through the means. That's going to be part of the best fit for that line. But we see there are multiple lines that can pass through the means. So depending on how you look at it, you can kind of wiggle the line around back and forth. So we keep moving the line to ensure that the best fit line has the least square distance from the data points. And this is, you can see right here residual, we have our data point and then we look at this distance between them and we square that distance. And that's what they mean by the least square distance. We want all those distances to add up to the smallest amount we can. When we talk about that distance, we call it the residual. It equals the y actual minus the y predicted. Very straightforward, we're just looking at the distance. You can accidentally switch these and it'll come out the same because we're going to square it. But when you're working with other sets of linear regression, you want to make sure you do the y actual minus the y predicted. The value of m and c for the best fit line, y equals mx plus c, can be calculated using the mentioned formula. And you can see here we have m equals the number of points, that's what n stands for. Then we have the sigma, the Greek symbol is there, which is a summation of x times y minus the summation of x times the summation of y over the number of the summation of x squared minus the summation of x squared, of x, all of it squared. That can be a little confusing trying to say that. And then of course your c value is going to be the summation of y times the summation of x squared minus the summation of x times the summation of x times y over the total count of the summation x squared minus the summation of x squared. That's a mouthful. Normally we don't worry too much about these formulas other than to know they're there. Now if you're a mathematician, you might go back in there and work on those. And those people who originally started to put together the different models in R, of course, had to know all this math to build them and had to test it out. That's one of the nice things about R. What is important is that you know about these formulas so that you know where it's coming from. So if you're using one linear regression model, this is how this one works. There's other linear regression models based on different math. And so you'd have to be aware when that math changes and how that changes the model. We find the corresponding values. So in this case, if you're going to break this up and you're building your own model instead of using the one in R, you would have your rent, you would have your area, you would find your rent squared, your area squared, and your rent times area. And if we go back one, we can see that that's all the different little pieces in this model. We have x times y, we have x squared, we have the sum of x, which is going to be squared, we have the sum of x, the sum of y. This is the same. These are all the little pieces in here that we see for m equals and c equals. And so once we compute all these, we have 15, 25, 55, 145, 88. Very easy to do on a computer, thankfully. You could have millions of these points and it would do it in a very short period. We can then plug in those values very easily into this formula and get a final answer. And we'll see that m equals 1.3, and c equals 1.1. And then when we take this for the y predicted equals m of I, x of I plus c, we can take these and actually run the data we have. So we're going to see how it predicts. So now we find the value of y predicted. So we have our xn, and we want to know what we think y will be based on our formula we generated, the linear regression formula. And so when we come in here, we have our x, we have our actual y, then we have our y predict, what we think it's going to be. And then we have, we take y minus y predict, and we get those values, minus 0.4, it's off by 0.3, this one's off by 1, this one's off by minus 1.3, by 0.4. And we go ahead and square that, and then we can sum that square and average it out, and we'll get a value. This is just a summation down here of y minus y predicted square is 3.1. And we call that the least square value for this line is 3.1, and we go ahead and divide that by 5. So when we plot the y predict, and this is the best fit line, and you can see that it does a pretty good job going right through the middle of lines. And in something like rent versus area, if you're trying to figure out how much rent to charge or how many people are allowed to be in the area that's going to work. But if you're looking for the rent value compared to the area, this gives you a good idea based on the area of what you should rent the place for. It's close enough that in the business world this would work. You're not computing something down to the millimeters or micrometers or nuclear physics. We're just charging people. And so if you're off by a couple dollars, it's not a big deal. You'll be pretty close to what you think it's worth and get the right value for your property. Use case: predicting the revenue using linear regression. Now that you have a good idea of how linear regression works, and we're kicking back on our lounging sofa today, let's work on a real-life scenario where you have to predict the revenue. So we're going to take a data set, and we'll pull this up in just a minute. We'll have paid, organic, social, and revenue. There are 3 attributes we'll be working on. The first one is our paid traffic, so all the traffic through the advertisement that comes in. The non-paid traffic from search engines. So these are people coming to the website and are doing so because they did a search for something specific, so it's pulling it from your website. All the traffic coming from social networking sites. So we want to know what's coming from Twitter and Facebook, and somehow they've linked into your website and coming into your marketing area to buy something. And we'll use this to predict the revenue. So we want to know how all this traffic comes together and how it's going to affect our sales if the traffic's coming in. We're going to make use of the multiple linear regression model. So you'll see that this is very similar to what we had before, where we had y equals m times x plus c, but instead we have y equals m1 x1 plus m2 x2 plus m3 x3 plus c. M is the slope. So you have M1, M2, M3, the 3 different slopes of the 3 different lines. Y is the revenue, so we're only looking for one variable. And remember, this is regression, so we're looking for a number. X1 is going to be the paid traffic, and of course M1, the corresponding slope. X2, the organic traffic, and X3, the social traffic. We will follow these steps to create the regression model. We'll start by generating inputs using the CSV files. We'll then import the libraries, splitting the data into train and test. Very important whenever you're doing any kind of data science. Applying regression on paid traffic, organic traffic, social traffic. So we're going to apply a regression model on them. And then we're going to validate the model. That's the whole reason we split it to a training and testing, is so we can now validate to see just how good our model is. Now before we open up I always like to just take a quick look at the data itself, and we're using the rev.csv file. And this is a .cs file, or a comma-separated variable file. We'll just open that with WordPad. Any kind of text editor would be nice to show you what's going on. And you can see we have paid, organic, social, and revenue across the top. So those are your titles for your columns, and the values going down. And this is the same as what we saw on the slide just a minute ago. Paid, organic, social, and then the revenue from them. They probably have it in more of a spreadsheet than just a WordPad. And I'm using the newer version of RStudio, which already has a nice layout. It automatically opens up with your console and terminal window down and left. You have your script, and we'll run it in script, and then when I run it line by line in script, you'll see it show up on the console bottom left. I could type it straight into the console and it would do the same thing. And then on the right we have our environment, and under the environment we'll see plots. If you're in an older version, the plots will pop up, and you usually are running just in the console, and then you have to open up a different window to run the script, and you can run the script from there. This opens up everything at the same time when you use the new RStudio setup. And the first thing we want to do is we want to go ahead and generate a variable. We'll call it cells. And we want to load this with our data set. And so in R, we use the less than minus sign. That's the same as assigned to. It's like an arrow pointing at cells. And it says whatever it goes past here is going to be assigned to cells. And we want to read in our CSV file. And then I went ahead and fixed the CSV file up a little bit. When I say the CSV file, I mean the path to it. And we'll go ahead and just paste that in there. And this is my edited version. And you'll see I took wherever we had the backward slash, I switched it for a forward slash, because a backward slash is an escape character, and whenever you're programming in just about any scripting language, you want to do the forward slash instead. So like a good chef, I prepped this and copied it into my clipboard, and we can see the full path here, and the full path ends in our rev.csv file. So that's the path on my machine. And then I'm going to run that, and now we have down here, you see it appear right here. Uh-oh, must have an error in my path. It says object rev not found. Let me fix that real quick and run it again, and this time it does assign the cells the data set, and then we'll just type in cells, and this is the same as printing it. So if you work in other languages, you'll do like print and then cells, or maybe print cells.head if you're in pandas in Python or something like that. But in R, you just type in the variable. We'll run this, and you can see it printed out all those columns. So that's the same thing we just looked at. And it says max print, so it omitted 750 rows, so it has a total of 1,000 rows. And we can scroll up here on our console where the answer came in. And if I scroll up to the top, way up to the top, there we go, you'll see paid, organic, social, and revenue. So everything looks good on this. And then there's a lot of cool things we can do with it. One of the things we can do is I can summary it. So let's do a summary of cells, and we'll run that. And the summary of cells comes in. It tells you your min, first quarter, median, mean, third quarter, max for paid, organic, social. Breaks it up, and you can actually get kind of a quick view as to what the data is doing. You can take more time to study this. A lot of people look at this, and you can see from the median, the mean, that tells you a lot. And it's divided into quarters, so you have your first quarter value and your third quarter set up on there, and max. It just gives you a quick idea of what's going on in the data. The summary is a really wonderful tool. One of the reasons I like to jump into R before I might do a major project in something else, or you can run everything in R. And let's take a look at the head of cells, and let me run this. And you can see it just shows the head of our data, the first 6 rows in this case, and it starts with 1. Important to know, other different systems start with 0 and go up. R is one that starts with the first as 1. And then if we want to do a plot, I'll go ahead and do a plot cells. Another really powerful tool that you can just jump right into with R once you have your data in here. And you'll see that the plot comes over on the right hand side. And what it does is it compares them. So if I look at my paid and my organic, and you cross the two, you'll see there's a nice line down the middle, big black line where it plots the two together. Let me just widen this a little bit so we can see more of it. There we go. The same thing with paid and social, paid and revenue. So each one of these has a clear connection to each other. So that's a good sign. We have a nice correlation between the data, and you can just eyeball that. That's a good way to jump in and explore your data rather quickly and see what's going on. So we'll go ahead and I'll put a pound sign there, hashtag, and splitting the data into training and test data. And we want to split it so that we have something to work with to train our data set. And when we do our data set, you do this with any data set because you want to make sure you have a good model. And then once we've trained it, we're going to take the other set of data we pulled off to the side and we'll test it to see how good it is. If you test it with the training data, it's already got that memorized and should give you a really good answer. In fact, when you get into more advanced machine learning tools, you watch those very closely. You watch your training set and how it does versus your testing set. And if your training set starts doing better than your testing set, then you're starting to overtrain it. Now that's more with deep learning and some other packages that are beyond what we're working with today. But this is important. It's very important to understand that that test and that training correlate with each other and gives you an idea of what's going on, and make sure that you're set up correctly. And we'll go ahead and set a seed of 2, and that's for our random generators, so that when we run them, you could seed them with just there's ways to randomize a number. You could do like date and stuff like that. But that way we always use the same random numbers. So we'll seed it with 2. And then we're going to need a library. In this case, we're going to import the library. And we want to import CA tools. And CA Tools has our split function, so we're going to be able to split our data, along with many of the other tools we're going to need for this example. So they're all built into the CA Tools. That's why we need to import that. A lot of times they call them library, or sometimes you hear them referred to as packages. So let's go ahead and run that line, and that brings the library in, so now we can use all those different tools that are in there. And then I'm going to do a split, and we're going to assign to the split, that's going to be our variable, sample split. Okay, so that's one of the tools we just brought in, is to sample is the actual keyword or the function word, sample.split. And we're going to take our cells and we're going to go ahead and do a split ratio equals to 0.7, and let's do 0.7 so we make sure it knows it's a decimal point or float. And what this is saying is that we're going to take our cells data, the variable we created called cells that has the data in there, and I want to split it, and I'm going to split it so that 70% of it goes in one side, we'll use that for training, and 30% will go into the other side, which we'll use then for testing out our model. Let me go ahead and run that, and let's hold on one second. Got an error there. Spit is definitely very different than split. I don't think we want to spit our data out, which is actually kind of what we're doing, is spitting it out. But we want to split. We want to split the data. So let me get that spelled correctly. And then when I type in split, we can just run that because that's now a variable. You'll see that it has true, false, false, true. So it generates a number of interesting different statistics going across there as far as the way it splits the data. And right here, if you have not used R in a while, or if you're new to R completely, that line 1, that's what that little 1 means down there, and then true, false, false, true. That means that's how we're looking at the data. We're splitting all those different pieces of data in line 1, different directions. And so we now want to create our train set, and we're going to assign that. And when we take it and we assign to the train set a subset of cells, and then the subset of cells is going to be based on split equal, and I put this in brackets, true. So you can see the values down here is capital T, capital R, capital U, capital E. So I just want to reflect that on the train. And this is going to take everything where our split variable is equal to true, and it's going to set cells equal to that. And we'll go ahead and run that. And then we're going to set our test variable as a subset of cells, and if we assign the true to the train set, then we want to assign the false to our test set. So now we'll have this will have 30% of the variables in it, and train will have 70%. We'll go ahead and run that. So we've now created both our training set and our test set, and we can just real quickly type in train, hit the run on there, and you can see our train set. If we scroll way up to the top, we'll have the column names on there, which should match what we had before. Paid, organic, social, and revenue. And then we'll type in test. When I hit run on there, that's going to do the same thing. It'll spit out all the test variables going out. So now that we have the test and train variables, we want to go ahead and create the model. And you'll see this in any of the machine learning tutorials. They always refer to them as models. We're modeling a function of some kind on the data to fit the data, and then we're going to put the test data through there to see how well it does. And so we're going to create the variable called models, and I'm going to assign that LM, that is our linear regression model. I love how simplified R makes it. Just LM, linear regression, and then model, M. I guess it dates back because the linear regression model is like one of the first major models used, so they kept it easy on there. And revenue happens to be the main variable that we want to track. So if you remember correctly from our formula, Y is the revenue, and then we have X is our paid traffic, X2 our organic traffic, and X3 our social traffic. So Y is what we want to predict in here. And then you'll see this notation where we have our squiggle and the period, which means we're going to match up the revenue lines with the lines of the data we're putting in here. And then I'll put comma, and then our data equals train. And of course, that's the training data that we created. So when I hit the run, remember we did all that discussion about all those different functions and formulas to compute our model and how that's set up. When it comes down to it, we spend all our time setting up our data, and then I hit the run button on the single line, and our model's been trained. So we now have a trained model here. And we can do a summary of the model. Summary is such a wonderful command because you can do that on R. That works on all kinds of different things on there. Oops. And of course it does help if I remember that my model has a capital N when I run it. And you'll see right here, it tells you a little bit about the model. Use a summary on there. Comes down here, it has our residuals. This is all the information on there as far as like the minimum, the median, the max. It has all our coefficients in there. if you remember correctly from our formula. Let's just go ahead and switch back over to that. We have M1, X1, M2, X2, M3, X3 plus C. Well, that's right here. Here's our intercept, and then we have our different values for each of these. So you have our intercept, our paid, organic, and social. And then it also shows us error and information on the error. And one of the really nice things about when you're working with R, you can come down here and you see where we have our stars down here, and it says 3 stars, really good. 2 stars, maybe. 1 star, probably no correlation. And we can see with all of these, it has 3 stars on them. So out of 3 stars, we get 3 stars on all of these. There's no 4 stars. 4 stars would mean that you have the exact same data going in as coming out. And then if we're going to do this, we want to actually run a prediction on here. And that's what we saved our test data for. So let's come down here, we'll do our prediction. We'll take this variable and we'll assign it predict model. And remember, the predict comes from when we imported that package, the CA tools. That's all part of the CA tools in there. So we're going to predict, we're going to use the model, and then we're going to use our test data. Pretty straightforward, quick and easy. We'll run this, and then if we go ahead and type in the predict, it'll print out what's in that variable, and you'll see down here the predicted values it expects to come out. It's going to say our revenue is, and it goes through and it gives it both the line number and the actual revenue value. So that's quick and easy. Boy, we got a prediction really fast. And this is also how you would do it if you had new data coming in after this. You could predict the revenue based on these other factors. So now that we have a training model, or we trained the data with our training data, or we trained the model with our training data, and we've done a prediction on our model with our test data, we want to look this up, and we took a quick glance from our training thing. Our training said it trained really well. But that's not the final word on it. The final word is going to be comparing it. So we want to go ahead and we're going to do comparing predicted versus actual values. What I'm going to do is I'm going to do a plot, and I'm going to do our test, and we're going to do test revenue.type equals, and we're going to put this in as a type 1 and then, or L, and then we have LTY equals 1.8, and we're going to set it up for column blue. That's a lot of stuff in there. Let's go ahead and just run that so we can see what that looks like and what's that's doing. It's going to generate this nice graph we see on the right. There's our graph. You can see the data comes up and down. We're plotting the prediction on there, so this is the values we predicted. And then let's go ahead and do lines. And I actually did this backwards, so let me try that again. And we'll start with the red one. We're going to do the first one in red. And I want to start with the actual test revenue. So here's our test revenue, and we'll go ahead and run this. And so we have our red plot over here in red. Go ahead and take a look at that. Pull that over, you can see how that looks. It goes up and down, hard to track there. And then we're going to do a couple things here. We'll plot our test revenue. And then we'll make it a little pretty, although it's kind of hard to see the way I have it scrunched up here on the right as far as size and sizing and everything. But we'll go ahead and have our columns in blue and run our prediction on there too. And you can see they overlap the two graphs. So we have our test revenue and our prediction. And then finally, what I started with is we'll go ahead and plot the prediction fully on the bottom and run that. And if you look over here on the graph, we put the blue lines over the red lines. And so you'll see a couple spots where there's red underneath there, but for the most part, our prediction's pretty right on. So it looks really tight. It looks like a good set of predictions for what we're working on. And this is what we were looking at the slide right before we started diving into the RStudio. We can see in the slide here, here's a red that's a little bit better spread out than what I have on my screen from my RStudio. And the graph shows the predicted revenue. We see that the two lines are very close. So again, they're tight. It's right on. This is what we're looking for in our prediction model. But it's not good enough just having a graph. You always do both. And the reason we do both is you want to have a visual of it, because sometimes you look at these and you get to the graph, you're like, oh my gosh, what is that? And then sometimes you look at the graph and go, that's right on. How come my accuracy doesn't look right? And you realize that your accuracy might be off, or you're plotting it incorrectly. So let's go ahead and look up the accuracy. And we'll use RMSE. That's going to be the variable name we're going to give it. And SQRT, the square root of the mean, and mean just means average. And then we want prediction minus sales revenue, and then we're going to take this whole thing and we're going to square it. So what we've got here is we're going to go through, and let's just explain this formula we're using, is I'm going to look at what I predict it for to be and what the actual sales, what's our prediction versus our sales, in comparison to the revenue. And when we compare those two, we're going to find the average, and then we're going to square each one of those values, and then we're going to average the square and then find the square root of that. And that's quite a mouthful. The reason we do it this way, the reason we square the value and then we find the means, is to generate an answer based on, doesn't matter whether it's plus or minus. And there's a lot of other formulas you can use there to check your accuracy and all kinds of other things you can do. But a quick, straightforward way of doing it is just like this, and then let's go ahead and run this. And then we type in the RMSE, and that'll give us an actual printed value out. Let's just see what that looks like. And so we have 866.6338 for our accuracy. And so when we look at the 866.63 and we compare that to, say, 50,000, that's pretty close. That's actually a pretty good accuracy given this model. It takes a little bit more when you're playing with accuracies and start dividing out other different aspects of it to get something you can communicate better with. But you always start with the square root means. That's always a good place to start.
There's no better time to train yourself in the exciting field of machine learning. If you're looking for a course that covers everything from the fundamentals to advanced techniques like machine learning algorithm development and unsupervised learning, look no further than our Caltech postgraduate program in AI and machine learning in partnership with IBM. This AI and ML course covers the latest tools and technologies from the AI ecosystem and features masterclasses by Caltech faculty and IBM experts, hackathons, and Ask Me Anything sessions. This program showcases Caltech's CTM's excellence and IBM's industry prowess. The Artificial Intelligence course covers key concepts like statistics, data science with Python, machine learning, deep learning, NLP, and reinforcement learning through an interactive learning model with live sessions. Enroll now and unlock exciting AI and ML opportunities. The course link is mentioned in the description box below.
What is logistic regression? Let's say we have to build a predictive model or a machine learning model to predict whether the passengers of the Titanic ship have survived or not, the shipwreck. So how do we do that? So we use logistic regression to build a model for this. How do we use logistic regression? So we have the information about the passengers, their ID, whether they have survived or not, their class and name and so on and so forth. And we use this information where we already know whether the person has survived or not. That is the labeled information. And we help the system to train based on this information, based on this labeled data. This is known as labeled data. And during the process of building the model, we probably will remove some of the non-essential parameters or attributes here. We only take those attributes which are really required to make these predictions. And once we train the model, we run new data through it, whereby the model will predict whether the passenger has survived or not. Let's start with what is supervised learning. Supervised learning is one of the two main types of machine learning methods. Here we use what is known as labeled data to help the system learn. This is very similar to how we human beings learn. So let's say you want to teach a child to recognize an apple. How do we do that? We never tell the child, okay, this is an apple has a certain diameter on the top, a certain diameter at the bottom, and this has a certain RGB color. No, we just show an apple to the child and tell the child this is apple. And then next time when we show an apple, child immediately recognizes, yes, this is an apple. Supervised learning works very similar on the similar lines. So where does logistic regression fit into the overall machine learning process? Machine learning is divided into two types, mainly two types. There is a third one called reinforcement learning, but we will not talk about that right now. So one is supervised learning and the other is unsupervised learning. Unsupervised learning uses techniques like clustering and association, and supervised learning uses techniques like classification and regression. Now, supervised learning is used when you have labeled data. You have historical data, then you use supervised learning. When you don't have labeled data, then you used unsupervised learning. In supervised learning, there are two types of techniques that are used, classification and regression, based on what is the kind of problem we are solving. Let's say we want to take the data and classify it. It could be binary classification, like a 0 or a 1. An example of classification we have just seen, whether the passenger has survived or not survived. It's like a 0 or 1. That is known as binary classification. Regression, on the other hand, is you need to predict a value, what is known as a continuous value. Classification is for discrete values. Regression is for continuous values. Let's say you want to predict a share price, or you want to predict the temperature that will be there. What will be the temperature tomorrow? That is where you use regression. Whereas classification are discrete values. Will the customer buy the product or will not buy the product? Will you get a promotion or you will not get a promotion? I hope you're getting the idea. Or it could be multi-class classification as well. Let's say you want to build an image classification model. So the image classification model would take an image as an input and classify into multiple classes, whether this image is of a cat or a dog or an elephant or a tiger. So there are multiple classes, so not necessarily binary classification. So that is known as multi-class classification. So we are going to focus on classification because logistic regression is one of the algorithms used for classification. Now, the name may be a little confusing. In fact, whenever people come across logistic regression, it always causes confusion because the name has regression in it, but we are actually using this for performing classification. Okay, so yes, it is logistic regression, but it is used for classification. And in case you are wondering, is there something similar for regression? Yes, for regression, we have linear regression. Keep that in mind. So linear regression is used for regression. Logistic regression is used for classification. So in this video, we are going to focus on supervised learning, and within supervised learning, we are going to focus on classification, and then within classification, we are going to focus on logistic regression algorithm. So first of all, classification. So what are the various algorithms available for performing classification? The first one is decision tree. There are of course multiple algorithms, but here we will talk about a few. Decision trees are quite popular and very easy to understand, and therefore they are used for classification. Then we have k-nearest neighbors. This is another algorithm for performing classification. And then there is logistic regression, and this is what we are going to focus on in this video, and we are going to go into a little bit of details about logistic regression.
And if you are an aspiring Python enthusiast or an AI and ML enthusiast looking for online training and graduating from the best universities, or a professional who elicits to switch careers in AI by learning from the experts, then try giving a shot to Simplilearn's postgraduate program in AI and machine learning in collaboration with Purdue University and IBM. And the course link is mentioned in the description box that will navigate you to the course page where you can find a complete overview of the program being offered.
The term generative AI has emerged seemingly out of nowhere in recent months, with a notable surge in interest according to Google Trends even within the past year. The spike in curiosity can be attributed to the introduction of generative models such as DALL-E 2, BART, and ChatGPT. However, what does generative AI entail? As a part of our introductory series on generative AI, this video will provide a comprehensive overview of a subject starting from the basics. The explanation will cater to all levels of familiarity, ensuring that viewers gain a better understanding of how this technology operates and its growing integration to our daily lives. Generative AI is, after all, a tool that is based on artificial intelligence. A professional who elicits to switch careers with AI by learning from the experts. Then try giving a shot Simplilearn's postgraduate program in AI and machine learning from Purdue University in collaboration with IBM. The link in the description box should navigate to the home page where you can find a complete overview of the program being offered. Take action, upskill, and get ahead. What is generative AI? Generative AI is a form of artificial intelligence possesses the capability of to generate a wide range of content including text, visual, audio, and synthetic data. The recent excitement surrounding generative AI stems from the user-friendly interfaces that allow users to effortlessly create high-quality text, graphics, and video within a seconds. Now moving forward, let's see how does generative AI works. Generative AI begin a prompt which can take form of text, image, video, design, audio, musical notes, or any input that AI system can process. Various AI algorithms that generate new content in response to the given prompt. This content can range from essay and problem solution to realistic created using images or audio of a person. In the early stages of generative AI, utilizing the technology involved submitting data through an API or a complex process. Developers need to acquaint themselves with a specialized tool and writing application using programming language like Python. Some of the recent and fully operational generative AIs are Google BART, DALL-E, OpenAI ChatGPT, Microsoft Bing, and many more. So now let's discuss ChatGPT, DALL-E and BARD, which are the most popular generative AI interfaces. So first is DALL-E 2, which was developed using OpenAI GPT implementation in 2021. Exemplify a multimodal AI application. It has been trained on a vast dataset of images and their corresponding textual description. DALL-E is capable of establishing connection between various media forms such as vision, text, audio. It specifically links the meaning of words to visual elements. OpenAI introduced an enhanced version called DALL-E 2 in 2022, which empowers users to generate imagery in multiple styles based on their prompts. And the next one is ChatGPT. In November 2022, ChatGPT, an AI-powered chatbot built on OpenAI GPT 3.5 implementation, gained immense popularity worldwide. OpenAI enabled users to interact with and fine-tune the chatbot's text response through a chat interface with interactive feedback. Unlike earlier version of GPT that was solely accessible via an API, ChatGPT brought a more interactive experience. On March 14, 2023, OpenAI released GPT-4. ChatGPT integrates the conversational history with a user, making a genuine dialogue. Microsoft, impressed by the success of new ChatGPT interface, announced a substantial investment in OpenAI and integrated a version of GPT into its Bing search engine. And the next one is BARD, Google BARD. Google was also an earlier forerunner in advancing transformer AI techniques for language processing, protein analysis, and other content types. It made some of these models open source for researchers but were not made available through a public interface. In response to Microsoft's integration of GPT into Bing, Google hurriedly launched a public-facing chatbot named Google Bard. Bard's debut was met by an error when the language model incorrectly claimed that the Webb telescope was the first to discover a planet in a foreign solar system. As a consequence, Google's stock price suffered a significant decline. Meanwhile, Microsoft's implementation of ChatGPT and GPT-powered system also faced criticism for producing inaccurate results and displaying erratic behavior in their early iteration. So, moving forward, let's see what are the use cases of generative AI. Generative AI has broad applicability and can be employed across a wide range of use cases to generate diverse forms of content. Recent advancements like GPT have made this technology more accessible and customizable for various applications. Some notable use cases for generative AI are as follows. Chatbot implementation. Generative AI can be utilized to develop chatbots for customer service and technical support, enhancing interaction with users and providing efficient assistance. The second one is language dubbing enhancement. In the realm of movies and educational content, generative AI can contribute to improving dubbing in different languages, ensuring accurate and high quality translation. And the third one is content writing. Generative AI can assist in writing email responses, dating profiles, resumes, and term papers, offering valuable support and generating customized content tailored to specific requirements. And the fourth one is art generation. Leveraging generative AI, artists can create photorealistic artwork in various styles, enabling the exploration of new artistic expression and enhancing creativity. The fifth one is product demonstration videos. Generative AI can enhance product demonstration video, making them more engaging, visually appealing, and effective in showcasing product features and benefits. So generative AI versatility allows it to employed in many other applications, making it a valuable tool for content creation and enhancing user experience across diverse domains. So after seeing use cases of generative AI, let's see what are the benefits of generative AI. So generative AI offers extensive application across various business domains, simplifying the interpretation and comprehension of existing content while also enabling the automated creation of a new content. Developers are actively exploring ways to leverage generative AI in order to enhance the optimize existing workflows and even to reshape workflows entirely to harness the potential of technology fully. Implementing generative AI can bring numerous benefits, including automated content creation. Generative AI can automate the manual process of writing content, saving time and effort by generating text or other form of content. The next one is efficient email response. Responding to emails can be made more efficient with generative AI, reducing the effort required and improving response time. And the third one is enhanced technical support. Generative AI can improve responses to specific technical queries, providing accurate and helpful information to users or customers. And the fourth one is realistic person generation. By leveraging generative AI, it becomes possible to create realistic representation of people, enabling applications like virtual characters or avatars. And the fifth one is coherent information summarization. Generative AI can summarize complex information into a coherent narrative, distilling key points and making it easier to understand and communicate complex concepts. The implementation of generative AI offers a range of potential benefits, streamlining process and enhancing content creation in various areas of business operation. So after seeing advantages of generative AI, let's move forward and see what are the limitations of generative AI. Early implementation of generative AI serve as vivid examples highlighting the numerous limitations associated with this technology. Several challenges arise from the specific approaches employed to implement various use cases. For instance, while a summary of a complex topic may be more reader-friendly than explanation incorporating multiple supporting sources, the ease of readability comes at the expense of transparent identifying the information sources. So the first one is when implementing or utilizing a generative AI application, it is important to consider the following limitation. I repeat, the first one is lack of source identification. Generative AI does not always provide clear identification of content source, making it difficult to trace and verify origin of the information. The second one is assessment of bias. Assessing the bias of original sources used generative AI can be challenging, as it may be difficult to determine the underlying perspective or agenda of the data utilized in the training process. The third one is difficulty in identifying inaccurate information. Generative AI can generate realistic content, making identifying inaccuracy or falsehoods within the generated output harder. And the fourth one is adaptability to a new circumstances. Understanding how to fine-tune generative AI for a new circumstances or specific context can be complex, requiring careful consideration and expertise to achieve desired result. And the fifth one is glossing over bias, prejudice, and hatred. Generative AI results may amplify or perpetuate biases, prejudices, or hateful content present in the training data, requiring vigilant scrutiny to prevent such issues. So, awareness of these limitations is crucial when the implementing of utilizing generative AI, as it helps users and developers critically evaluate and mitigate potential risks and challenges associated with the technology. So, future of generative AI. Furthermore, advances in AI development platforms will contribute to the accelerated progress of research and development in the realm of generative AI. The development will encompass various domains such as text, images, videos, 3D content, drugs, supply chains, logistic, and business processes. While the current standalone tools are impressive, the true transformative impact generative AI will realize while these capabilities are seemingly integrated into the existing tools with regular use.
Hello and welcome to this video on Edge AI for Artificial Intelligence. If you're interested in learning more about how AI is revolutionizing the world around us, this video is for you. Edge AI is a new concept in the world of AI that refers to devices and sensors at the edge of the network that can collect and process data in real time. This allows for faster, more accurate decision-making and greater efficiency in a variety of applications, such as self-driving vehicles, smart homes, and health monitoring. So, how is Edge AI different from cloud computing and cloud computing AI? The main difference is the location where the data is processed. Edge AI enables devices at the edge of the network to process data locally without having to send it to the cloud. This can lead to faster, more responsive systems and can help you preserve bandwidth and reduce latency. In contrast, cloud computing AI processes data in the cloud, where it can access vast amount of data and compute resources, but also requires a reliable internet connection and can be slower. As Edge AI becomes more advanced, it has the potential to transform many industries, such as healthcare, transportation, manufacturing, and a lot more. It can enable new applications such as autonomous vehicles, remote surgery, and real-time monitoring of machines and equipments. While cloud computing AI has many benefits, Edge AI offers the advantages of faster decision-making, reduced latency, and improved efficiency. So, if you're interested in learning more about the future of AI, Edge AI is definitely a topic worth exploring. On that note, hello everyone and welcome to Simplilearn. In today's video, we'll understand what edge computing is and how it is different from traditional cloud computing. But before we begin, Make sure to subscribe to our channel to stay updated with all the latest technologies and hit that bell icon to never miss any updates from us. So without any further delay, let's get started.
But wait, if you want to become an expert in edge computing, then look no further than Caltech postgraduate program in AI and machine learning offered by Simplilearn, which is an online program designed to provide students with a comprehensive understanding of AI and machine learning concepts, tools, and techniques. This program is created in collaboration with Caltech CTME and IBM, and it is designed to provide learners with a strong foundation in AI and machine learning concepts. This program covers various topics such as data science, statistics, deep learning, computer vision, and NLP, and help you gain the right skill set on various tools such as Keras, Matplotlib, TensorFlow, Django, and many more. Furthermore, the curriculum is structured around interactive online classes, live sessions with industry experts, and hands-on projects. So why wait? Hurry up! Enroll now in the Caltech postgraduate program in AI and machine learning and create your own successful career. Link is added in the description box below, so make sure you check that out. So without any further ado, let's jump directly into our today's topic. So firstly, let us understand what is edge computing. The term edge computing for AI refers to the process of running AI computations and processing close to the data source or edge devices at the edge of a network, as opposed to relying on centralized cloud-based servers. In order to enable real-time data analysis, quicker response times, and a decreased reliance on cloud infrastructure, it deploys AI models and algorithms directly on edge devices or local servers. AI edge computing typically entails the deployment of lightweight AI models designed to use on edge devices with constrained computational power. Then these models are frequently deployed to the edge after being trained using cloud-based resources. The edge devices gather data from their sensors or from outside sources, process the data locally using the AI models that have been deployed, and give prompt responses or start processes based on the data. But what led to the rise of edge AI? Well, with rapid advancement in technology in every sector, and businesses are looking to increase automation to increase workflow, productivity, and security, and for that, computer programs must be able to identify patterns and carry out tasks repeatedly and safely in order to assist people. Now, the range of tasks that humans perform, however, covers different situations that are impossible to fully describe in codes and rules because the world is very unstructured. Well, with the help of developments in edge AI, machines and gadgets can now function with the intelligence of human cognition wherever they may be. Smart applications with AI capabilities can learn to carry out the same tasks under various conditions, just like in real life. And here are the 3 recent innovations that explain why using AI models at the edge is on the rise. Well, first on the list, we have advancement of neural networks. Now, over the years, as you know, neural networks and related AI infrastructure have advanced and matured, allowing for more generalized machine learning capabilities. This means organizations have to gain a deeper understanding on how to train AI models effectively and deploy them in production at the edge. Development in computational infrastructure. Now, running AI at the edge requires substantial computational power. The field has witnessed notable advancements in computational infrastructure to support AI at the edge. Particularly, recent strides in highly parallel graphic processing units or GPUs and CPUs have enabled efficient execution of neural networks. GPUs are specifically designed to handle complex parallel computation, making them a suitable choice for processing AI workloads. And finally, widespread usage of IoT devices. Now, the widespread adoption of Internet of Things devices has generated vast amounts of data. These devices, such as industrial sensors, smart cameras, and robotics, provide a rich source of data that can be utilized for AI analysis at the edge. The availability of diverse IoT devices and their ability to capture real-time data has facilitated the deployment of AI models at the edge. But why deploy AI at the edge? What are the benefits of edge computing? Now, edge computing for AI addresses the limitations and challenges associated with conventional cloud-centric AI methods. So, here are some of the advantages which it offers. Firstly, decreased latency. Now, by performing AI processing at the edge, there is a significant reduction in network latency since data no longer needs to be transmitted to the cloud and back. This is particularly beneficial for applications that demand real-time responses or decision-making, let's say like autonomous vehicles or industrial automation. Secondly, real-time data analysis. Edge computing for AI enables immediate data analysis and inference directly on the edge devices themselves. This is especially valuable for time-sensitive applications that require real-time insights or predictions, eliminating the need for reliance on cloud connectivity. Enhanced privacy and security. Well, edge computing enhances privacy and security by keeping data and AI processing local. Sensitive information can be processed on the edge devices without being transmitted to the cloud, minimizing the risk of data breaches and ensuring compliance with data privacy regulations. Next, we have bandwidth optimization. Edge computing reduces the volume of data that needs to be transmitted to the cloud, sending only relevant or let's say summarized data. Now, this optimization minimizes bandwidth requirements, reduces network cost, and even lightens the load on the cloud infrastructure in total. And finally, it offers offline functionality. Edge computing enables AI models to function even in situations with limited or no internet connectivity. This capability is crucial for scenarios that require continuous operation in remote or disconnected environments, such as certain IoT applications or field deployments. So these were some of the reasons why we need to deploy AI at the edge and the benefit it's offering. Now comes the main question. How exactly does edge computing works? Well, edge computing is primarily focused on the proximity and location of data processing and storage. The fundamental principle is simple. When it's not feasible to bring data to a centralized data center, the alternative is to bring the data center close to the data. Now, in order to enable machines to perform tasks like, let's say, visual perception, object detection, driving cars, understanding speech, speaking, walking, and emulating other human skills, they need to replicate human intelligence in a functional manner. So for that, AI uses a deep neural network as a data structure to emulate human cognition. These DNNs undergo training in data centers and are exposed to numerous examples of specific task or question type along with their correct answer. And once the training is complete, the model advances to become an inference engine capable of addressing real-world questions. Now from there on, here's how it typically works. Firstly, deployment of inference engine. Now, in edge AI deployments, the inference engine, which is the component responsible for making predictions or performing AI tasks, is deployed on local computers or devices located in diverse environments like factories, hospitals, cars, satellites, homes, and much more. Problem identification and data upload. Now, while the inference engine operates at the edge, it may encounter situations where it struggles to provide accurate predictions or encounter challenging scenarios. In such cases, the problematic data associated with these instances is commonly identified and uploaded to a centralized cloud structure. Now, from there on, there is a continuous cloud-based model training. Now, the cloud infrastructure typically in a data center receives the problematic data from edge devices. Data scientists and AI experts can then utilize this data to refine and train the original AI models further. This involves using the cloud's computational resources, larger data sets, and collaboration tools for model training and improvement. Now, and finally, with the updated model deployed at the edge after being retrained, the AI system continues to operate, gaining new data and insights from its environment. The edge AI model can collect further additional data, which can be periodically uploaded to the cloud and further training and continuous improvement. This feedback loops ensures that the edge AI models become progressively smarter over time. So this is in a nutshell how edge computing for AI works. Hope you have understood. Well, let us talk some of the use cases of edge computing for AI in real world. Well, the combination of AI, IoT, and edge computing has opened up a multitude of opportunities for edge AI, revolutionizing the various aspects of our daily lives. So let's delve into some key areas where edge AI is making a significant impact. First on the list, we have healthcare. Edge AI is enhancing medical diagnostics and patient care. For instance, by deploying AI edge algorithms on medical imaging devices, radiologists can accurately and efficiently identify and analyze pathologies. Wearable devices with local edge analytics enable real-time monitoring of patient data, facilitating any early detection of anomalies and timely interventions. Next, autonomous vehicles. Edge AI plays a pivotal role in enabling real-time navigation and decision-making for autonomous vehicles. AI algorithms running on edge devices within vehicles process sensor data, analyze the environment, and make split-second decisions to ensure safe and efficient driving. Agriculture. Edge AI is being used to address agriculture challenges as well, such as pollination. Autonomous drones equipped with edge AI capabilities can identify and pollinate plants, aiding in crop cultivation and maximizing yields. This application demonstrates the diverse potential of edge AI beyond traditional domains. Next, we have smart home and cities. Now, edge AI enhances the functionality and efficiency of smart homes and cities. Local processing and analysis of data from IoT devices enable real-time automation, energy management, security surveillance, and personalized user experience. Edge AI-powered systems adapt to individual preferences, optimize resources usage, and respond to events in real time. Next, we have industrial applications. Edge AI is transforming industries thoroughly through real-time monitoring, predictive maintenance, and process optimization. Edge devices equipped with AI algorithms analyze sensor data, detect anomalies, and predict equipment failures, reducing downtime and improving efficiency. Next, we have security and surveillance. Well, Edge AI plays a crucial role in security and surveillance, which empowers real-time video analytics for security and surveillance applications. Edge devices with AI capabilities can analyze video feeds locally, detect suspicious activities like theft, identify objects or individuals of interest, and trigger alerts or responses, enhancing security measures and reducing response times. And finally, we have personal devices. Edge AI is increasingly being integrated into personal devices such as your smartphones, laptops, wearables, and smart home assistants. This allows for on-device AI processing, enabling faster and more personalized experience without relying heavily on cloud connectivity, which can support voice recognition, facial recognition, among other features as well. Well, as more businesses and industries recognize the advantage of Edge AI, its adoption is rapidly growing. The ability to process data locally, enhance privacy, reduce latency, and make real-time decisions empowers organizations in various sectors to enhance operations, deliver better services, and improve user experience. So these were some of the real-time applications of Edge AI. And with that, we've come to the end of today's session on what edge computing for AI is.
Hello everyone and welcome to this fantastic video on what is LangChain on the Simplilearn YouTube channel. All of you must be already aware of blockchain, but let me give you a quick refresher. A blockchain is a digital ledger that stores information like a digital database, without a central authority controlling it. Instead, a blockchain is maintained by a network of computers, each one is storing a copy of the ledger. When a new transaction is added to the ledger, the network has to approve it before it can be recorded. Other side, LangChain is like a blockchain but with a few differences. Unlike a blockchain which stores information about financial transaction, LangChain can store any kind of data or information like medical records, supply chain data, or even social media profiles. LangChain's design also allows for private transaction where only a certain people can access and view the stored data, which differs from a regular blockchain. Sounds fascinating, right? Well, it is, and there is a lot more to learn and discuss about blockchain technology in this video. So stay tuned till the very end as we embark on this amazing journey of exploring LangChain. According to recent studies, AI and machine learning related job posting have increased by 344% in the past 5 years. Companies across the globe are actively seeking professionals who can harness the power of data and build intelligent systems. The average salary is $150,000 in the US and 15 lakhs in India. As the field evolves, new job titles and responsibilities are anticipated to cater to industry requirements. Prominent companies like Microsoft, Google, Amazon, IBM, Goldman Sachs, and Apple are actively recruiting machine learning engineers. Hey everyone, welcome to Simplilearn's YouTube channel. But before we dive into that, don't forget to subscribe, like, and share.
There is no better time to train yourself in the exciting field of machine learning. If you are looking for a course that covers everything from the fundamentals to advanced techniques that accelerate your career in AI and ML with our comprehensive postgraduate program in AI and machine learning. Gain expertise in machine learning, deep learning, NLP, computer vision, and reinforcement learning. You will receive a prestigious certificate, exclusive alumni membership, and Ask Me Anything session by IBM. With 3 capstone and 25 plus industry projects using real datasets from Twitter, Uber, and many more, you will gain practical experience. Masterclasses by Caltech faculty and IBM expert, and no top-notch education. Simplilearn's job assist help you to get noticed by leading companies. This program covers statistics, Python, supervised and unsupervised learning, NLP, neural network, computer vision, GAN, Keras, TensorFlow, and many more skills. So enroll now and unlock exciting AI and ML opportunities. The link is in the description box below. So without any further delay, let's get started. So what is LangChain? LangChain is a versatile open source framework that empowers AI developers to integrate large language model LLMs, such as GPT-4 with the external data available in the Python or JavaScript packages. LangChain addresses the limitation of GPT models trained only up until 2021. While GPT-4 models exhibit impressive general knowledge, their potential is greatly enhanced by connecting them to customized data and customized computations. And this is precisely what LangChain facilitates. By enabling LLMs access comprehensive database, LangChain empowers them to generate responses based on the most up-to-date information found in the reports, documents, and website content. Since the launch of GTP4 in March, LangChain has garnered substantial popularity due to its flexibility and the myriad of possibilities it unlocks when combined with the high-powered LLM. So moving forward, let's see why we need LangChain. So LangChain represents a practical solution to overcome this limitation through a practical approach. It involves pre-processing the text corpus by dividing it into manageable chunks or summaries, embedding them in a vector space and subsequently searching for similar chunks when a question is posed. So this methodology of pre-processing, real-time and data collection and interaction with the LLM is not only applicable in the context but also extend to other scenarios such as code semantic search. So LangChain simplifies the composition of these components by offering an abstraction. The simplification of the process, often called prompt plumbing, plays a crucial role and will grow in significance as LLMs becomes more powerful and necessitate the provision of additional data during the prompt execution. So moving forward, let's see how does LangChain work. So LangChain simplifies the process of organizing large volume of data that can be easily accessed by the LLM requiring minimal computational power. It operates by taking a subsequential data source like 50-page PDF and breaking it down into manageable chunks and that are embedded into a vector store. So with the vectorized representation of the extensive document at hand, we can combine them with the LLM to selectively retrieve the necessary information for creating prompt completion pairs. So when we input a prompt into our chatbot equipped with LangChain, it queries the vector store to find pertinent information, a kind of miniature Google tailored to your document. Once the relevant details are obtained, they are combined with the LLM prompts and fed into the LLM to generate our desired response. After that, integration of LangChain with the OpenAI's LLMs also enables the creation of applications capable of taking action, such as web surfing, email sending, and other tasks related to API. And at the end, you will get a reply. So this is how LangChain works with OpenAI's LLMs. Moving forward, let's see some use cases of LangChain. So there is a wide range of potential application for LangChain. Here are few examples. So first one is personal AI email assistant. LangChain can be used to develop an intelligent email assistant that understands and generates responses based on the user's preferences and writing style. The second one is AI study buddy. So LangChain can assist students in their studies by providing real-time access to relevant research papers, textbooks, and educational resources, offering personalized study recommendation and answering theoretical questions. And the third one is AI data analytics. LangChain can be employed to enhance data analytics by allowing large language model to access and analyze vast amount of structured and unstructured data, enabling more comprehensive insight and prediction. And the fourth one is custom company customer service chatbot. LangChain can power chatbots that provide tailored customer service experience by integrating up-to-date company information, product knowledge, and the customer data to offer personalized and accurate responses. And the fifth one is social media content creation. So LangChain can help content creators generate engaging and relevant social media content by leveraging its ability to access the latest information trends and insights from various sources. So these examples illustrate just a fraction of the potential application for LangChain, and its versatility extends to a wide array of other scenarios as well. So after seeing use cases of LangChain, let's move forward and see using OpenAI how LangChain works or not. So welcome to the demo part. So here first we will set up what the problem is using the ChatGPT. So this is the ChatGPT. This is something that we all know, and I'm going to first ask ChatGPT what is LangChain, and we will see what it will say. Okay, so here I will write what is LangChain. So as you can see, it is saying, I'm sorry, but as of my knowledge cutoff in September 2021, I'm not familiar with the term LangChain. It is possible that it could be a term or concept that emerged or became popular at that time. And could you provide more context or details about what you are referring to? That way I can try to assist you better. So as you can see, why this has happened. It is because LangChain is a more recent library. So this is the new library, and LangChain is, I think, published in somewhere around January, and it is new. And ChatGPT has not been trained on the data more recent than, I think, like around 2021. As you can see, it is written here September 2021. Okay, so this is the problem number 1. So let's see the problem number 2. So here I will write, hey chat GPT, tell me how many meetings are blocked today using my Google Calendar. Again, it is saying, I'm sorry, but as an AI language model, I don't have access to personal data about individuals unless it has been shared with me during our conversation. I can browse or retrieve information from your Google Calendar or any other personal documents or accounts. However, if you have access to your Google Calendar, you can easily check the number of meetings blocked today by opening your calendar and looking at the scheduled events for the day. The calendar interfaces should display the number of meetings or events you have scheduled. And why this is happening? Because we are using ChatGPT OpenAI. Okay, but if we will use API of OpenAI, okay, currently I am using the ChatGPT, but if we will use the OpenAI API, so we can connect to our Google Drive, Google Calendar, and anything. After that, we can easily retrieve our information. Okay, so this is where, so as you can see using this image, what LangChain does, okay, is it is going to connect your AI models. Okay, these are the AI models, OpenAI Hugging Faces. So what the LangChain does, okay, using LLMs, it is going to connect to outside sources like Google Drive or Wikipedia, Wolfram, or Google Calendar, anything, to the outside sources. And you can do some really cool things without those outside sources. Okay, you can ask to the chat GPT, and or you can make your own model, LLM model, but without LLM model and LangChain, you can't connect with the outside sources. Okay, so all of a sudden you can start to chain together commands. Okay, that is why the LangChain is used. Chain. Okay, these are the LLM models, OpenAI Hugging Faces, and you can chain both of them using LangChain. Okay, you can chain the outside sources and this LLMs using LangChain. Okay, after chaining LLM and outside sources using LangChain, you can ask any question to them. Okay, what is how many documents I wrote in the last year and this month, or you can say, hey ChatGPT, what's the weather today, to OpenAI, or anything. You can ask these kind of questions. And the application for the LangChain are the endless, and we have already seen some of them. Okay, so now let's see the documentation part of the LangChain, official documentation part of the LangChain. So as you can see, this is the official documentation of the LangChain. Okay, so here as you can see, what is the LangChain? LangChain is a framework for developing application powered with language models, LLM models. It enables applications that are data aware or agentic. So as you can see, there are the certain modules and the example use cases. As you can see, the chatbots, and you can create the chatbots using LLMs like OpenAI, and there are the many things like interaction with APIs, autonomous. Okay, you can check anything. These are some of the modules of the LangChain. LangChain provides standard extendable interfaces. Okay, so these are the modules, and these are the use cases. Okay, ecosystems and the support, API references. These are the API references, how you can use the API. And as you can see, this is the installation part. Using pip, you can install the LangChain, and the conda part is here, the conda install. Okay, so this is this official document, you can go through it and you will definitely learn something if you will go through the official document. What is transfer learning by Simplilearn? Do you know training a classifier to distinguish beverages can help predict the cuisine of an image? To know more about transfer learning and how it works, stay tuned till the end of this video. In this video, we will cover topics like what transfer learning is, how transfer learning works. Moving forward, we will dive into why you should use transfer learning. After that, we will cover the steps to use transfer learning, and at the end, we will see popular model trained using transfer learning. And let me tell you guys that we have regular updates on multiple technologies. If you are a tech geek in a continuous hunt for the latest technological trends, then consider getting subscribed to our YouTube channel and press that bell icon to never miss any update from Simplilearn. By the end of this video, I can ensure that all your questions and doubts related to transfer learning will have been cleared. Also, accelerate your career in AI and ML with our comprehensive postgraduate program in AI and machine learning. Boost your career with this AI and ML course delivered in collaboration with Purdue University and IBM. Learn in-demand skills such as machine learning, deep learning, NLP, computer vision, reinforcement learning, generative AI, prompt engineering, ChatGPT, and many more. You will receive a prestigious certificate and Ask Me Anything session by IBM. With 5 capstone in different domains using real dataset, you will gain practical experience. Master classes by Purdue University and IBM experts ensure top-notch education. Simplilearn Job Assist helps you get noticed by leading companies. This program covers statistics, Python supervised and unsupervised learning, NLP, neural network, computer vision, GAN, Keras, TensorFlow, and many more skills. So why wait? Enroll now and unlock exciting AI and ML opportunities. The course link is in the description box below. So without any further ado, let's get started. So what is transfer learning? Transfer learning is machine learning refers to reusing a pre-trained model to improve prediction on a new task. It involves using knowledge gained from a previous assignment to tackle a related problem. For instance, a model trained to recognize backpacks can also be used to identify other objects like sunglasses. Due to the substantial CPU power required, this approach is widely utilized in computer vision and natural language processing tasks, including sentiment analysis. So moving forward, let's see how transfer learning works. So how does transfer learning work? In computer vision, neural networks have distinct objectives for each layer, detecting edges in the first layer and identifying forms in the middle layer, and capturing task-specific features in the later layer. Transfer learning utilizes the early and center layers for a pre-trained model and only retrains the later layer. It leverages the labeled data from its original task. For instance, if you have a model trained to identify backpacks in images and now want to use it to detect sunglasses, we will retrain the later layers to understand the distinguished features of sunglasses from the other objects. So moving forward, let's see why should you use transfer learning. Transfer learning offers several advantages, including reduced training time, improved neural network performance in most cases, and the ability to work with limited data. Training a neural model from scratch typically requires a substantial amount of data, which may not always be readily available. Transfer learning becomes valuable in such scenarios. Here is why you should consider using transfer learning. First one is efficient use of data. With pre-trained models, you can perform well even with limited training data. That is especially beneficial in tasks like NLP, where obtaining large labeled datasets can be challenging and time-consuming. The second one is faster training. Building a deep neural network from a scratch of a complex task can be time-consuming, taking days or even weeks. By leveraging transfer learning, the training time is significantly reduced as you start with a model that has already learned general features from a related problem. Now moving forward, let's see steps to use transfer learning. The first one is training a model to reuse it. In machine learning, training a model involves providing it with the data to learn patterns and make prediction. Once a model is trained on a specific task, it can be reused and repurposed for related tasks, saving time and computational resources. The second one is using a pre-trained model. A pre-trained model is a model that has already been trained on a large dataset for a specific task. Instead of training a model from scratch, using a pre-trained model as a starting point allows us to benefit from the knowledge it has gained during its previous training. The third one is extraction of features. Feature extraction is a process in which meaningful patterns and characteristics are identified and separated from our raw data. In the context of machine learning, it involves identifying relevant information from input data to feed into a model for a better prediction. The fourth one is extraction of features in neural networks. In neural networks, feature extraction involves identifying important patterns or features in the data at different network layers. The early layers typically capture simple features like edges, while deeper layers capture more complex features relevant to the task at hand. This hierarchical representation enables neural network to learn and generalize from the data effectively. So moving forward, let's see some popular models trained using transfer learning. So numerous machine learning models have been trained using transfer learning. Some popular ones include, the first one is VGG16 and VGG19. These models were trained on the ImageNet dataset for image classification test. The second one is Inception V3. These models were pre-trained on ImageNet and are known for their effectiveness in object detection and object recognition. The third one is BERT, bidirectional encoder representation from transformer. This language model is pre-trained on the extensive text collection and find extensive application in NLP tasks like sentiment analysis and named entity recognition. The fourth one is GPT, Generative Pre-trained Transformer series. These models are pre-trained language models for various NLP tasks. These are just a few examples of pre-trained models that have been used in transfer learning to accelerate training and improve performance across different tasks.
In this video, we are going to take you through an interesting AI tool which can help you in different ways. The Flare AI we are going to discuss, and this AI can help you create your own advertisement. I mean, if you own a product or if you want to advertise something, then this tool is the go-to option for you, and we are going to see how to use this tool in this particular video. But before we begin, if you enjoy watching these videos and if you find them interesting, then subscribe to Simplilearn's YouTube channel because we bring the best videos for you daily. Also hit the bell icon to never miss any updates from Simplilearn. We all know that AI is expanding at a very rapid pace. ChatGPT is a great example. So in this time, bagging a job in this field is super beneficial because of course it offers great salary packages and AI is interesting, as we all know. So on that note, we present to you the Simplilearn's postgraduate program in AI and machine learning in collaboration with Purdue University. Boost your career with this AI and ML course delivered in collaboration with Purdue University and IBM. You can learn in-demand skills such as machine learning, deep learning, NLP, computer vision, reinforcement learning, generative AI, prompt engineering, ChatGPT, and many more. You'll receive a prestigious certificate and Ask Me Anything session by IBM. With 5 capstones in different domains using real data sets, you will gain practical experience as well. Masterclasses by Purdue faculty and IBM experts ensure top-notch education. Simplilearn's Job Assist helps you get noticed by leading companies. So this program covers statistics, Python, supervised and unsupervised learning, NLP, neural networks, computer vision, GANs, Keras, TensorFlow, and many more skills. So enroll now and unlock exciting AI and machine learning opportunities. The link is mentioned in the description box below. So let's begin with Flare AI. What we have to do first is we have to go to Google and just write here Flare AI. Fine. So this is the first option you will get. Click on it, Flare AI. So this is the interface of Flare AI, the AI design tool for branded content. So it can help you with your brand. Definitely you will get better reach because what usually happens is we use different tools like Adobe Photoshop and other tools to just show a brand item in different ways. But with this AI tool, we can use this and it's not time consuming as well. So let's start. What we'll do is we'll write here create with Flare. So here you can see we have a demo video basically. So here you can see we have a product, a perfume bottle, and here we have different items, or we can say different options. We can generate, we can customize, and that's it. Just right here, click generate, it will generate a beautiful image for you. So let's start, or if you want to watch the video, here's the video. So here you can see this image turned into that. So we don't have to do much of editing, everything was done by AI. So let's see how we can do it. So we'll click on create with Flare. Now continue with Google. So you will have to log in. Although it's free to use, this AI tool is completely free. So here we are going to click on create new project. So here you can see we have a box for placing our product here. So let's say we are placing something out of here. Fine. So here you can see we have a Starbucks coffee. Let's place it in the middle. So generated images will appear here. See, here you can see generated images will appear here. It's written.
Now click on generate what you want to do. So here you can see we have different templates. Fine. We have this template, we can use this, we can use any of them. So let's use this one. Fine. And click on this, click on generate. So paper cup on a rock surrounded by trees in front of canyon and river. Fine. So here you can see it's still progressing. And now here you can see we have a coffee mug present over here, Starbucks coffee. If I zoom in for you a little bit, so here you can see how nice it's looking. It's not even looking like that this cup is edited. It's looking like that this cup is actually placed there. So another way, if we want to do the same thing, what we have to do is we have to use Adobe Photoshop, we have to use different tools, right? But here you can see how detailed it is. We have shadows for the cup as well. Not just that, but if you click here on generate, and if you will find the mirror one, you will get to see the reflection completely. So if I click here, paper cup on a wet surface surrounded by rain in front of spotlight and strong shadows. So it's pretty good. We'll copy it as well. We'll need it later on. I'll tell you why we'll need it. So here you can see it's good, right? So here you can see, and here you can see we have a image, the paper cup. What it said, paper cup on a wet surface, the surface is wet, surrounded by rain. So here you can see rain in front of a spotlight and strong shadows. In front of spotlight and strong shadows. So here you can see the shadow of a paper cup. Fine. Similarly, we can use different tools. We have different elements as well. Like if you want to use, for example, if you go on humans, if you want to use, we have a hand thing. So here you can see if you want to put it here, and if you want to bring it to the front, so here you can see it's on a hand. So here you can see how we can use this tool. Fine. So we have a number of options available here. If we'll go to assets, so here you can see we have a perfume bottle as well. We'll delete this one. We'll use a perfume bottle. It's from Chanel. And now what we are going to do is we are going to delete them as well. Now what we are going to do is we are going to generate something else. Fine. So now we are going to use the editor. So here you can see we have a product which is a perfume bottle. So we have to edit the prompt in the form below. Fine. The product is a perfume bottle. Then we have a placement where we want to place it on a mirror. Or here you can see we have different options. So let's say we are using wooden surface surrounded by let's say flowers. Fine. Now create this image in your mind. We have a perfume bottle which is present on a wooden surface. Its placement is on a wooden surface and it is surrounded by flowers. Fine. Now number of results, how many number of results you want? I'll make it extra strong color strength and outline strength, just to show you guys how it looks. Now click on generate and wait for few seconds, not even minutes, but it will be done in few seconds. Here you can see how fast this AI is. So this AI tool is very useful if you have your own brand, if you have your own products, not services but product. So here you can see it's present on a wooden surface and we have flowers on it. Fine. So what we'll do is we'll write here next to orange. Fine. Generate. It totally depends on your creativity, how you want to create your image, how you want to present your brand service or your brand product. So here you can see we are done with almost 85%. We have to wait for few more seconds, not even a minute, as I already mentioned, and it will be done. So here you can see it's present on a wooden surface and the orange is not there. So basically what we have to do is we have to go to generate. We have to use something else then. We'll use almonds. Fine, let's see if it works or not. Perfume bottle on a wooden surface next to almonds in front of spotlight and strong shadow. Okay, we are not going to use this. What we are going to do is nature in the background. Let's see how it looks. Wait for few more seconds and again it will give you an AI generated image which
will be present on a wooden surface next to almonds in front of nature in the background. Now here you can see we have a wooden surface, we have almonds present over here, and we have nature behind it. Wow, it looks fine, not that good. So what we'll do next is we'll write here circular glass platform, and we'll write here next to a mug. We are not going to use jungle, we are going to use orange sunset in the background. Maybe it will look better because sunsets are always beautiful. So let's see how it comes out. So here we have the output. So it's present on a circular glass platform. Okay, it's fine. We have a mug. Okay, the mug is not visible, or maybe this is the mug, it's not that good. And then we have the sunset. So sunset is here you can see. Now the image looks real, that's the point. It's not something that looks like that it's edited or it's just cropped from somewhere and put it over there. No, it looks real, fine, right? It has the shadows and all the edges and saturation, it's changed as per the background. So right now the background is sunset, so here you can see the orange lights here present over here, fine. So that's how you can use this tool to create an advertisement for your brand product. Now the next thing is not just that, but it allows you to upload your own pictures. So it's quite interesting. Let me just delete all of them. So what you have to do is you have to download the picture of your product, upload it from here, and we have a product of an iPhone. So here I have this picture. Okay, so I'll skip this for now because I'm going to show you. If I write here, let's say it's an iPhone, done. Now here you can see we have a product placed here. So here you can see we have a background, right? We have blue and white, this base as well. So the first thing we are going to do is we are going to click on that. We are going to click on edit. Now the best part is we can remove this background, and it turns out to be so good. Let's check it out. So click on remove background. It will take few seconds to remove all this from your background, and you will notice something, that the background, the edges of the phone, how nicely it has done it. So here you can see there is nothing wrong and every edge is perfectly fine, right? The background is completely removed now. Now what we have to do is we have to generate a image. So we have an iPhone, we want it to be presented as circular glass platform. We will do golden sparkles in front of. Let's remove it and see what else we have. Desert in the background. Let's try this, generate it, and it will again take few seconds. So are you guys ready to check out an iPhone present in the desert? So basically the idea of this AI tool is it saves a lot of time for anyone, right? So here you can see the iPhone is present in a circular glass platform, right? And we have, what else we had? Okay, we had golden sparkles. Golden sparkles are here somewhere, and we have a desert in the background. So desert, here you can see we have a desert. Now what we'll do is we'll write here mirror, and we want it to be present in water and droplets. Fine, so let's try it. I haven't tried it either till now, so it will take some time. The iPhone will be placed on water with some droplets surrounding it, and the background will be okay, a mirror. So it looks good, right? So here you can see the shadow, actually the shadow of the phone, how realistic it looks. So this is how you can use this AI tool, and not just that, but you can download your images. So here you can see, click on download image, and done. The image is downloaded, and just click, you have from this to this, and it totally depends on your creativity how you want to present your brand product.
And if you are an aspiring Python enthusiast or an AI and ML enthusiast looking for online training and graduating from the best universities, or a professional who elicits to switch careers in AI by learning from the experts, then try giving a shot to Simplilearn's postgraduate program in AI and machine learning in collaboration with Purdue University and IBM and the course link is mentioned in the description box that will navigate you to the course page where you can find a complete overview of the program being offered.
Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis. X is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3, and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the outcome rather. So for a logistic regression curve, a threshold has to be set, saying that because this is a probability calculation, remember this is a probability calculation, and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them, so it can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. it is trained, and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the height. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this, where you're trying to find continuous values, is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion, that is a no, and this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not, yes, no, right? So there is nothing in between, and what is the employee's rating, okay? And ratings can be continuous, that is not an issue. But the output is discrete in this case, whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right, because it looks like there will be a lot of errors. The root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation, we will see very soon what that equation is, then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process, and this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening, and this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model, we train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. All right, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, alright, so with that, let's go into Jupyter Notebook and see how the code looks.
So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 70, 97, by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now, from here onwards, we are basically once again importing some of the libraries that are required like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now, based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of that entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2. So this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. so that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these two lines, so the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes two parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations that will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values, so which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0, so the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1, and again this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
Okay, so let's summarize what we have learned in this video. We discussed about what is logistic regression and how it fits into the overall machine learning. We discussed about the different types of machine learning and how logistic regression is one of the algorithms for classification. And then we compared logistic regression with linear regression, because the names may be sounding similar, but these are completely different algorithms. Linear regression is used for predicting continuous values, whereas logistic regression is used for finding discrete values. And then we talked about the math behind logistic regression, and we derived that function as well, the sigmoid function. We did a quick tabular comparison between linear and logistic regression. We saw some examples of day-to-day life, how logistic regression is used for solving some of the classification problems. And then in the end, we looked at the code to see how we can implement logistic regression to train the model to identify images.
There's all kinds of regression models that come out of this. So we put them side by side. We have our linear regression, which is a predictive number used to predict a dependent output variable based on independent input variable. Accuracy is measured using least squares estimation. So that's where you take, you could also use absolute value. The least squares is more popular. There's reasons for that mathematically and also for computer runtime. But it does give you an accuracy based on the least square estimation. The best fit line is a straight line, and clearly that's not always used in all the regression models. There's a lot of variations on that. The output is a predicted integer value. Again, this is what we're talking about when we talk about linear regression. And we're talking about regression, it means the numbers coming out. Linear usually means we're looking for that line versus a different model. And it's used in business domain, forecasting stocks. It's used as a basis of most predictions with numbers. So if you're looking at a lot of numbers, you're probably looking at a linear regression model. For instance, if you do just the high lows of the stock exchange, and you're going to take a lot more of that if you want to make money off the stock, you'll find that the linear regression model fits probably better than almost any of the other models, even high-end neural networks and all these other different machine learning and AI models, because they're numbers. They're just a straight set of numbers. You have a high value, a low value, volume, that kind of thing. So when you're looking at something that's straight numbers and are connected in that way, usually you're talking about a linear regression model, and that's where you want to start. A logistic regression model used to classify dependent output variable based on independent input variable. So just like the linear regression model and like all of our machine learning tools, you have your features coming in. And so in this case, you might have label, an image or something like that is probably the very popular thing right now, labeling broccoli and vegetables or whatever. Accuracy is measured using maximum likelihood estimation. The best fit is given by a curve, and we saw that when we're talking about linear regression, you definitely are talking about a straight line, although there is other regression models that don't use straight lines. And usually when you're looking at a logistic regression, the math, as you saw, was still kind of a Euclidean line, but it's now got that sigmoid activation, which turns it into a heavily weighted curve. And the output is a binary value between 0 and 1. And it's used for classification. Image processing, as I mentioned, is what people usually think of, although they use it for classification of like a window of things. So you could take a window of stock history and you could generate classifications based on that and separate the data that way. If it's going to be that this particular pattern occurs, it's going to be upward trending or downward trending. In fact, a number of stock traders use that not to tell them how much to bid or what to bid, but they use it as to whether it's worth looking at the stock or not, whether the stock's going to go down or go up. And it's just a 0 or 1. Do I care? Do I even want to look at it? So let's do a demo so you can get a picture of what this looks like in Python code. Let's predict the price at which insurance should be sold to a particular customer based on their medical history. We will also classify on a mushroom dataset to find the poisonous and non-poisonous mushrooms. And when you look at these two datas, the first one, we're looking at the price. So the price is a number. So let's predict the price which the insurance should be sold to. And the second one is we're looking at either it's poisonous or it's not poisonous. So first off, before we begin the demo, I'm in the Anaconda Navigator. In this one, I've loaded the Python 3.6 and using the Jupyter Notebook. And you can use Jupyter Notebook by itself. You can use the Jupyter Lab, which allows multiple tabs. It's basically the notebook with tabs on it. But the Jupyter Notebook is just fine, and it'll go into Google Chrome, which is what I'm using for my Internet Explorer. And from here, we open up New, and you'll see Python 3. And again, this is loaded with Python 3.6. And we're doing the linear versus logic regression, or logit. You'll see L-O-G-I-T is one of the names that kind of pops up when you do a search on here. But it is a logic. We're looking at the logistic regression models. And we'll start with the linear regression because it's easy to understand. You draw a line through stuff. And so in programming, we got a lot of stuff to unfold here in our startup as we preload all of our different parts. And let's go ahead and break this up. We have at the beginning import pandas. So this is our data frame. It's just a way of storing the data. Think of when you talk about a data frame, think of a spreadsheet. You have rows and columns. It's a nice way of viewing the data. And then we have, we're going to be bringing in our pre-processing label encoder. I'll show you what that is. When we get down to it, it's easier to see in the data, but there's some data in here like sex. It's male or female, so it's not like an actual number. It's either you're one or the other. That kind of stuff ends up being encoded. That's what this label encoder is right here. We have our test split model. If you're going to build a model, you do not want to use all of the data. You want to use some of the data and then test it to see how good it is. And if it can't have seen the data you're testing on until you're ready to test it on there and see how good it is. And then we have our logistic regression model, our categorical one, and then we have our linear regression model. These are the two, these right here. Let me just clear all that. There we go. These two right here are what this is all about. Logistic versus linear. Is it categorical? Are we looking for a true false, or are we looking for a specific number? And then finally, usually at the very end, we have to take and just ask how accurate is our model. Did it work? If you're trying to predict something, in this case we're going to be doing insurance costs, how close to the insurance cost does it measure that we expect it to be? If you're an insurance company, you don't want to promise to pay everybody's medical bill and not be able to. And in the case of the mushrooms, you probably want to know just how much at risk you are for following this model as to far as whether you're going to eat a poisonous mushroom and die or not. So we'll look at both of those, and we'll talk a little bit more about the shortcomings and the value of these different processes. So let's go ahead and run this. This is loaded the data set on here, and then because we're in Jupyter Notebook, I don't have to put the print on there. We just do data set, and it prints out all the different data on here, and you can see here for our insurance, because that's what we're starting with, we're loading that with our pandas, and it prints it in a nice format where you can see the age, sex, body mass index, number of children, smoker. So this might be something that the insurance company gets from the doctor. It says, hey, this is what we need to know to give you a quote for what we're going to charge you for your insurance. And you can see that it has 1,338 rows and 7 columns. You can count the columns, 1, 2, 3, 4, 5, 6, 7. So there's 7 columns on here. And the column we're really interested in is charges. I want to know what the charges are going to be. What can I expect? Not a very good arrow drawn. What to expect them to charge on there. So is this going to be, is this person going to cost me $16,884, or is this person only going to cost me $3,866? How do we guess that so that we can guess what the minimal charge is for their insurance? And then there's one other thing you really need to notice on this data. And I mentioned it before, but I'm going to mention it again because pre-processing data is so much of the work in data science. Sex. Well, how do you deal with female versus male? Are you a smoker? Yes or no? What does that mean? Region. How do you look at region? It's not a number. How do you draw a line between southwest and northwest? They're objects. It's either your southwest or your northwest. It's not like I'm southwest. I guess you could do longitude and latitude, but the data doesn't come in like that. It comes in as true, false, or whatever. It's either your southwest or your northwest. So we need to do a little bit of pre-processing of the data on here to make this work. Oops, there we go. Okay, so let's take a look and see what we're doing with pre-processing. And again, this is really where you spend a lot of time with data science, is trying to understand how and why you need to do that. And so we're going to do, you'll see right up here, label. And then we're going to do a label encoder, one of the modules we brought in. So this is sklearn's label encoder. I like the fact that it's all pretty much automated, but if you're doing a lot of work with the label encoder, you should start to understand how that fits. And then we have label.fit right here, where we're going to go ahead and do the dataset .sex.drop duplicates. And then for dataset sex, we're going to do the label transform the dataset sex. And so we're looking right here at male or female. And so it usually just converts it to a 0 or 1 because there's only 2 choices on here. Same thing with the smoker. It's 0 or 1, so we're going to change the smoker 0 or 1 on this. And then finally we did region down here. Region does it a little bit different. We'll take a look at that. And I think in this case it's probably going to do it because we did it on this label transform. With this particular setup, it gives each region a number, like 0, 1, 2, 3. So let's go ahead and take a look and see what that looks like. Go and run this. And you can see that our new data set has age, that's still a number. Sex is 0 or 1, so 0 is female, 1 is male. Number of children, we left that alone. Smoker, 1 or 0. It says no or yes on there. We actually just do 1 for no, 0 or no. Yeah, 1 for no. I'm not sure how it organized them, but it turns the smoker into 0 or 1, yes or no. And then region, it did this as 0, 1, 2, 3. So it's 3 regions. Now, a lot of times in when you're working with data science and you're dealing with regions or even word analysis, instead of doing one column and labeling it 0, 1, 2, 3, a lot of times you increase your features, and so you would have region northwest would be one column, yes or no. Region southwest would be one column, yes or no. True, 0, 1. But for this particular setup, this will work just fine on here. Now that we spent all that time getting it set up, here's the fun part. Here's the part where we're actually using our setup on this, and you'll see right here we have our Y linear regression data set drop the charges, because that's what we want to predict. And so our X linear data set drop the charges, because that's what we're going to predict. We're predicting charges right here, so we don't want that as our input for our features. And our Y output is charges. That's what we want to guess. We want to guess what the charges are. And then what we talked about earlier is we don't want to do all the data at once, so we're going to take 0.3, means 30%. We're going to take 30% of our data, and it's going to be as the testing site. So here's our Y test and our X test down there. And so that part, our model will never see it until we're ready to test to see how good it is. And then of course right here you'll see our training set, and this is what we're going to train it. We're going to train it on 70% of the data. And then finally the big ones, this is where all the magic happens. This is where we're going to create our magic setup, and that is right here. Our linear model, we're going to set it equal to the linear regression model, and then we're going to fit the data on here. And then at this point, I always like to pull up, if you're working with a new model, it's good to see where it comes from. And this comes from the scikit-learn, and this is the sklearn linear model, linear regression that we imported earlier. And you can see they have different parameters. The basic parameter works great if you're dealing with just numbers. I mentioned that earlier with stock, high-lows. This model will do as good as any other model out there if you're doing just the very basic high-lows and looking for a linear fit, a regression model fit. And one of the things when I'm looking at this is I look for methods. And you'll see here's our fit that we're using right now, and here's our predict. And we'll actually do a little bit in the middle here as far as looking at some of the parameters hidden behind it, the math that we talked about earlier. And so when we go in this, we go ahead and run this, you'll see it loads the linear regression model and just has a nice output that says, hey, I loaded the linear regression model. And then the second part is we did the fit. And so this model is now trained. Our linear model is now trained on the training data. And so one of the things we can look at is the, for IDX and column name and enumerate X linear trained columns. Kind of an interesting thing. This prints out the coefficients. So when you're looking at the back end of the data, you remember we had that formula, bxx1 plus bxx2 plus the intercept, and so forth. These are the actual coefficients that are in here. This is what it's actually multiplying these numbers by. And you can see like region gets a minus value, so when it adds it up, I guess region. You can read a lot into these numbers. It gets very complicated. There's ways to mess with them. If you're doing a basic linear regression model, you usually don't look at them too closely. But you might start looking in these and saying, hey, you know what, smoker, look how smoker impacts the cost. It's just massive. So this is a flag that, hey, the value of the smoker really affects this model. And then you can see here where the body mass index, so somebody who is overweight is probably less healthy and more likely to have cost money. And then of course age is a factor, and then you can see down here we have sex is then a factor also, and it changes as you go in there. Negative number, it probably has its own meaning on there. Again, it gets really complicated when you dig into the workings and how the linear model works on that. And so we can also look at the intercept. This is just kind of fun. So it starts at this negative number and then adds all these numbers to it. That's all that means. That's our intercept on there. And that fits the data we have on that. And so you can see right here, we can go back and oops, give me just a second. There we go. We can go ahead and predict the unknown data, and we can print that out. And if you're going to create a model to predict something, we'll go ahead and predict it. Here's our Y prediction value, linear model predict. And then we'll go ahead and create a new data frame. In this case, from our X linear test group, we'll go ahead and put the cost back into this data frame. And then the predicted cost, we're going to make that equal to our Y prediction. And so when we pull this up, you can see here that we have the actual cost and what we predicted the cost is going to be. There's a lot of ways to measure the accuracy on there, but we're going to go ahead and jump into our mushroom data. And so in this, you can see here we've run our basic model. We built our coefficients. You can see the intercept, the back end. You can see how we're generating a number here. Now with mushrooms, we want a yes or no. We want to know whether we can eat them or not. And so here's our mushroom file. We're going to go ahead and run this, take a look at the data. And again, you can ask for a copy of this file. Send a note over to simplylearn.com. And you can see here that we have a class, the cap shape, cap surface, and so forth. So there's a lot of feature. In fact, there's 23 different columns in here going across. And when you look at this, I'm not even sure what these particular, like PEE, PE, I don't even know what the class is on this. I'm going to guess by the notes that the class is poisonous or edible. So if you remember before, we had to do a little pre-coding on our data. Same thing with here. We have our cap shape, which is B or X or K. We have cap color. These really aren't numbers, so it's really hard to do anything with just a single number. So we need to go ahead and turn those into a label encoder, which again, there's a lot of different encoders. With this particular label encoder, it's just switching it to 0, 1, 2, 3 and giving it an integer value. In fact, if you look at all the columns, all of our columns are labels. And so we're just going to go ahead and loop through all the columns in the data, and we're going to transform it into a label encoder. And so when we run this, you can see how this gets shifted from XBXXK to 0, 1, 2, 3, 4, 5, or whatever it is. Class is 0, 1, 1 being poisonous, 0 looks like it's editable, and so forth on here. So we're just encoding it. If you were doing this project, depending on the results, you might encode it differently. Like I mentioned earlier, you might actually increase the number of features as opposed to labeling it 0, 1, 2, 3, 4, 5. In this particular example, it's not going to make that big of a difference how we encode it. And then, of course, we're looking for the class, whether it's poisonous or edible. So we're going to drop the class in our X logistics model, and we're going to create our Y logistics model is based on that class. So here's our XY. And just like we did before, we're going to go ahead and split it using 30% for test, 70% to program the model on here. And that's right here. Whoops, there we go. There's our train and test. And then you'll see here on this next setup, this is where we create our model. All the magic happens right here. We go ahead and create a logistics model. I've upped the max iterations. If you don't change this for this particular problem, you'll get a warning that says this has not converged. Because that's what it does, is it goes through the math and it goes, hey, can we minimize the error? And it keeps finding a lower and lower error, and it still is changing that number. So that means it hasn't converged yet. It hasn't found the lowest amount of error it can. And the default is 100. There's a lot of settings in here. So when we go in here to, let me pull that up from the sklearn. So we pull that up from the sklearn model. You can see here we have our logistic. It has our different settings on here that you can mess with. Most of these work pretty solid on this particular setup, so you don't usually mess a lot. Usually I find myself adjusting the iteration, and I'll get that warning and then increase the iteration on there. And just like the other model, you can go, just like you did with the other model, we can scroll down here and look for our methods. And you can see there's a lot of methods available on here, and certainly there's a lot of different things you can do with it. But the most basic thing we do is we fit our model, make sure it's set right, and then we actually predict something with it. So those are the two main things we're going to be looking at on this model, is fitting and predicting. There's a lot of cool things you can do that are more advanced, but for the most part, these are the two which I use when I'm going into one of these models and setting them up. So let's go ahead and close out of our sklearn setup on there, and we'll go ahead and run this. And you can see here it's now loaded this up there. We now have a logistic model, and we've gone ahead and done a predict here also, just like I was showing you earlier. So here's where we're actually predicting the data. So we've done our first two lines of code as we create the model. We fit the model to our training data, and then we go ahead and predict for our test data. Now, in the previous model, we didn't dive into the test score. I think I just showed you a graph, and we can go in there, and there's a lot of tools to do this. We're going to look at the model score on this one. And let me just go ahead and run the model score. And it says that it's pretty accurate. We're getting a roughly 95% accuracy. Wow, that's good. 95% accuracy. 95% accuracy might be good for a lot of things, but when you look at something as far as whether you're going to pick a mushroom on the side of the trail and eat it, we might want to look at the confusion matrix. And for that, we're going to put in our logistic test, the actual values of edible and unedible, and we're going to put in our prediction value. And if you remember on here, let's see, I believe it's poisonous was 1, 0 is edible. So let's go ahead and run that, 0, 1. 0 is good. So here is a confusion matrix, and this is, if you're not familiar with these, we have true, 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 false, true, false, false, false. So it says out of the edible mushrooms, we correctly labeled 1,201 mushrooms edible that were edible. And we correctly measured 1,113 poisonous mushrooms as poisonous. But here's the kicker. I labeled 56 edible mushrooms as being poisonous. Well, that's not too big of a deal. We just don't eat them. But I measured 68 mushrooms as being edible that were poisonous. So probably not the best choice to use this model to predict whether you're going to eat a mushroom or not. And you'd want to dig a little deeper before you start picking mushrooms off the side of the trail. So a little warning there when you're looking at any of these data models, looking at the error and how that error fits in with what domain you're in. Domain in this case being edible mushrooms. Be a little careful. Make sure that you're looking at them correctly. So we've looked at edible or not edible. We've looked at regression model as far as the end values, what's going to be the cost and what our predicted cost is, so we can start figuring out how much to charge these people for their insurance. And so these really are the fundamentals of data science. When you pull them together, when I say data science, I'm talking about your machine learning code. And hopefully you got a little. Classification is probably one of the most widely used tools in machine learning in today's world. It is also one of the simpler versions to start understanding how a lot of machine learning works. We're going to start by taking a look at what exactly is classification, the important terminologies around classification. We'll look at some real-world applications, my favorite, popular classification algorithms. And there are a lot out there, so we're only going to touch briefly on a variety of them so you can see how the different flavors work. And we'll have some hands-on demos in Python embedded throughout the tutorial. Classification. Classification is a task that requires the use of machine learning algorithms to learn how to assign a class label to a given data. You can see in this diagram we have our unclassified data. It goes through a classification algorithms, and then you have classified data. It's hard to just see it as data, and that really is where you kind of start and where you end when you start running these machine learning algorithms and classification. And the classification algorithms is a little black box in a lot of respects. And we'll look into that. You can see what I'm talking about when we start swapping in and out different models. Let's say we are given the task of classifying a given bunch of fruits and vegetables on the basis of their category, i.e. fruits are to be grouped together and vegetables are to be grouped together. And so we have a data set, we'll call it the bunch, is divided into clusters, one of which consists of the fruits, while the other has the vegetables. You can actually look at this as any kind of data. When we talk about breast cancer, can we sort out in images to see what is malignant, what is benign? Very popular one. Can you classify flowers? The iris data set. Certainly in wildlife, can you classify different animals and track where they're going? Classification is really the bottom starting point or the baseline for a lot of machine learning and setting it up and trying to figure out how we're going to break the data up so we can use it in a way that is beneficial. So here the fruits and the vegetables are grouped into clusters, and each cluster has a specific characteristic, i.e. whether they are a fruit or a vegetable. And you can see we have a pile of fruits and vegetables. We feed it into the algorithm, and the algorithm separates them out, and you have fruits and vegetables. So some important terminologies before we dig into how it sorts them out and what that all means. When we look at the terminologies, you have a classifier. That's the algorithm that is used to map the input data to a specific category. The classification model, the model that predicts or draws a class to the input data given for training. Feature, it is an individual measurable property of the phenomena being observed. And labels, the characteristics on which the data points of a data set are categorized. The classifier and the classification model go together. A lot of times the classifier is part of the classification model. And then you choose which classifier you use after you choose which model you're using. Where features are what goes in, labels are what comes out. So your classifier model is right in the middle of that. That's that little black box we were just talking about. Clusters. They are a group of data points which have some common characteristics. Binary classification. It is a classification condition with two outcomes which are either true or false. Multi-label classification. This is a classification condition where each sample is assigned to a set of labels or targets. Multi-class classification, the classification with more than two classes. Here each sample is assigned to one and only one label. When we look at this group of terminologies, a few important things to notice. Going from the top, clusters, when we cluster data together, we don't necessarily have to have an end goal. We just want to know what features cluster together. These features then are mapped to the outcome we want. In many cases, the first step might not even care about the outcome, only about what data connects with other data. And there's a lot of clustering algorithms out there that do just the clustering part. Binary classification. It is a classification condition with two outcomes which are either true or false. We're talking usually it's either a cat or it's not a cat. It's either a dog or it's not a dog. That's the kind of thing we talk about binary classification. And then that goes into multi-label classification. Think of label as you can have an object that is brown, you can have an object that is labeled as a dog, so it has a number of different labels. That's very different than a multi-class classification where each one's a binary. You can either be a cat or a dog. You can't be both a cat and a dog. Real-world applications. So to make sense of this, of course, the challenge is always in the details, is to understand how we apply this in the real world. So in real-world applications, we use this all the time. We have email spam classifier. So you have your email inbox coming in. It goes through the email filter that we usually don't see in the background, and it goes, this is either valid email or it's a spam, and it puts it in the spam filter if that's what it thinks it is. Alexa's voice classifier, Google Voice, any of the voice classifiers, they're looking for points, so they try to group words together, and then they try to find those groups of words trigger a classifier. So it might be that the classifier is to open your tasks program or open your text program so that you can start sending a text. Sentiment analysis is really big. When we're tracking products, we're tracking marketing, trying to understand whether something is liked or disliked is huge. That's like one of the biggest driving forces in sales nowadays, and you almost have to have these different filters going on if you're running a large business of any kind. Fraud detection. You can think of banks. They find different things on your bank statement and they detect that there's something going on there. They have algorithms for tracking the logs on computers. They start finding weird logs on computers. They might find a hacker. I mentioned cat and dog, so here's our image classification. We have a neighbor who runs an outdoor webcam, and we like to have it come up with a classification when the wild animals in our area are out, like foxes. We actually have a mountain lion that lives in the area, so it's nice to know when he's here. Handwriting prediction, classifying A, B, C, D, and then classifying words to go with that. So let's go ahead and roll our sleeves up and take a look at some popular classification algorithms. Before we look at the algorithms, let's go back and take a look at our definitions. We have a classifier and a classification model. So we're looking at the classifier, an algorithm that is used to map the input data to a specific category. One of those algorithms is a logistic regression. The logistic regression is a classification algorithm used to model the probability of a certain class or event existing, such as pass, fail, or win, lose, etc. It provides its output using the logistic function or sigmoid function to return the probability value that can then be mapped to two or more discrete classes. A sigmoid function is an activation function that fits the variable and limit the output to a range between 0 and 1. A standard sigmoid function or logistic function is represented by the formula fx equals 1 over 1 plus e to the minus x, where x is the equation of the line and e is the exponential. Just taking a quick look at this, you can think of this as being a point of uncertainty. And so as we get closer and closer to the middle of the line, it's either activated or not. And we want to make that just shoot way up. So you'll see a lot of the activation formulas kind of have this nice S-curve where it approaches 1 and approaches 0. And based on that, there's only a small region of error. And so you can see in the sigmoid logistic function, the 1 over 1 plus e minus x to the minus x, you can see it frames that nice S-curve. We also can use a tangent variation. There's a lot of other different models here as far as the actual algorithm. This is the most commonly used one. Let's go ahead and roll up our sleeves and take a look at a demo that is going to use a logistic regression. So we're going to have the activation formula and the model, because you have to have both. For this, we will go into our Jupyter notebook. Now, I personally use the Anaconda Navigator to open up the Jupyter notebook to set up my IDE as a web-based. It's got some advantages that it's very easy to display in, but it also has some disadvantages in that if you're trying to do multi-threads and multi-processing, you start running into single get issues with Python, and then I jump to PyCharm. Really depends on whatever IDE you want. Just make sure you've installed NumPy and the sklearn modules into your Python in whatever environment you're working in so that you'll have access to that for this demo. Now, the team in the back has prepared my code for me, which I'll start bringing in one section at a time so we can go through it. Before we do that, it's always nice to actually see where this information is coming from and what we're working with. So the first part is we're going to import our packages, which you need to install into your Python, and that's going to be your NumPy. We usually use NumPy as in P, and then from sklearn, the learn model, we're going to use a logistic regression. And from sklearn metrics, we're going to import the classification report confusion matrix. And if we go ahead and open up the scikit-learn.org and go under their API, you can see all the different features and models they have. And we're looking at the linear model logistic regression, one of the more common classifiers out there. And if we go ahead and go into that and dig a little deeper, you'll see here where they have the different settings. And it even says right here, note, the regularization is applied by default. So by default, that is the activation formula being used. Now, we're not going to we might come back to this, look at some of the other models, because it's always good to see what you're working with. But let's go ahead and jump back in here. And we have our imports. We're going to go ahead and run those. So these are now available to us as we go through our Jupyter Notebook script. And they put together a little piece of data for us. This is simply going through 0 to 1. Actually, let's go ahead and print this out over here. We'll go ahead and print X just so you can see what we're actually looking for. And when we run this, you can see that we have our X is 0, 1, 2 through 9. We reshaped it. The reason for this is just looking for a row of data. Usually we have multiple features. We just have the one feature which happens to be 0 through 9. And then we have our 10 answers right down here. 0, 1, 0, 0, 1, 1, 1, 1, 1, 1. You can bring in a lot of different data depending on what you're working with. You can make your own. You can, instead of having this as just a single, you could actually have like multiple features in here, but we just have the one feature for this particular demo. And this is really where all the magic happens right here. And I told you it's like a black box. That's the part that is kind of hard to follow. And so if you look right here, we have our model. We talked about the model right there, and then we went ahead and set it for library linear. As I showed you earlier, that's actually default, so it's not that important. Random state equals 0. This stuff you don't worry too much about. And then with the scikit-learn, you'll see the model fit. This is very common to scikit. They use similar stuff in a lot of other different packages, but you'll see that that's very common. You have to fit your data. And that means we're just taking the data and we're fitting our X right here, which is our features. That's our X. And here's Y. These are the labels we're looking for. So before we were looking at, is it fraud? Is it not? Is it cat? Is it not? That kind of thing. And this is looking at 0, 1, so we want to have a binary setup on this. And we'll go ahead and run this. You can see right here it just tells us what we loaded it with as our defaults, and that this model has now been created and we've now fit our data to it. And then comes the fun part. You work really hard to clean your data, to bake it and cook it. There's all kinds of, I don't know why they go with the cooking terms as far as how we get this data formatted. Then you go through and you pick your model, you pick your solver, and you have to test it to see, hey, which one's going to be best. And so we want to go ahead and evaluate the model. And you do this is that once you've figured out which one is going to work the best for you, you want to evaluate it so you can compare it to your last model. And you can either update it to create a new one, or maybe change the solver to something else. I mentioned tangent. That's one of the other common ones that's commonly used with language. For some reason, the tangent, even though it looks almost to me identical to the one we're using with the sigmoid function, for some reason it activates better with language, even though it's a very small shift in the actual math behind it. We already looked at the data early, but we'll go ahead and look at it again just so you can see what we look at. We have our rows of 0, 1, row, it only has one entity. And we have our output that matches these rows, and these do have to match. You'll get an error if you put in something with a different shape. So if you have 10 rows of data and 9 answers, it's going to give you an error because you need to have 10 answers for it. A lot of times you separate this too when you're doing larger models. But for this, we're just going to take a quick look at that. The first thing we want to start looking at is the intercept, one of the features inside our linear regression model. We'll go ahead and run that and print it. You'll see here we have an intercept of minus 1.516. And if we're going to look at the intercept, we should also look at our coefficients. And if you run that, you'll see that we get our coefficient is the 0.7035. You can just think of this as your Euclidean geometry for a very basic model like this, where it intercepts the y at some point and we have a coefficient multiplying by it. A little more complicated in the back end, but that is the gist of this simple model with just the one feature in there. And we'll go ahead and we'll reprint the y because I want to put them on top of each other with the y predict. And so these were the y values we put in, and this is the y predict we had coming out. And you can see, here we go. There's the y actual, and there's what the prediction comes in. Now keep in mind that we used the actual complete data as part of our training. That is, if you're doing a real model, a big stopper right there, because you can't really see how good it did unless you split some data off to test it on. This is the first step, is you want to see how your model actually tests on the data you trained it with. And you can see here, there is this point right here where it has it wrong, and this point right here where it also has it wrong. And it makes sense because our input is 0 through 9, and it has to break it somewhere, and this is where the break is. So it says this half the data is going to be 0 because that's what it looked like to me if I was looking at it without an algorithm, and this data is probably going to be 1. And I forgot to point this out, so let's go back up here. I just kind of glanced over this window here where we did a lot of stuff. Let's go back and just take a look at that. What was done here is we ran a prediction. So this is where our predict comes in, is our model.predict. So we had a model fit, We created the model, we programmed it to give us the right answer. Now we go ahead and predict what we think it's going to be. There's our model.predict probability of X. And then we have our Y predict, which is very similar, but this has to do more with the probability numbers. So if you remember down below, we had the setup where we're looking at that sigmoid function. That's what this is returning. And the Y predict is returning a 0 or a 1. And then we have our confusion matrix. We'll look at that. And we have our report, which just basically compares our Y to our Y predict, which we just did. It's kind of nice. It's simple data, so it's really easy to see what we're doing. That's why we use the simple data. This can get really complicated when you have a lot of different features and things going on and splits. So here we go. We've had I printed out our actual and our prediction. So this is the actual data. This is what the predict ran. And then we'll go ahead and we're going to print out the confusion matrix. We were just talking about that. This is great if you have a lot of data to look at. But you can see right here our confusion matrix says, if you remember from the confusion matrix, we have the 2. This is 2 correct. 1, 2. And it's been a while since I looked at a confusion matrix. There's the 2, and then we have this one, which is our 6. That's where the 6 comes from. And then we have this one, which is the 1 false. This is the 2 1s. So we have this one here and this one here, which is misclassified. This really depends on what data you're working with as to what is important. You might be looking at this model, and if this confusion matrix comes up and says that you've misclassified even one person as being non-malignant cancer, that's a bad model. I wouldn't want that classification. I'd want this number to be 0. I wouldn't care if this false positive was off by a little bit more, as long as I knew that I was correct on the important factor that I don't have cancer. So you can see that this confusion matrix really aims you in the right direction of what you need to change in your model, how you need to adjust it. And then there's, of course, a report. Reports are always nice. If you notice, we generated a report earlier. We'll go and just print the report up, and you can remember this is our report. It's a classification report, Y, Y predict. So we're just putting in our 2 values. Basically what we did here visually with our actual and our predicted value. And we'll go ahead and run the report. And you can see it has the precision, the recall, your F1 score, your support, translated into accuracy, macro average, and weighted average. So it has all the numbers. A lot of times when working with clients or with the shareholders in the company, this is really where you start, because it has a lot of data and they can just kind of stare at it and try to figure it out. And then you start bringing in like the confusion matrix. I almost do this in reverse as to what they show. I would never show your shareholders the intercept of the coefficient. That's for your internal team only working on machine language. But the confusion matrix and the report are very important. Those are the 2 things you really want to be able to show on these. And you can see here we did a decent job of classifying the data, managed to get a significant portion of it correct. We had our accuracy here is a 0.80 F1 score, that kind of thing. So, it's a pretty accurate model. Of course, this is pretty goofy because it's a very simple model, and it's just splitting the model between 1s and 0s. So that was our demo of the on logistic regression on there. Let's go and take a look at K nearest neighbors. This one is another very highly used and important algorithm to understand. K nearest neighbors is a simple algorithm which stores all available cases and classifies new cases based on the similarity measure. The K nearest neighbor finds out the class of the new data point by finding its nearest neighbors. If there are 3 data points of class A and 2 data points of class B near to the new data point, then the KNN classifies the new data point as class A. The K in K nearest neighbors is the number of nearest neighbors we are looking for. i.e., if we say K equals 3, this means that we are looking for nearest 3 neighbors of unclassified data point. Usually we take the K value between 3 to 10 as it leads to a better result. A smaller value of K means that noise will have a bigger influence on the result, and a larger value of K makes it computationally expensive. Hence, the data scientists prefer the range of K between 3 and 10. when we talk about noise, you remember the data we just looked at was 0, 1, 1, 0, 0. It had some values where it cut it and said everything to the right is a 1, everything to the left is a 0, but it had some 1s and 0s mixed in there. That's called noise. That's what they're talking about, is there's some things that are right in the middle in the classification, which makes it very hard to classify. So suppose we're trying to find the class for a new point indicated by the red color. And you can see it's kind of right between the cat, right between the dogs. Let k equal 3, so we are finding the 3NN for the red data point. By looking at the plot on the right, we can see that the red data point belongs to the class dogs, as it has 2 votes for class dog and 1 vote for class cat. And if you ask the question, well, what are you measuring the distance? What is that distance? It could be the measurements of the ears, whether they're pointed or floppy. That might be one of the features you're looking at, is how floppy the ears are. Another one might be the whiskers versus the nose. And then you take those measurements, and using one of the most common things in k-means measurement is the Euclidean geometry, you can figure out the distance between those points. There's a lot of different algorithms for that. But you can think about it that you do have to have some kind of solid data to measure. And so we can conclude that the new data point belongs to the class dog. So let's go ahead and see what this looks like in code and do a demo on the k nearest neighbors in here. And we'll go right back into our Jupyter notebook and open up a new Python programming script page. Of course, once we're in here, we'll want to look at the scikit-learn. I did just a quick search for skneighbors, kneighbors classifier. This actually is the older version, 0.023 is the one we want. And you'll see here that we have all their defaults. In neighbors equals 5. At defaults, we were talking about that between 3 and 10. There's different ways to weigh it. There's an algorithm based on it. I mentioned Euclidean geometry, finding the distance. There's other algorithms for figuring out what that distance is and how to weight those. And there's a lot of other parameters you can adjust. For the most part, the k-means basic setup is a good place to start, and just let the defaults go. We might play with some of those. We'll see what the guys in the back did. And from here we're going to import NumPy. We're going to use pandas. If you haven't been running pandas, pandas is our data frame which sits on top of NumPys. Data frames are, NumPys is our number array. Pandas is our data frame. Matplot library, because we're going to plot some graphs. Everybody likes some pretty pictures. It makes it a lot easier to see what's going on when you have a nice display. And that's also what the Seaborn is in here in the setup that sits on top of the Matplot library. The ones we really want to look at right here are what we're bringing in from sklearn. These ones right here. So from sklearn, we're going to load, I mentioned the breast cancer. That's a very popular one because it has, I believe it's 36 measurements, so there's 36 features, and unless you're a expert, you're not going to know what any of those features really mean. You can sort of guess, but there's special measurements they take of when they take an image. And of course our confusion matrix, so that we can take a look and see what the data looks like and how good we did. And then we have our KN neighbors classifier on here. And then I mentioned that whenever you do training and testing, you want to split the data up. You don't want to train the data and then test it on the same data. That just tells you how good your training model is. It doesn't tell you whether it actually works on unknown data. And so this just splits it off so that we can train it, and then we can take a look at data we don't have in there and see how good it did. And we'll go ahead and load our data up. So here's our setup on that. Oops, there we go. So we're going to go ahead and load the data up. We have our X value, and that's going to come from our breast cancer.data and column breast cancer feature names. So there's our actual, all our different features. We'll print that out here in a second. And then we have our mean area, mean compactness. So I guess we're going to take the data and we're only going to use a couple of the columns. This just makes it easier to read. Of course, when you actually we're going to do this, you'd want to use all your columns. And then we have our Y, and this is simply whether it's either malignant or benign. And then we want to go ahead and drop the first line because that's how it came in on there. And we'll go ahead, let's just take a look at this a little closer here. Let's go and run this real quick. And just because I like to see my data before I run it, we can look at this and we can look at the original features. Remember, we're only going to use 2 features off of here just to make it a little easier to follow. And here's the actual data, and you can see that this is just this massive stream of data coming in here. It's going to just skip around because there's so much in there to set up. I think there's like 500 if I remember correctly, and you can see here's all the different measurements they take. But we don't really need to see that on here. We're just going to take a look at just the 2 columns. And then also our solution. We'll go ahead and just do a quick print y on here so you can see what the y looks like. And it is simply just 0, 0, 0, B9, 0, 0, 0, 1. So a 1 means it's B9, a 0 means it's malignant, is what we're looking at on that. Go ahead and cut that out of there. The next stage is to go ahead and split our data. I mentioned that earlier. We'll just go ahead and let them do the splitting for us. We have xtrain, xtest, ytrain, ytest, and so we go ahead and train, test, split, x, y, random state equals 1. It makes it nice and easy for us. We'll go ahead and run that. And so now we have our training and our testing. Train means we're going to use that to train the model, and then we're going to use the test to see how good our model does. And then we'll go ahead and create our model. Here's our KNN model, the k-neighbors classifier. N neighbors equals 5. The metrics is Euclidean. Remember I talked about Euclidean? This is simply your c squared equals a squared plus b squared plus a squared equals b squared plus c squared plus c squared plus d squared, and then you take the square root of all that. That's what they're talking about here. It's just the length of the hypotenuse of a triangle, but you can actually do that in multiple dimensions, just like you do in 2 dimensions with a regular triangle. And here we have our fit. This should start to look familiar since we already did that in our last example. That's very standard for scikit and any other one, although sometimes the fit algorithms look a little bit more complicated because they're doing more things on there, especially when you get into neural networks. And then you have your k-neighbors. It just tells you we created a k-neighbors setup. They kind of wanted us to reformat the y, but it's not that big of a deal for this. And it comes out and shows you that we're using the Euclidean metric for our measurement. So now we've created a model. Here's our live model. We fitted the data to it. We say, hey, here's our training data. Let's go ahead and predict it. So we're going to take our y predict equals knn predict y test. So this is data we have not. This model has not seen this data, and so we're going to create a whole new set of data off of there. Now, before we look at our prediction, in fact, let's. I'm going to bring this down and put it back in here later. Let's take a look at our x test data versus the y test. What does it look like? And so we have our mean area. We're going to compare it to our mean compactness. We're going to go ahead and run that. And we can see here the data, if you look at this, just eyeballing it, we put it in here, we have a lot of blue here, and we have a lot of orange here. And so these dots in the middle, especially like this one here and these here, these are the ones that are going to give us false negatives, and so we should expect this is your noise. This is where we're not sure what it is. And then B9 is, in this case, is done in blue, and malignant is done in 1. So if you look at it, there's 2 points based on these features, which makes it really hard to have 100% where the 100% is down here or up here. That's kind of the thing I'd be looking for when we're talking about cancer and stuff like that, where you really don't want any false negatives. You want everything. False positive, great. You're going to go in there and have another setup in there where you might get an autopsy or something like that done on it. Again, that's very data specific on here. So now let's go ahead and pull in and get our prediction in here, and we'll create our y prediction. We'll go ahead and run that. So now this is loaded with what we think the unknown data is going to be. And we can go ahead and take that and go ahead and plot it, because it's always nice to have some pretty pictures. And when we plot it, we're going to do the mean area versus mean compactness. Again, you look at this map and you can see that there's some clear division here. We can clearly say on some of the stuff that our y prediction, if we look at this map up here, and this map down here, we probably got some pretty good deal. It looks pretty good, like they match a lot. This is, of course, just eyeballing it. Really, you don't want to eyeball these things. You want to show people the pictures so that they can see it, and you can say, hey, this is what it looks like. But we really want the confusion matrix. And when we do the y test and the y predict, we can see in the confusion matrix here, it did pretty good. And we'll just go ahead and point that out real quick. Here's our 42, which is positive, and our 79, And if I remember correctly, I'd have to look at the data, which one of these is a false negative. I believe it's the 9. That's scary. I would not want to be one of those 9 people told that I don't have cancer and then suddenly find out I do. So we would need to find a way to sort this out. And there is different ways to do that. A little bit past this, but you can start messing with the actual Euclidean geometry and the activation measurements and start changing those and how they interact. But that's very advanced. There's also other ways to classify them or to create a whole other class right here of we don't knows. Those are just a couple of the solutions you might use for that. But for a lot of things, this works out great. You can see here, maybe you're trying to sell something. Well, if this was not life dependent, and this was, if I display this ad, 42 of these people are going to buy it. And if I display this other ad, if I don't display it, 79 people are going to go a different direction or whatever it is. So maybe you're trying to display whether they're going to buy something if you add it on to the website. In which case, that's really a good numbers. You've just added a huge number of cells to your company. So that was our K nearest neighbors. Let's go ahead and take a look at support vector machines. So support vector machines is the main objective of a support vector machine algorithm is to find a hyperplane in an n-dimensional space, n is the number of features, that distinctly classifies the data points. And if you remember, we were just looking at those nice graphs we had earlier. In fact, let me go ahead and flip back on over there. If we were looking at this data here, we might want to try to find a nice line through the data. And that's what we're talking about with this next setup. So the main objective of support vector machine algorithm is to find a hyperplane in an n-dimensional space. N is the number of features that distinctly classifies the data points. To separate the two classes of data, there are many hyperplanes that can be chosen. Our objective is to find the plane that has the maximum margin, i.e. the maximum distance between data points of both classes. The dimensions of the hyperplane depends on the number of features. If there are 2 input features, then the hyperplane is just a line. If there are 3 features, then the hyperplane becomes a 2-dimensional plane. The line that separates the data into 2 classes is called as support vector classifier, or hard margin. And that's what I just showed you on the other data. You can see here where we look for a line that splits the data evenly. The problem with hard margin is that it doesn't allow outliers and doesn't work with non-linearly separable data. And we just were looking at that. Let me flip back on over here. And when we look at this setup in here, and we look at this data, here we go. Look how many outliers are in here. These are all these blue dots on the wrong side of the line would be considered an outlier, and the same with the red line. And so it becomes very difficult to divide this data unless there's a clear space. There we go. Therefore, we introduce soft margins, which accept the new data point and optimize a model for nonlinear data points. Soft margins pass through the data points at the border of the classes. The support vector machine can be used to separate the 2 classes of shapes. Here we can see that although triangles and diamond shapes have pointy edges, but we are able to classify them in 2 categories using a support vector machine. Let's go ahead and see what that looks like in a demo. We'll flip back on over to our Jupyter notebook. We always want to start with taking a look at the sklearn API, in this case the SVM SVC. There is a significant number of parameters because the SVM has been a lot of development in the recent years and it's become very popular. If we scroll all the way down to methods, you'll see right here is our fit and our predict. That's what you should see in most of the scikit-learn packages. So this should look very familiar to what we've already been working on. And we'll go ahead and bring in our import and run that. We should already have pandas, numpy, our matplot library, which we're going to be using to graph some of the things. A little bit different right here. You'll see that we're going to go ahead and bring in one of the fun things you can do with test data is make circles. Circles are really hard to classify. You have a ring on the inside and a ring on the outside, and you can see where that can cause some issues. And we'll take a look at that a little closer in a minute. Here's our SVM setup on there, and then of course our metrics, because we're going to use that to take a closer look at things. So we go ahead and run this. Whoops, already did. Once we've gone ahead and done that, we're going to go ahead and start making ourselves some data. And this part, probably a little bit more complicated than we need. I'm not going to go too much in detail on it. We're going to make a mesh grid And we'll see what that looks like in a minute. We're defining the minimums. You can see in here, create a mesh grid of points. Here's our parameters of x, y, and h. It's going to return x, x, y, y. You can also send a note to us. Make sure you get a copy of this if you want to dig deeper into this particular code especially. And we have a ymin, ymax, ymin, ymax, plus 1. Here's our mesh grid we're actually going to make, x, x, and y, y. Plot the contours all the way through, and this is just a way of creating data. It's kind of a fun way to create some data. We go plot contours AX, CLF, X, X, Y, Y, and return an out. Add some perimeters here so that when we're doing it, we have our setup on there, train property, and then we'll go ahead and make our data. Just throw that right in there too in the same setup and run that. So now we have X and Y. We're going to make our circles. We have n samples equals samples. In this case, we're going to have 500 samples. We went ahead and gave it noise of 0.05, random state 123. These are all going into, oops, go back up. Here we go. Make our mesh grid, make circles. There it is. So this is going into our make circles up here. And this is part of that setup on this. And then once we've gone ahead and make the circle, let's go ahead and plot it. That way you can see what we're talking about. Right now what I'm saying is really confusing because without a visual it doesn't really mean very much what we're actually doing. So I'm going to go ahead and run this with the plot. And let's go back up here and just take a look. We've made our circle. We have our n samples equals samples. So we're going to have 500. We're going to have training property 0.8. Here's our data frame. We go and load it into the data frame so we can plot it. Groups, df group by label. This is kind of a fun way if you have multiple columns. You can really quickly pull whatever setup is in there. And then we go ahead and plot it. And you can see here we have 2 rings that are formed. And that's all this is doing, is just making this data for us. This is really hard data to figure out. A lot of programs get confused in this because there's no straight line or anything like that. But we can add planes and different setups on here. And so you can see we have some very interesting data. We have our zeros in blue and our ones in the yellow in the middle. And the data points are an XY coordinate plot on this. One of the things we might want to do on here is go ahead and find the min to max ratio set up in there. And we can even do, let's just do a print x so you can see what the data looks like that we're producing on this. There we go. So x equals x minus x min over x max minus x min. All we're doing is putting this between 0 and 1. Whatever this data is, we want a 0 to 1 setup on here. And if you look at this, all our data is 0.8, 0.5. That's what this particular line is doing. That's a pretty common thing to do in processing data, especially in neural networks. Neural networks don't like big numbers. They create huge biases and cause all kinds of problems. And that's true in a lot of our models. Some of the models it doesn't really matter, but when you're doing enough of these, you just start doing them. You just start putting everything between 0 and 1. There's even some algorithms to do that in the sklearn, although it's pretty, as you can see, it's pretty easy to do it here. So let's go ahead and jump into the next thing, which is a linear kind of setup. C equals 1.0. This is the SVM regularization parameter we're going to use. Models, here's our SVM. And let's go and scroll up just a notch. There we go. There we go. So here we are with our model. We're going to create the setup with the SVC. Kernel is linear. And we'll come back to that because that's an important setup in there as far as what our kernel is. And you'll see why that's so important here in a minute, because we're going to look at a couple of these. And so this one is, we're actually going to be changing how that processes it. And then our C, here's our 0.0, and then the rest of this is plotting. We're just adding titles, making the contours so it's a pretty graph. You can actually spend, this would be a whole class just to do all the cool things you can do with scatter plots and regular plots and colors and things like that. In this case, we're going to create a graph with a nice white line down the middle so that you can see what's going on here. And when we do this, you can see that as it split the data, the linear did just that. It drew a line through the data, and it says this is supposed to be blue, and this is supposed to be red, and it doesn't really fit very well. And that's because we used a linear division of the data, and it's not very linear data on there. It's anything but linear. So when we look at that, it's like, well, okay, that didn't work. What's the next option? Well, there's a lot of choices in here. One of them is just simply we can change this from the kernel being linear to poly. And we'll just go back up here and use the same chart. Oops, here we go. So here we go, linear kernel. We'll change this to poly. And then when we come in here and create our model, here's our model up here, linear. We can actually just go right in and change this to the poly model. And if you remember, when we go back over here to the SVC, and let's scroll back up here, there's a lot of different options. Oops, even further. Okay, so when we come up here and we start talking about the kernel, here's the kernel. There's linear, there's poly, RBF, sigmoid, pre-computed. There's a lot of different ways to do this setup, and their actual default is RBF. Very important to note that. So when you're running these models, understanding which parameter really has a huge effect on what's going on. In this particular one with the SVM, the kernel is so important. You really need to know that. And we switched our kernel to poly, and when we run this, you can see it's changed a little bit. We now have quite an interesting looking diagram, and you can see on here it now has these classifications correct, but it messes up in this blue up here, and it messes up on this blue is correct, and this blue is supposed to be red. You can see that it still isn't quite fitting on there. And so that is, when we do a polyfit, you can see if you have a split in data where there's a group in the middle that's one kind of data and the groups on the outside are different, the polyfit or the polykernel is what's going to be fit for that. So if that doesn't work, then what are we going to use? Well, they have the RBF kernel. And let's go ahead and take a look and see what the RBF looks like. And let me go and turn my drawing off. And the RBF kernel, oops, there we go, RBF. And then of course for our title, it's always nice to have it match with the RBF kernel. And we go ahead and run this, and you can see that the RBF kernel does a really good job. It actually has divided the data up on here, and this is the kind of what you expect here was that ring. Here's our inner ring and an outer ring of data, and so the RBF fits this data package quite nicely. And that, when we talk about SVM, it really is powerful in that it has this kind of sorting feature to it in its algorithms. This is something that is really hard to get the SK means to do, or the k-means setup. And so when you start looking at these different machine learning algorithms, understanding your data and how it's grouped is really important. It makes a huge difference as far as what you're computing and what you're doing with it. So that was a demo on the support vector. Certainly you could have continued on that and done like a confusion matrix and all that kind of fun stuff to see how good it was and split the data up to see how it vectorizes. The visual on that's so important. It makes a big difference just to see what it looks like and that giant donut and why it does circles so well, or your poly version or your linear version. So we've looked at some very numerical kind of setups where there's a lot of math involved, Euclidean geometry, that kind of thing. A totally different machine learning algorithm for approaching this is the decision trees. And there's also forests to go with the decision trees. They're based on multiple trees combined. The decision tree is a supervised learning algorithm used for classification. It creates a model that predicts the value of a target variable by learning simple decision rules inferred from the data features. A decision tree is a hierarchical tree structure where an internal node represents features or attribute. The branch represents a decision rule, and each leaf node represents the outcome. And you can see here where they have the first one, yes or no, and then you go either left or right, and so forth. One of the coolest things about decision trees is, and I'll see people actually run a decision tree even though their final model is different, because a decision tree allows you to see what's going on. You can actually look at it and say, why did you go right or left? What was the choice? Where's that break? And that is really nice if you're trying to share that information with somebody else as to why. When you start getting into the why this is happening, decision trees are very powerful. So the topmost node of a decision tree is known as the root node. It learns to partition on the basis of the attribute value. It partitions the tree in a recursive manner. So you have your decision node. If you get yes, you go down to the next node. That's a decision node. And either yes, you go to, if it ends on a leaf node, then you know your answer, which is yes or no. So there's your in classification set up on there. Here's an example of a decision tree that tells whether I'll sleep or not at a particular evening. Mine would be depending on whether I have the news on or not. Do I need to sleep? No. Okay, I'll work. Yes. Is it raining outside? Yes, I'll sleep. No, all work. So I guess if it's not raining outside, it's harder to fall asleep where you have that nice rain coming in. And again, this is really cool about a decision tree is I can actually look at it and go, oh, I like to sleep when it rains outside. So when you're looking at all the data, you can say, oh, this is where the switch comes in. When it rains outside, I'll sleep really good. If it's not raining or if I don't need sleep, then I'm not going to sleep. I'm going to go work. So let's go ahead and take a look at that looks like in the code. Just like we did before, we go ahead and open up the scikit setup just to say what the decision tree classifier has. You have your parameters, which we'll look a little bit more in depth at as we write the code. It has different ways of splitting it. The strategy used to choose a split at each node, criterion, max depth. Remember the tree, how far down do you want it? Do you want it to take up the space of your whole computer with and map every piece of data, or the smaller that number is, the smaller the level of the tree is and the less processing it takes, but it's also more general, so you're less likely to get as in-depth an answer. And then of course minimal samples you need for it to split, samples for the leaves. There's a lot of things in here as far as how big the tree is and how to define it and when do you define it and how to weight it. And they have their different attributes which you can dig deeper into. That can be very important if you want to know the why of things. And then we go down here to our methods, and you'll see just like everything else, we have our fit method, very important, and our predict, the two main things that we use. What we're going to predict our x to be equal to. And we'll go ahead and go up here and start putting together the code. We're going to import our NumPy, our pandas, there's our confusion matrix, our train test split, decision tree classifier. That's the big one that we're actually working with. That's the line right here where we're going to be, decision tree, there it is. Decision tree classifier, that's the one I was looking for. And of course we want to know the accuracy and the classification report on here. And we're going to do a little different than we did in the other examples. And there's a reason for this. Let me go ahead and run this and load this up here. We're going to go ahead and build things on functions. And this is, when you start splitting up into a team, this is the kind of thing you start seeing a lot more, both in teams and for yourself, because you might want to swap one data to test it on a different data depending on what's going on. So we're going to have our import data here, the data set length, the balance, and so forth. This just returns balanced data. Let me just go ahead and print, because I'm curious as to what this looks like. Import data, and it's going to return the balanced data. So if I run that, if we go ahead and print this out here and run that, you can see that we have a whole bunch of data that comes in there, and some interesting setup on here has let's see, BRR. I'm not sure exactly what that represents on here. 111, 112, and so forth. So we have a different set of data here. The shape is 5 columns, 1, 2, 3, 4, 5. It seems to have a number at the beginning, which I'm going to guess BRL, a letter I mean, and then a bunch of numbers in there. 1111. Let's see, down here we got 555 set up on this. And let's see, balanced data. And since it said balanced data, I'm going to guess that B means balanced, R means you need to move it right, and L means it needs to be moved left or skewed to the left. I'm not sure which one. Let's go and close that out. And we'll go ahead and create a function to split the data set. X balance data equals data values. Y balance equals data values of 0. There's that letter. Remember left, right, and balance. And then we're looking for the values of 1 through 5. And we go ahead and split it just like you would X train, Y train set, random state 100. Test size is 0.3, so we're taking 30% of the data. And it's going to return your X, your Y train, your X train, your X test, your Y train, your Y test. Again, we do this because if you're running a lot of these, you might want to switch how you split the data and how you train it. I tend to use a bifold method. I'll take a third of the data and I'll train it on the other 2/3 and test it on that third. And then I'll switch it. I'll switch which third is the test data. And then I can actually take that information and correlate it, and it gives me a really robust package for figuring out what the complete accuracy is. But in this case, we're just going to go ahead. This is our function for splitting data. And this is where it kind of gets interesting, because remember we were talking a little bit about the different settings in our model. And so in here we're going to create a decision tree, but we're going to use the Genie setup. And where did that come from? What's the Genie on here? So if we go back to the top of their page, and we have what criterion are we going to use? We're going to use Genie. They have Genie and entropy. Those are the two main ones that they use for the decision tree. So this one's going to be Genie, and if we're going to have a function that creates the Genie model, and it even goes down here, and here's our fit train of the Genie model, we'll probably also want to create one for entropy. Sometimes I even just, I might even make this just one function with the different setups. And I know one of the things I worked on recently, I had to create one that tested across multiple models. And so I would send the parameters to the models, or I would send this part right here where it says decision tree classifier. That whole thing might be what I send to create the model, and I know it's going to fit. We're going to have our X train, and we're going to have our predict, and all that stuff is the same. So you can just send that model to your function for testing different models. Again, this just gives you one of the ways to do it. And you can see here we're going to train with the Genie, and we're also going to train with the entropy to see how that works. And if you're going to have your models going, two separate models you're sending there, we'll go ahead and create a prediction. This simply is our y predict equals our whatever object we sent, whatever model we sent here, the CLF object, and predict against our x test. And you can see here print y predict and return y predict set up on here. And we'll load that definition up. And then if you're going to have a function that runs a predict and prints some things out, we should also have our accuracy function. So here's our calculate the accuracy. What are we sending? We're sending our y test data. This could also be y actual and y predict. And then we'll print out a confusion matrix. Then we'll print out the accuracy of the score on here and print a report, classification report. Bundle it all together there. So if we bring this all together, we have all the steps we've been working towards, which is importing our data. By the way, you'll spend 80% of your time importing data in most machine learning setups and cooking it and burning it and getting it formatted so that it works with whatever models you're working with. The decision tree has some cool features in that if you're missing data, it can actually pick that up and just skip that and says, I don't know how to split this. There's no way of knowing whether it rained or didn't rain last night, so I'll look at something else, like whether you watched TV after 8 o'clock, that blue screen thing. So we have our function importing our data set. We bring in the data. We split the data, so we have our x test and y train. And then we have our different models, our CLF Genie, so it's a decision tree classifier using the Genie setup, and then we can also create the model using entropy. And then once we have that, we have our function for making the prediction, and we have our function for calculating the accuracy. And then if we're going to have that, we should probably have our main code involved here. This probably looks more familiar if you're, depending on what you're working on. If you're working on like a PyCharm, then you would see this in throwing something up real quick in Jupyter Notebook. So here's our main data import, which we've already defined. We get our split data. We create our Genie. We create our entropy, so there's our two models going on here. There's our two models. So these are two separate data models. We've already sent them to be trained. Then we're going to go ahead and print the results using Genie index. So we'll start with the Genie, and we want to go ahead with the Genie and print our predictions, x test to the Genie, and calculate the accuracy on here. And then we want to print the results using entropy. So this is just the same thing coming down like we did with the Genie. We're going to put out our y predict entropy and our calculations. So let's go ahead and run that and just see what this piece of code does. We do have, like, one of our data is getting a warning on there. That's nothing major because it's just a simple warning. Probably an update of a new version's coming out. And so here we are. We have our data set. It's got 625. You can actually see an example of the data set. B meaning balanced, I guess. And here's our 5 data points. 1, 1, 1, 1 means it's balanced. It's skewed to the right with 1, 1, 1, 2, and so forth on here. And then we're going to go ahead and predict from our prediction whether it's to the right or to the left. You can think of a washing machine that's banging on one side of the thing, or maybe it's an automated car where we're down the middle of the road that's in balance and it starts veering to the right, so we need to correct for it. And when we print out the confusion matrix, we have 3 different variables, R, L, and B. So we should see the 3 different variables on here. And you have, as far as whether it predicts, in this case, the balance. There's not a lot of balanced loads on here. and didn't do a good job guessing whether it's balanced or not. That's what I took from this first one. The second one I'm guessing is the right. So it did pretty good job guessing the right balance. You can see that a bunch of them came up left unbalanced. Probably not good for an automated car, as it tells you 18 out of the 18 missed things and tells you to go the wrong direction. And here we are going the other way, 19 to 71. And of course we can back that up with an accuracy report on here, and you can see the precision, how well the left and right balance is, 79%, 79% precision, and so forth. And then we went and used the entropy, and let me just see if we can get, so we can get them both next to each other. Here's our entropy of our the first setup, our first model, which is the Genie model. 67, 18, 1971, 63, 22, 2070, pretty close. The two models, you know, that's not a huge difference in numbers. This second one of entropy did slightly, it looks like slightly worse, because it did one better as far as the right balance and did, what is this, 4 worse on the left balance or whatever. So slightly worse. If I was guessing between these, I'd probably use the first one. They're so close though that it wouldn't be a clear choice as to which one worked better. And there's a lot of numbers you can play with here which might give better results depending on what the data is going in. Now, one of the takeaways you should have from the different category routines we ran is that they run very similar. You certainly change the parameters in them as to whether you're using what model you're using and how you're using it and what data they get applied to. But when you're talking about the scikit-learn package, it does such an awesome job of making it easy. You split your data up, you train your data, and you run the prediction, and then you see what kind of accuracy, what kind of confusion matrix it generates. So we talk about algorithm selection. Logistic regression, k-nearest neighbors. Logistic regression is used when we have a binomial outcome. For example, to predict whether an email is spam or not, whether the tumor is malignant or not. The logistic regression works really good on that. You can do it in a k-nearest neighbors also. The question is, which one will it work better in? I find the logistic regression models work really good in a lot of raw numbers. So if you're working with, say, the stock market, is this a good investment or a bad investment? So that's one of the things that it handles the numbers better. K-nearest neighbors are used in scenarios where non-parametric, no fixed number of parameters, algorithms are required. It is used in pattern recognition, data mining, and intrusion detection. So K means really good in finding the patterns. I've seen that as a preprocessor to a lot of other processors where you use the k-nearest neighbors to figure out what data groups together. Very powerful package. Support vector machines. Support vector machines are used whenever the data has higher dimensions, the human genome microarray. SVMs are extensively used in the handwriting recognition models. And you can see that we were able to switch between the parabolic and the circular setup on there, where you can now have that donut kind of data and be able to filter that out with the support vector machine. And then decision trees are mostly used in operational researches, specifically in decision analysis to help identify a strategy most likely to reach any goal. They are preferred where the model is easy to understand. I like that last one. It's a good description. Is it easy to understand? So you have data coming in. When am I going to go to bed? You know, was it raining outside? You can go back and actually look at the pieces and see those different decision modes. It takes a little bit more to dig in there and figure out what they're doing, but you can do that, and you can actually help you figure out why. People love it for the why factor. So, strengths and limitations. Big one on all of these. The strengths and limitations, we talk about logistic regressions. The strengths are it is easy to implement and efficient to train. It is relatively easy to regularize the data points. Remember how we put everything between 0 and 1? When you look at logistic regression models, you don't have to worry about that as much. Limitations, it has a high reliance on proper representation of data. It can only predict a categorical outcome. With the k-nearest neighbors, it doesn't need a separate training period. New data can be added seamlessly without affecting the accuracy of the model. Kind of an interesting thing because you can do partial training. That can become huge if you're running across really large data sets or the data is coming in. It can continually do a partial fit on the data with the k-nearest neighbors and continue to adjust that data. It doesn't work on high dimensional and large data sets. We were looking at the breast cancer, 36 different features. What happens when you have 127 features or 1,000,000 features? And you say, well, what do you have 1,000,000 features in? Well, if I was analyzing the legal documents, I might have a tokenizer that splits the words up to be analyzed, and that tokenizer might create 1,000,000 different words available that might be in the document for doing weights. Sensitive to noisy data, outliers, and missing values. That's a huge one with k-nearest neighbors. They really don't know what to do with a missing value. How do you compute the distance if you don't know what the value is? The SVM works more efficiently on high-dimensional data. It is relatively memory efficient. So it's able to create those planes with only a few different variables in there as opposed to having to store a lot of data for different features and things like that. It's not suitable for large data sets. The SVM, you start running this over gigabytes of data, causes some huge issues. Underperforms if the data has noise or overlapping. That's a big one. We were looking at that where the SVM splits it and it creates a soft buffer, but what happens when you have a lot of stuff in the middle that's hard to sort out and doesn't know what to do with? That causes SVM to start crashing or not perform as well. Decision trees. Handles non-linear perimeters and missing values efficiently. The missing values is huge. I've seen this in, the wine tasting data sets where they have 3 different data sets and they share certain features, but then each one has some features that aren't in the other ones and it has to figure out how to handle those. Well, the decision tree does that automatically instead of having to figure a way to fill that data in before processing like you would with the other models. It's easy to understand and has less training period. So it trains pretty quickly. Comes up there and just keeps forking the tree down and moving the parts around. And so it doesn't have to go through the data multiple times, guessing and adjusting. It just creates the tree as it goes. Overfitting and high variance are the most annoying part of it. That's an understatement. That has to do with how many leaves and how many decisions you have it do. The more you have, the more overfit it is to the data. It also, just in making the choices and how the choices come in, it might overfit to a specific feature because that's where it started at and that's what it knows. And it really is challenged with large data sets. They've been working on that with the data forest, but it's not suitable for large data sets. It's really something you'd probably run on a single machine and not across a data pool or anything. Decision tree, one of the many powerful tools in the machine learning library, begins with a problem. I think I have to buy a car. So in making this question, you want to know, how do I decide which one to buy? And you're going to start asking questions. Is the mileage greater than 20? Is the price less than 15? Will it be sufficient for 6 people? Does it have enough airbag, anti-lock brakes? All these questions come up. Then as we feed all this data in, we make a decision. And that decision comes up, oh, hey, this seems like a good idea. Here's a car. So as we go in through this decision process, using a decision tree, we're going to explore this, maybe not in buying a car, but in how to process data. What's in it for you? Let's start by finding out what is machine learning and why we even want to know about it for processing our data. And we'll go into the 3 basic types of machine learning and the problems that are used by machine learning to solve. Finally, we'll get into what is a decision tree. What are the problems a decision tree solves? What are the advantages and disadvantages of using a decision tree? And then we want to dig in a little deep into the mechanics. How does the decision tree work? And then we'll go in and do a case loan repayment prediction where we actually are going to put together some Python code and show you the basic Python code for generating a decision tree. What is machine learning? There are so many different ways to describe what is machine learning in today's world and illustrate it. We're going to take a graphic here and making decisions or trying to understand what's going on. And really underlying machine learning is people wish they were smarter, wish we could understand the world better. And so you can see a guy here who's saying, hey, how can I understand the world better? And someone comes up and says, let's use artificial intelligence. And machine learning is a part of artificial intelligence. And now he gets a big smile on his face because now he has artificial intelligence to help him make his decisions. And they can think in new ways. So this brings in new ideas. So what is machine learning? This is a wonderful graph here. You can see where we have a learn, predict, decide. These are the most basic three premises of machine learning. In learning, we can describe the data in new ways and be able to learn new aspects about what we're looking at. And then we can use that to predict things, and we can use that to make decisions. So maybe it's something that's never happened before, but we can make a good guess whether it's going to be a good investment or not. It also helps us categorize stuff so we can remember it better. So it's easier to pull it out of the catalog. We can analyze data in new ways we never thought possible. And then, of course, there's the very large growing industry of recognize. We can do facial recognition, driver recognition, automated car recognition. All these are part of machine learning. Going back to our guy here who's in his ordinary system and would like to be smarter, make better choices. What happens with machine learning is an application of artificial intelligence wherein the system gets the ability to automatically learn and improve based on experience. So this is exciting because you have your ordinary guy who now has another form of information coming in, and this is with the artificial intelligence, helps him see things he never saw or track things he can't track. So instead of having to read all the news feeds, he can now have an artificial intelligence sorted out so he's only looking at the information he needs to make a choice with. And of course we use all those machine learning tools back in there, and he's now making smarter choices with less work. Types of machine learning. Let's break it into three primary types of learning. First is supervised learning, where you already have the data and the answers. So if you worked at a bank, you'd already have a list of all the previous loans and who defaulted on them and who made good payments on them. You then program your machine learning tool, and that lets you predict on the next person whether they're going to be able to make their payments or not on their loan. If you have one category where you already know the answers, the next one would be you don't know the answers. You just have a lot of information coming in. Unsupervised learning allows you to group liked information together. So if you're analyzing photos, it might group all the images of trees together and all the images of houses together without ever knowing what a house or a tree is. Which leads us to the third type of machine learning. The third type of machine learning is reinforcement learning. Unlike supervised or unsupervised learning, you don't have the data prior to starting. So you get the data one line at a time, and then whether you make a good choice or a bad choice, the machine learning tool has to then adjust accordingly. So you get a plus or minus feedback. You can liken this to the way a human learns. We experience life 1 minute at a time, and we learn from that. And either our memories is good or we learn to avoid something. Problems in machine learning. To understand where the decision tree fits into our machine learning tools, we have to understand the basics of some of the machine learning problems. And three of the primary ones fall underneath classification, problems with categorical solutions like yes or no, true or false, 1 or 0. This might be, does it belong to a particular group? Yes or no. Then we have regression, problems where there's a continuous value needs to be predicted, like product prices, profit. And you can see here, this is a very simple linear graph. You can guess what the next value is based on the first 4. It kind of follows a straight line going up. And clustering. This is problems where the data needs to be organized to find specific patterns, like in the case of product recommendation. They group all the different products that people just like you viewed on a shopping site and say, if people who bought this also bought this. The most commonly used for the decision tree is for classification, for figuring out is it red or is it not? Is it a fruit or is it a vegetable? Yes or no? True, false? Left or right, 0, 1. And so when we talk about classification, we're going to look at the basic machine learning. These are the 4 main tools used in classification. There's Naive Bayes, Logistic Regression, Decision Tree, and Random Forest. The first 2 are for simpler data. So if your data is not very complex, you can usually use these to do a fairly good representation by drawing a line through the data or a curve through the data. They work wonderful in a lot of problems. But as things get more complicated, the decision tree comes in. And then if you have a very large amount of data, you start getting into the random forest. So the decision tree is actually a part of the random forest. But today we're just going to focus on the decision tree. What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is the measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here where I have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the numpy come in for your numbers. It's called NumPython. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it as source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data.values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally, we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here, they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or I'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And that's very common in the sklearn modules, that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test, that's the one we ran the predict on. And then we put in our yPredict in, that's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not.
There's no better time to train yourself in the exciting field of machine learning. If you're looking for a course that covers everything from the fundamentals to advanced techniques like machine learning algorithm development and unsupervised learning, look no further than our Caltech postgraduate program in AI and machine learning in partnership with IBM. This AI and ML course covers the latest tools and technologies from the AI ecosystem and features masterclasses by Caltech faculty and IBM experts, hackathons, and Ask Me Anything sessions. This program showcases Caltech CTM's excellence and IBM's industry prowess. The Artificial Intelligence course covers key concepts like statistics, data science with Python, machine learning, deep learning, NLP, and reinforcement learning through an interactive learning model with live sessions. Enroll now and unlock exciting AI and ML opportunities. The course link is mentioned in the description box below.
Forest. Currently today it's used in remote sensing. For example, they're used in the ETM devices. If you're a space buff, that's the enhanced thermatic mapper they use on satellites, which see far outside the human spectrum for looking at land masses. And they acquire images of the Earth's surface. The accuracy is higher and training time is less than many other machine learning tools out there. Also, object detection, multi-class object detection is done using random forest algorithms. A good example is traffic, where you're trying to sort out the different cars, buses, and things. And it provides a better detection in complicated environments. They're very complicated up there. And then we have another example, Connect. And let's take a little closer look at Connect. Connect, they use a random forest as part of the game console. And what it does is it tracks the body movements and it recreates it in the game. And let's see what that looks like. We have a user who performs a step. In this case, it looks like Elvis Presley going there. That is then recorded so that Connect registers the movement. And then it marks the user based on accuracy. And it looks like we have Prince going on this one. From Elvis Presley to Prince. It's great. So it marks the user based on the accuracy. If we look at that a little closer, we have a training set to identify body parts. Where are the hands? Where are the feet? What's going on with the body? That then goes into a random forest classifier that learns from it. Once we've trained the classifier, it then identifies the body parts while the person's dancing. And it's able to represent that in a computer format. And then based on that, it scores the game and how accurate you are as being Elvis Presley or Prince in your dancing. Let's take an overview of what we're going to cover today. What's in it for you? What we're going to start with is what is machine learning. We're not going to go into detail on that. We're going to specifically look at how the random forest fits in the machine learning hierarchy. Then we're going to look at some applications of random forest. What is classification, which is its primary use? Why use random forest? What's the benefits of it? And how does it actually come together? What is random forest? And then we'll get into random forest and the decision tree, that's like the final step and how it works. And finally, we'll get some Python code in there and we'll use the case, the iris flower analysis. Now, if you don't know what any of these terms mean or where we're going with this, don't worry. We're going to cover all the basics and have you up and running and even doing some basic script in Python by the end. Let's take a closer look at types of machine learning. Specifically, we're going to look at where the decision tree fits in with the different machine learning packages out there. We'll start with the basic types of machine learning. There's supervised learning, where you have lots of data and you're able to train your models. There's unsupervised learning, where it has to look at the data and then divide it based on its own algorithms without having any training. And then there's reinforcement learning, where you get a plus or negative if you have the answer correct. This particular tool belongs to the supervised learning. Let's take a closer look at that, what that means in supervised learning. Supervised learning falls into two groups, classification and regression. We'll talk about regression a little later and how that differs. This particular format goes underneath classification. So we're looking at supervised learning and classification in the machine learning tools. Classification is a kind of problem wherein the outputs are categorical in nature, like yes or no, true or false, or 0 or 1. In that particular framework, there's the KNN, where the NN stands for nearest neighbor, naive Bayes, the decision tree, which is part of the random forest that we're studying today. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area, and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision 3 tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. We have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in 2. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set which has a very high entropy to 2 lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second 2, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has 2 or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out, how does a decision tree work? So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, they're very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle. It's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is, how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by a diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python. And let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there. And let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in 2 more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Pandas is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have them. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now, what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way, when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the three that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into two different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25% we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create two variables. We're going to create two new data frames. One's called train, one's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans. And let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a panda thing, the df columns, and we know the first 4 of them, 0, 1, 2, 3, that'd be the first 4, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first 4. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, pd. Factorize. What's factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this just like when we were up here and I typed in y and it printed out y instead of print y. This does the same thing. It treats this as a variable and prints it out. But if you're actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see in jobs equals 2. You can see the random state equals 0. Those are the 2 that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit, and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only, I think, 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to have, we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today, though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the Setosa, the Virginica, and the Versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal length, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, Setosa, Virginica, and Versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result. And we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for Virginica, and it predicts a 0 for Versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. we want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next two steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the zeros, the ones, and the twos. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes and it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually let's do the first 25 just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head. And you'll see it says Setosa, 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 Setosa. And they match. So the first one is what our forest is doing. And the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in. And then because I'm on the Jupyter notebook, I can do a control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versicolor, Virginica, and the actual species, Setosa, Versicolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have Versicolor where they meet, and you have Virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says Virginica, but it was supposed to be Versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction, and we read it on test features. But, we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as Versicolor and Versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this.
So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with K-means clustering, we will have here, that means K is equal to 2, and we will have 2 clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in K-means clustering is the allocation of 2 centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want 2 clusters, which means K is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. Initially, they are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these 2 clusters. So we have this one initial cluster, this one initial cluster. But as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined, and the original randomly allocated centroid is repositioned to the actual centroid of these new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D, E, and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add B, C to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes: k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students, Students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with. And then as we progress, we keep changing until we get the best clusters. Or there is a technique called elbow technique whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly that to start with randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point. And if required, the data points are reallocated to the new centroids and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares. And the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters. And for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS, because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated, and the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here, but after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned the value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we picked the centroids randomly, so they are not real centroids. So now what we have to do? We have to calculate the actual centroids for each of these groups, which is like the mean position, which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to Ck, and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. x1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing, and that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick k cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to Ck. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each x value from each c value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into k groups because we wanted to create k clusters, right? So we have k groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have k groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group. which means the original point which we thought was the centroid will shift to the new position, which is the actual centroid for each of these groups. Okay, and we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids, and if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have k groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of k-means clustering. We will actually see some live demos in Python Notebook, using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python Notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python Notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python Notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like matplotlib and numpy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4, so it will go ahead and create some test data for us. And this is how it looks. As you can see visually also, we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and it will create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or will actually start from 0, cluster 0, 1, 2, and 3 maybe. And then for each of the observations, it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k means. When we call predict, that is what it does. And we can take a quick look at these y underscore k means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance, and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now the next section of this code is the implementation of a k-means. Now this is kind of a rough implementation of the k-means algorithm. So we will just walk you through, I will walk you through the code at each step what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering, and there is a function or a library calculates for a given 2 pairs of points it will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid. And then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare. And if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop, it only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically, what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about, for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed, using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this. And so this is how the original, the color, the pixel distribution is. These are 2 plots. One is red against green and another is red against blue, and this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in, the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that this is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also three-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors, and this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors, and then we go ahead and apply this and visualize how it is looking for with the new just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering, and we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering, and we use some sample data using blob to just execute the k-means clustering. All right, so
have you ever wondered how your mail provider implements spam filtering, or how online news channels perform news text classification, or how companies perform sentimental analysis of their audience on social media? All of this and more is done through a machine learning algorithm called naive Bayes classifier. What is naive Bayes? Let's start with a basic introduction to the Bayes theorem. named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing two coins. Here we have two quarters, and if we look at all the different possibilities of what they can come up as, we get that they can come up as heads, they can come up as head-tail, tail-head, and tail-tail. When doing the math on probability, we usually denote probability as a P, a capital P. So the probability of getting two heads equals 1/4. You can see on our data set we have two heads, and this occurs once out of the four possibilities. And then the probability of at least one tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting two heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with two coins it's easy to see, but when you have something more complex you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case, the first coin toss will be B and the second coin toss A. This can be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A after given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our two quarters, and we'll notice that the first two probabilities of getting two heads and at least one tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4, or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with two coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in, and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also a reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the two heads and two tails and head tail tail heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like, and then we're going to solve it in Python. And in here we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our 3 inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount, yes or no? Do we have a free delivery, yes or no? On those days, how many people made a purchase, how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy, yes or no? As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember, when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy. It would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally, we look at the probability of B if A. In this case, we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities, and based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB. If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367, which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple, and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all 3 independent variables. Now we can construct the likelihood tables for all 3 of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. We filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these 3 likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We're actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the 3 different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those 3 separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for 3 different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those 3 different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. those are our three variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our three probabilities of A if B multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B being all three categories. Did we have a discount with a purchase? Did we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29%, given these three different variables. So if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on and we're going to do two steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data, so if you have smaller amounts of data, this is a great, powerful tool for that. Handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjusts for that. Those formulas are very automatic, and so you can still get a very solid predictability even if you're missing data or you have overlapping data for 2 completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the 2 overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time so you can walk through it, since we walk through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines and classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. Roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor, inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x. If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplot library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since it's an inline setup, that we want the graphs to show up on this page. Without it in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplot library inline. And then we're going to import NumPy as NP. That's NumberPython, which has a lot of different formulas in it that we use for both of our sklearn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as NP, NumPy as NP. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplotlibary.pyplot as PLT, and you'll see that PLT is a very common setup, as is the SNS, and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of pyplot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. The term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch20 newsgroups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch20 newsgroups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.target names. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp os ms windows.miscellaneous, and it goes all the way down to talk politics.miscellaneous, talk religion.miscellaneous. These are the categories they've already assigned to this news group. And it's called fetch20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter notebook, and let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target_names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into fetch20 newsgroups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals fetch20 newsgroups, subset equals test, and categories equals categories. And let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, lines 58, in article, etc. And you can scroll all the way down and see all the different parts to there. Now, we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter notebook and walk through it. And here we are in our Jupyter notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top, we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the sklearn features extraction.text, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let it know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the tf-idf vectorizer is going to do for us. And then we're going to import our sklearn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes, pretty easy to understand that, where that comes from. And then finally we have the Skylearn pipeline import make pipeline. Now the make pipeline is just a cool piece of code because we're going to take the information we get from the tf-idf vectorizer and we're going to pump that into the multinomial NB. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through, or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the TF-ID vectorizer and then we're going to push that into the multinomial NB. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the train data, and then the train target. Now, the train data has the different articles in it. You can see the one we were just looking at. And the train.target is what category they already categorized that particular article as. And what's happening here is the train data is going into the TF-ID vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, and then puts that into the multinomial NB. And once we go into our naive Bayes, we want to put the train target in there. So the train data that's been mapped to the TF-ID vectorizer is now going through the multinomial NB, and then we're telling it, well, these are the answers. These are the answers to the different documents. So this document that has all these words with these different weights from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels and we're going to set that equal to model.predict. Most of the sklearn use the term .predict to let us know that we've now trained the model and now we want to get some answers. And we're going to put our test data in there because our test data is the stuff we held off to the side. We didn't train it on there and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there or have some missed labels? And then we're going to put that on a heat map so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline. That way my graph shows up on the inline here. And let's walk through the code, and then we'll look at this and see what that means. So make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here from sklearn metrics import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborn, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And do we have other variables that go into the SNS.heatmap? We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS, Windows, miscellaneous. And then finally, we have our plt.x label. Remember, the SNS or the seaborn sits on top of our matplot library, our PLT. And so we want to just tell it x label equals a true is true. The labels are true, and then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides, because they have a black background they put in there that helps it shine a little bit better so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does. As you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it S, a string. And then we're sending it train equals train. We have our training model. And then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train, and I put the equal for model. And then we're going to set the prediction equal to the model.predict S. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words, and then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNamesPredict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word, or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. and it comes back and says it's social, religion, Christian. That's pretty good. Now, note I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE, you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous.
There's no better time to train yourself in the exciting field of machine learning. If you're looking for a course that covers everything from the fundamentals to advanced techniques like machine learning algorithm development and unsupervised learning, look no further than our Caltech postgraduate program in AI and machine learning in partnership with IBM. This AI and ML course covers the latest tools and technologies from the AI ecosystem and features masterclasses by Caltech faculty and IBM experts, hackathons, and Ask Me Anything sessions. This program showcases Caltech CTM's excellence and IBM's industry prowess. The Artificial Intelligence course covers key concepts like statistics, data science with Python, machine learning, deep learning, NLP, and reinforcement learning through an interactive learning model with live sessions. Enroll now and unlock exciting AI and ML opportunities. The course link is mentioned in the description box below.
So when we take our definition or our function and we run all these things through, kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF IDF vectorizer, we threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier. But they're important to know. One of the main uses for the naive Bayes is with the TF IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction and our trained model. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question. Usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or is not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning and is important for better accuracy. So at K equals 3, we can classify, we have a question mark in the middle, as either a square or not. Is it a square or is it, in this case, a triangle? And so if we set K equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put K equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the K changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of K? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right K? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of K, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things and it's going to pick those things and you might get a skewed answer. And if your K is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing K, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your K value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the K value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, it doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having 2 variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have 2 variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the 2 edges of a triangle. We're computing the 3rd edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point. and we placed it there in red. And we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13, and distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer, and it's not a really complicated math. So you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the 3 closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. You know, at 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results, so we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the k-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this, so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, you know, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do it direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, numpy NAN is what that stands for, doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column dot mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NAN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, One of the tricks is you replace it with the average. What is the most common data for that? This way you can still use the rest of those values to do your computation, and it kind of just brings that particular value or those missing values out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you wanted to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle, because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set, we want to look at the I location, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far, we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there, but the actual running of our KNN, we need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our x train equals sc_x dot fit transform. So we're creating the scaler on the x train variable, and then our x test, we're also going to transform it. So we've trained and transformed the x train, and then the x test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replaced that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using k-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be xtrain. Before we do this, let's go ahead and do import math and do math square root length of y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the k neighbors classifier. In neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean is the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score, and finally accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, y test, y predict. So those are the two values we're going to put in there, and let me go ahead and run that and print it out. And the way you interpret this is you have the y predicted, which would be your title up here. We could do, let's just do PRED, predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
So, what is the A-star algorithm? Before we talk about the A-star algorithm, let's talk a bit about search algorithms. In computer science, a search algorithm is an algorithm which typically solves a search problem. They're used to retrieve information which is stored within some data structure like arrays, stacks, trees, hash buckets, etc., or calculate the search space of a problem domain, either with discrete or continuous variables. So consider you have a stack S which contains 4 elements. Now a stack is an ordered collection of items in which you can add a new item and remove an existing item at the same time. In stacks, You can put in an item on top of another item, and you can't access the elements below the top element without removing the top element first. So suppose we want to find the index of say an element in the stack, say 64. So we're gonna run it through a search algorithm to find 64 within our data structure. What this search algorithm is gonna do is that it's gonna take a look at the top element and see that it's not 64. It's gonna remove the top element and move on to the next element. Again, it's gonna compare and see if it's 64. If it's not, this element too will get removed, and then it'll move on to the next element in the stack, which is 64. In this case, it's gonna return the index of this element, which is at stack index 2. And using stack index 2, we can access this element. So in a way, we found the element in the stack. This is how search algorithms work. This is just an instance or a criteria on which we were searching. But using search algorithms, you can have multiple different search conditions. So you can search for every element which is below a certain number, say 40 within this stack. Or you can also search for elements which are at a certain index. So this is how powerful search algorithms are. Some examples of search algorithms include binary search, linear search, jump search, interpolation search, etc. Now, a vital aspect of search algorithms is pathfinding, which is used to find paths that can be taken to traverse from one point to another by finding the most optimum route. The A-star algorithm is one algorithm like this. It is a searching algorithm that is used to find the shortest path between an initial and a final point. So assume that you have a grid or a maze in this case. Your person is at the start, and they have to reach the end of the maze, which is here at this point, denoted by this flag. Now using A-star algorithm, we can perform map traversal and find the shortest path which has to be taken within a map to go from the starting position to the end position. Now, in this case, there are many different paths that can be taken. One option is to go along the top edges of the map. The other one is to go along the bottom edges. And the shortest path, as you can see, which takes only 4 grids, is to go directly through the center of the map, cut across its diagonal, and reach the end. Now, one major aspect of A-star algorithm is that it always takes the shorter paths first, which makes it an optimal and complete algorithm. An optimal algorithm will find the least cost outcome for a problem, while a complete algorithm finds all the possible outcomes of a problem. A-star algorithm combines all of these to find all the possible outcomes of a problem, starting with the least cost solution. Now, this is what makes A-star algorithms so handy. A-star was initially designed as a graph traversal problem to help build a robot that can find its own course. And because of this, it still remains a widely popular algorithm for graph traversal. Now, let's take a look at the basic concept behind the A-star algorithm. So we already know that A-star algorithm is an optimal and complete algorithm. But another aspect that makes it so powerful is the use of weighted graphs in its implementation. A weighted graph is nothing but a graph which uses numbers to represent the cost of taking each path or course of action. This means that the algorithms can take the path with the least cost and find the best route in terms of distance and time. In path finding algorithms, for algorithms such as A-star, you're obviously going to need a graph or a map or a path to travel, right? So for computers, we feed in something called a graph. A graph contains of 2 major components. First, it contains something called a node. So this is a node. and it contains something called a path. A path is nothing but a line which connects two nodes. Using this, we know the direction or the path that we have to take when we're traversing through our graph, right? So first let's just make a very simple graph. Okay, right now we have two nodes A and B. I'm just gonna add two more, C and D. Now this connection with four nodes A, B, C and D and their paths is called a graph. This whole thing is your graph. These are the graphs that these algorithms will have to travel through and find the shortest distance on. So now how do we know where we need to go in our graph? For this, we have something called a start node and an end node. So let's say our A is nothing but a start node. And our C over here, this node is our end node, right? So now we know that we have to go from this node A all the way to this node C. In this case, it becomes very easy. I can either go from A to B to C or from A to D to C. But how do I know which path is the most optimum path or the path which has the least cost? This is made very easy by the use of weighted graphs. This is a basic graph, but in weighted graphs, all these paths between nodes have a certain weight to them or a certain number assigned to them. Like say, let's just say this is 2. The cost of this path is 3. This path has a cost of 5. And this path has a cost of 1. So now, as you can see, we've assigned numbers to the paths between different nodes. These numbers tell us the cost of traversing through that path. So when I take this path between A to B, I get a cost of 2 incurred on me. And when I go from B to C, I have a cost of 3. Similarly, when I go from A to D, if I take this path, I'll have a cost of 5 and D to C will have a cost of 1. So this helps us in finding out which paths we should be taking when we're traversing from one node to the other. Now in this case, let's look at the different possible paths we can take to reach C. The first option is that we go from A to B, and this will give us a cost of 2. And then from B, we go to C, which will give us a cost of 3. Now the total cost of taking these paths can easily be obtained by finding the summation of the individual cost of these paths. So this will give us 5. All we have to do is add up the weights that each path has when we're traveling it, and we get to know what is going to be the cost of a path taken. So a path A, B to C has a cost of 5. Similarly, our path A to D and D to C has a cost of 5 plus 1, because A to D is 5 and D to C is 1, which is 6. So between 5 and 6, we know that 5 is lesser, which means that this path A to B to C is going to be our least cost path, and that is the path that we should be taking. So A-star algorithm makes use of something called weighted graphs, right? So A-star algorithm makes use of these graphs in these ways. Now let's consider that I have some other node here. Let's say that I have a node E, okay? Now B is connected to E and E is also connected to C. Let's say that the cost of taking this path B to E is 1 and E to C is 0. So now let's calculate the cost of taking the path A, B, E and C. Okay, so A to B to E to C is nothing but 2 plus 1 plus 0, which is equal to 3. When compared to A to B to C, which is nothing but 2 plus 3, which is 5, and A to D to C, which is nothing but 5 plus 1, which is 6. This path is obviously going to be the shorter path, right? But let's consider our programmer, or let's say we ourselves, don't actually want to take this path because coding for it is hard, or because it's very much isolated from the map. So we prefer to go transverse along some other nodes. And this is not a preferred node. But looking at the graph, no matter what we do, depending on how the weights are distributed, we are still going to have to go via this node. Now, to overcome this, programmers make use of something called heuristic values. What are heuristic values? So far, using a weighted graph, we've given importance to our paths. We found out which paths are the easiest to take and which paths are the ones which give us a higher cost of implementation. Now, using heuristic values, we're gonna do the same to our nodes. The heuristic value of a node in a graph attempts to capture the importance of that node's value within that graph. So the heuristic value is nothing but an arbitrary value which is assigned to these nodes based on the programmer's whims and needs. Just like how we have the weightage of paths, the heuristic value gives us the weight of a node and tells us how expensive it is to traverse through that node. It is represented by h of n. So now let's assign heuristic values to our graph and understand how exactly it changes how we traverse this graph, right? So let's say our initial start node A has a heuristic value of 1 and our node B has a heuristic value of, say, 3. Our node E, which is out of the way and which we don't really want to traverse much on, we can assign a very high heuristic value to it to ensure that it's not a path which is regularly taken. So we can assign a heuristic value of 10 to E. Let's assign other arbitrary values to the other nodes. Let's give D a heuristic value of 1 and C a heuristic value of 0. So now, as you can see, even though the paths over here take on a very short value, it would become a lot more expensive to traverse through E just because of its single high heuristic value as compared to the other nodes. How does having a heuristic value in our graph change how we are traversing? So after implementing the heuristic value to our graph, we now have two major values which come into the play. The heuristic value, which is nothing but the value of the node, and the path weight. We can represent this as g of n, which is nothing but the weights in our weighted graph, right? So as you can see, when we're traversing from one node A to a node B, we're gonna have to consider both of these values. So the cost function of a graph, or the total cost of taking a path, becomes the value of the path weight, which is given by the weighted graph, along with the heuristic value, which is assigned by the programmer or by you yourself. And this here is the basic function behind our A-star algorithm. This is the formula that our A-star algorithm works on. So initially, the A-star algorithm will calculate the cost to all of its immediate neighboring nodes and choose the one which is incurring the least cost. This whole process will repeat until no new nodes can be chosen and all the paths have been traversed. And then you should consider the best path among them. And how do you find the cost function? Again, you're just gonna add up the heuristic value and the path value that you've taken. Now g of n, which is the path value, is nothing but the cost of traversing from one node to another. Very obviously, this will vary from node to node. Whereas h of n, or heuristic approximation of a node's value, is not a real value but an approximation cost that you or some other person has assigned to various nodes. Now that we know the basic concept behind the A-star algorithm, let's take a look at how exactly the A-star algorithm works with the help of a case study. So now let's take a look at how the A-star algorithm works. To do this, we're first going to consider a weighted graph, since A-star algorithm uses weighted graphs to make its calculations easier. So consider this to be our weighted graph. We have a node A, a node B, a node C, a node D, and a node E. Okay. Now node A is connected to node B, node B is connected to node E, node E is connected to node D, D is connected to C, and C in turn is connected to A. C is also connected to B, and A is also connected to E. So now let's assign the path values to all the different paths in our weighted graph. Let's say A to B has a path value of 1, B to E has a path value of 6, D to E has a path value of 5, C to D has a path value of 9, A to C has a path value of 10, and A to E has a path value of 2, and this has a path value of 3. Now let's assign heuristic values. Let's give A the heuristic value of 2, B the heuristic value of 5. Let's just give this a 7. Let's make this 4. And let's give C a heuristic value of 0. Okay. So now this is what a weighted graph looks like. From the basic working, you already know that the cost function of your weighted graph is nothing but the path value along with the heuristic value. So let's now say that A here is where we have to start from, and E is our target node. Okay, and this is where we are going to be starting from. Now A is our starting node, so there are 3 different paths that we can take: A to B, A to C, or A to E. So first let's consider that we take A to B. Okay, the first thing that you have to consider is the heuristic value of A itself. So f of A is the first value that you're going to be considering, right? Now f of A here is going to be the path value plus heuristic value. Now because A is the starting node and there's no other node leading up to it, it is the parent node itself. So the path value here is going to be 0 because there's no path leading up to it. It's the starting node, and the starting node always has a path value of 0. Next, we're gonna add the heuristic value of A. In this case, 2. So 0 plus 2. So f of A is 2. Right? So this is the first node that you've considered. Okay. Now, after taking node A, we have 3 different options: A to C, A to E, or A to B. So the cost function of taking the path A to B is going to be, so now let's find the cost of taking the path A to B, right? A to B, so you have to add the graph node value plus a heuristic value. The weight of taking the node A to B is nothing but 1, and the heuristic value of B is 5. So this is going to give us C. Next, A to C. Next, let's look at the cost of taking the path A to E, right? F of A to E. So this is going to be 2 because the cost of taking this path is 2, along with the heuristic value of E, which is 7. So this is going to be 9. And let's look at f of A to C. Now the cost of taking this is going to be 10 plus the value of C, which is 0. So this is going to be 10. Now the way how A star algorithm works is it will calculate the cost function of all the neighboring nodes and go with the node which has the least cost function. In this case, the node being B. So we're not going to take this path or this path because the cost function value is way more than the cost function value of f of A to B. So after A, we are going to be at node B. So right now, this is the direction that we've traveled in. Now when we're at node B, to reach node E, we have two different options. We have two options that we can take. We can either go from B to E or we can go from B to C. Okay. The goal of A star algorithm is to always minimize the cost of the path that you're taking. So using this in mind, let's calculate f of B to C, which is going to be nothing but the cost of the path from B to C, which is 3, plus the heuristic value of C, which is 0. So this is going to be 3. Next, let's calculate the cost of B to E. Now this is going to be again nothing but the path value, in this case 6, plus heuristic value, in this case of E, which is 7, which is nothing but 13. So again, as you can see, this is the correct path to be taken. And we are not going to be taking this path because its value is way too high. So the next path that we're going to be taking is this path, B to C. So now we're at node C. From node C, we can either go to A, which is not possible because we do not go back in the direction that we came from, to B, again, that's not what we're going to be doing, or to D. So the only option that we have available is to go from C to D, right? So what we're going to do is we're going to find the cost of going from C to D. Again, this is going to be the value of the path, which is 9, plus the heuristic value of D, which is 4. The cost of traversing this path is 13, but we don't have any other path available to us because this path has already been closed. You can't backtrack in A star algorithm or go back to the path where you came from. And again, we've already considered A to C before, right? Like over here, we've already considered A to C and we've already ruled it out. So again, this is not a path that you can take. So what we're going to be doing right now is that we're going to be traversing from C to D. And the cost of taking this path is 13. So now this is the path that we're taken from C to D. We're at D now. At D again, we can't go back to this path. We can't go back to C. The only way we can go is E. So we're going to consider f of D to E. And this is going to be again the path that you're going to take from D to E, which is 5. Plus the heuristic value of E, which is 7. This whole thing is going to be 12. Now once we're at C, our A star algorithm is going to check if this is the target node. And lo and behold, it is. So we've traversed from A to E. Let's see the path we've taken. First, the starting node that we started off from was A. From there, we looked at the cost of taking A to C, A to E, and A to B, and finally we settled for going from A to B. From B, again we consider the paths B to E and B to C. We cannot consider A to B because this path has already been traveled on and it's already been considered before. Now after considering B to E and B to C, we found that B to C was the shortest path. From C, we didn't have any other option. We couldn't backtrack or go back to B, and we couldn't go to A because this path was already been considered and already it has been ruled out. So the only path we could take from here was to D. And again from D, the only path that we could take was to E. So now let's look at the path that we've taken while using our A-star algorithm. We started off at the node A. This was our starting node. From node A, we had three options. We could go to node B, to node E, or to node C. After considering all of these options, we realized that A to B was the path of least cost that we could take. Once at B, we considered two paths, B to E and B to C. And we found out that B to C was the path of least cost. From C, there was no other path we could take. We cannot go back to the node we came from, which is B, because A-star algorithm does not support backtracking. And we couldn't go back to A either because this path had already been considered and we'd already ruled this path out, right? So the only path we could take was to D. Now, once we arrived at node D, the only node that we could travel to again was E. So using A-star algorithm, this is the final path that we've taken to traverse from our start node A to our target node E. And with the help of this case study, we've also explained to you exactly how the A-star algorithm works. We use the path values and the heuristic values to find the cost of taking different paths available to us at each node. And then we take the path which has the least cost among all available paths. The same process will continue until we've reached the final target node. And again, remember, you cannot go back on the path that you came from, or you cannot go on a path which has already been considered. So now you know how the A-star algorithm works. But what is the flowchart of the A-star algorithm? Now, a flowchart is a picture of the separate steps of a process in a sequential order. It's basically a generic tool that can be adapted for a wide variety of purposes, and you can use it to describe various processes. In this case, this is the basic flowchart of the A-star algorithm. It tells the direction of control flow within the A-star program, and using this you can implement A-star algorithm in any desired language of your choice. So the first step of our A-star algorithm is to initialize a start node and put it in an open list. Now in this algorithm, we're gonna first create two lists, an open list and a closed list. The open list will contain all the nodes that have been visited, but their neighbors have yet not been explored. On the other hand, the closed list contains nodes that along with their neighbors have already been visited. So the first node or our starting node is going to be put in an open list because we're still exploring it. Then we're going to calculate the cost function of the starting node. From here onwards, we're going to remove this node from the open list and put it in the closed list since we've already visited it and calculated its cost function. If we're also looking at the neighbors which are surrounding this node, or if this node has many different nodes around it, then we're going to calculate the cost function for those nodes too and save the index of the node which has the smallest cost function f. Next, we're going to look at if the node we're currently on is our final node or our target node. If that's the case, we're going to terminate the algorithm and use pointers of all of our nodes to get the desired path. If that's not the case, then we're going to look at the successive nodes of n, or all the nodes which come after this node which are not in the closed list. We're going to calculate the cost function of each of these neighboring nodes, remove them from the open list as they're not already in the closed list, so they're obviously going to be in the open list. So we're going to remove them from the open list and then we're going to put them in the closed list. And again, we're gonna save the index of the neighboring node with the smallest cost function. And then this process is going to keep repeating over and over until we've reached the target node, which is where our program will get terminated. So basically what we're doing is we're going to a certain node, calculating the cost function for that node, looking at all the successive neighboring nodes of it, and going to the neighbor which has the least cost function. Now this process will again get repeated. So from this neighboring node, we're going to find all the other nodes which are connected to it. And then we are going to go to the node which has the least cost function. So using this, we're going to hop from one node to another depending on which node has the lowest cost function. Once this is over, we're going to again take some other node and we're going to repeat this process until we found all the possible paths to a final destination node. And in this way, the A-star algorithm is not only going to find the shortest path, but it's also going to find all possible paths. Now, let's see how the A-star algorithm can be implemented with the help of Python. In this demo, we will use the A-star algorithm to find the least cost path between various nodes in the weighted graph which is shown below. So in this graph, as you can see, we have 6 different nodes A, B, C, D, E, and G. The weights of the paths between these nodes is denoted by these numbers in black, and the heuristic values of the nodes itself are denoted by the numbers in red. Now using these values, we can find the shortest distance between any two nodes. Let's see how we can do this with the help of Python. So now let's start by creating a class for the A-star algorithm called the A-star algo. Now in this algorithm, we're gonna have to describe the open and the close list. And to do this, we're gonna be using two sets. So our sets are our open list and our closed list. We'll also be using two dictionaries, one to store distance from the starting node and another for parent nodes. And we're going to start by initializing them to 0. The open set is going to have the start node already in it. Now, we all know that the distance of the starting node from itself is 0 itself. So we're going to initialize the distance of the start node to 0. And we also know that the start node is the root node and it has no parent nodes. So the start node is its own parent node. The first step of initializations is to put the start node in the closed set to set the distance of the start node to itself as 0 and to set the start node as its own parent node. Now that we're done with the first couple of initializations, let's move on to finding all the neighboring nodes. So now we're going to have to find the neighboring nodes with the lowest value of the cost function. We also have to code for the condition of reaching the destination node. If this is not the case, we're going to have to put the current nodes in the open list, and if they're not already in it, then we're going to set their parent nodes. So that's what we're going to do. First, we're going to find the node with the lowest cost function. We're going to take the entire open set, and while the length of it is greater than 0, or basically while we're not at the parent node, we're going to loop through it. We're going to go to all the neighboring nodes of the open node, and then we're going to find their cost function. Now here, this is the function that you're going to use to find the cost function. Now here, what we're going to do is we're going to calculate the heuristic value for n, and if the cost function of n is 0, or if its cost function is less than the cost function of its neighboring node, then we're gonna move on to the next node, which is v. Now if n is equal to the stop node, or we've looped back and come to n itself, then we're not gonna go ahead, or we're gonna exit this loop and we're gonna move on to some other node. Otherwise, if the neighbor has a lower G value than the current node and is in the closed list, we're going to replace this new node as the neighbor's parent. And that's what we're doing here exactly. Now, if the neighbor is not in both the lists, then we're going to add it to the open list and set its G value. And that's basically what's going on here. So let's run this for the A-star algorithm. Now we're going to define a function to get the different neighbors and their distances. Next, we're going to create a function to store the heuristic values and retrieve them as and when required. Now we're going to describe our graph here. So these are all of our nodes and the nodes that they're connected to, along with the weight of their paths. So here A is connected to B and the weight of this path is 2. A is also connected to E and the weight of this path is 3. In the same way, B is connected to C and the path has a weight of 1. And B is also connected to G and the path has a weight of 9. So here, this is what we're going to do to describe our entire weighted graph. And then we're going to finally call our A-star algorithm and give our starting node and our final node. And it very quickly finds the path between our starting node and our final node. And over here, as we can see, the best path to take would be from A to E to D and finally to G.
Face detection system. It is a form of biometric recognition, a method for identifying or confirming someone's identity by glancing at their face is called facial recognition. People can be identified by securing a match on facial ID using this technique. Real-time visuals, videos and photos can be the sources to run face detection. This technology is mostly employed in security and law enforcement. OpenCV is the best technology to create it. A Python package called OpenCV is made specifically to address computer vision jobs. Computer vision is a process used in the processing of images by computers. It is concerned with the in-depth comprehension of digital photos or films. It is necessary to automate operations that can be performed by human visual systems. Therefore, a computer should be able to identify items like a statue or a lamppost or even the face of a human being. Second one is chatbot. It is the best idea if you have chosen chatbot as your project topic. This will make your resume more attractive in case you are looking for a job. An Oracle survey suggests that 80% of the businesses uses chatbot. You can use Python, Java, Ruby, C++ or PHP as a programming language to develop a chatbot. Designing and building NLP chatbots that accept speech and text data is made easier by Dialogflow. You can go through many projects to get the rough idea. There are many platforms which will help you to build a chatbot. Regardless of how excellent your chatbot is, there is always room for development. The finest chatbot developers constantly enhance their bots over the time using AI and machine learning. Social media recommendation system. The rise of web services like Netflix, Amazon and YouTube has increased the use of recommender systems in our daily lives. They are algorithms that insist users in finding information that is pertinent to them. Recommender systems are important in some firms since they can generate a lot of income or allow you to set yourself apart from rivals. In order to provide recommendations, it evaluates the relationship between the user and the object as well as the parallels between users and possessions. Coming to predicting stock, this application is widely applicable everywhere. As AI career aspirants, one will love to develop stock prediction applications as it is full of data. This project would be ideal for students who want to work in the finance industry because it can provide them a better understanding of various aspects of the field. coming to medical diagnosis, this project is advantageous from a medical standpoint. AI projects can be created to detect heart-based diseases and also detect cancer. It is intended to offer patients with heart illness online medical advice and guidance. After processing the data, this system will search the database for any illnesses that might be connected to the given details. Using data mining techniques, this intelligent system determines the disease that the patient's information most closely resembles. Based on the system diagnosis, users can then speak with qualified medical professionals. Users of the system can also view information about various doctors. Coming to an important project, that is search engine. Search engines are utilized by all. We look for information on the greatest product to buy, a nice area to hang out, or solutions to any questions we have. NLP is quite significant in modern search engines because a lot of language processing takes place there. Python is the widely used language to develop any search engine. Search engine is mainly confined with lots and lots of data. It is helpful for any AI career aspirants. Next is virtual assistants. Here the challenge is to build a virtual assistant to assist user. Why do you need virtual assistant in your devices when you are building your own? It is also interesting for a ML developer to build a virtual assistant. It involves NLP and data mining. Voice-based virtual assistants are popular today because they make life easier for users. NLP is utilized to comprehend human language in order to construct this system. When a voice command is received, the system will translate it into machine language and store the commands in its database. Hate speech detection in social media. Automated hate speech detection is a crucial weapon in the fight against hate speech propagation, especially on social media. For the job, many techniques have been developed, including a recent explosion of deep learning based system. For the objective of detecting hate speech, a number of techniques have been investigated, including conventional classifiers, classifiers based on deep learning, and combination of both of them. On the other hand, a number of dataset benchmarks, including Twitter sentiment analysis, have been introduced and made available for the evaluation of the performance of these algorithms. And the last one is predicting house price. You will need to estimate the sale price of a brand new home in any place for this assignment. The dataset for this project includes information on the cost of homes in various city neighborhoods. The UCI machine learning repository is the place where you may find the dataset needed for this research. You will also receive other dataset with information on the age of the population, the city's crime rate, and the location of non-retail enterprises in addition to the pricing of various residences. It's an excellent project to test your knowledge if you are a newbie.
Popular market research projects that the market for artificial intelligence will grow from $59.7 billion in 2021 to $422.4 billion in 2028. Artificial intelligence, automation, and robotics are disrupting almost every business. Companies that don't invest in AI services risk becoming obsolete, whether in machine learning, smart applications, appliance, digital assistants, or autonomous vehicles. Numerous companies stand to benefit from AI, but a handful of them have proven to be the game changers for 2023 and beyond. So hey everyone, you are already watching Simplilearn, and here we are with the list of top 10 AI companies in 2023. If you love watching videos like these, do hit the subscribe button to never miss an update from Simplilearn. So let's explore and learn about them one by one, starting with the 10th position, which is UiPath. Robotic Process Automation, or RPA, is a technology developed by UiPath that helps businesses to boost productivity and reduce cost by automating time-consuming and repetitive operations. Software robots can be equipped with UiPath AI technologies to carry out duties including reading documents and emails, interpreting language and visual cues, and comprehending the content and the intent of the communications. The RPA market is estimated to be worth $38 billion, and UiPath offers distinct advantages over the competitors, thanks to its patent computer vision technology and wide range of bot technologies. In the 9th position, we have Dynatrace. The services offered by Dynatrace include observability and infrastructure monitoring. The Davis AI engine developed by the business can analyze 368 trillion dependencies each second. Davis can quickly locate problems in a company's digital ecosystem, explain what went wrong, and evaluate and rate likely commercial ramifications. The company estimated a market worth $285.42 million and is poised to grow revenue by roughly 20% annually throughout at least 2025. Then at the 8th position, we have Palantir Technologies. Data analytics software startup Palantir Technologies uses AI to analyze data. According to revenue and market share, Palantir was ranked as the top AI software platform globally by IDC in September 2022. The United States intelligence and defense industries account for a sizable portion of Palantir's revenue. The business just won a new $85.1 million contract from the US Army Marshall Command to assist with the developing AI and machine learning technologies to enhance equipment reliability, improve predictive maintenance, and improve supply chains. Palantir may deliver revenues closer to the higher end of analysis estimates, roughly $2.5 billion in 2023. Then at the 7th position is Workday. Workday is a provider of cloud-based applications with an emphasis on human resources management. With the assistance of Workday's distinctive AI-based optimization engine, businesses can manage challenges with hiring and staffing, fluctuation labor demand, shift scheduling and prioritizing, and more. In April 2022, Workday incorporated Barista, an AI-powered virtual assistant from Espressive, into their platform. Workday is raising 2023 market worth to almost $5.53 billion, representing year-over-year growth of 22%. Now in the 6th position, we have Intuitive Surgical. The Da Vinci surgical system offered by Intuitive Surgical performs minimally invasive procedures using cutting-edge robots and computerized visualization technology. With the help of a big data and AI, Intuitive is developing tools that will help surgeons by improving their training and offering them real-time direction. Despite the fact that the Da Vinci surgical system has been approved by US FDA for 22 years, Intuitive reported a 13% year-over-year increase is installed in the system most recent quarter. The global intuitive surgical market is projected to reach $6.5 billion by 2023. Moving towards the 5th position, we have IBM. For years, IBM has been developing strategies to use its AI supercomputer to alter the legal, banking, academic, and healthcare industries. IBM's clients harness the power of AI to stay current on ever-changing regulations by providing end-to-end risk and compliance management. IBM continues to dominate the market for the other breakthroughs in AI, and its Auto AI and Auto ML products can help data scientists build and improve AI and machine learning models. The market worth of IBM in 2023 will range from $14.4 billion to $16 billion. Following that, in the 4th position is NVIDIA. High-end chip maker NVIDIA provides the significant computing power needed for advanced AI applications. In reality, one of the world's fastest supercomputers, Leonardo, is powered by NVIDIA graphics processing units. The parent company of Facebook, Meta Platforms, is building the biggest artificial intelligence supercomputer in the world. Meta also owns NVIDIA's Quantum InfiniBand networking system and 6080A 100 NVDA graphics processing processors. NVIDIA is a significant supplier for fast-growing industries like high-end gaming, business graphics, cloud computing, artificial intelligence, and advanced automotive technology. NVIDIA's outlook for 2023 revenue is expected to be around $6 billion. Here comes the top 3 in the list, and in the 3rd position, we have Amazon. AI is integrated into every aspect of Amazon's business, including e-commerce, search engines, targeted advertising, and Amazon Web Services. Amazon Alexa, one of the most popular virtual assistants, is already present in many American homes. Amazon said in August that it would pay $1.7 billion to acquire Robots Corp RBT, a maker of home robots. This action can allow Amazon to boost the use of AI in households worldwide. Amazon expects a $491 billion market worth between 2023 and 2027. In the 2nd position is Alphabet. Alphabet, the company that owns Google and YouTube, uses AI and automation in practically every part of its business, including ad pricing, Gmail spam filters, and content promotion. In addition, it is the parent company of the autonomous car manufacturer Waymo and the AI software business DeepMind, which created history in 2022 when it became the first completely autonomous commercial taxi service to operate on public roads. The market worth of Alphabet in 2023 will be around $70 billion. And the first position on the list is Microsoft. In 2020, Microsoft announced the construction of a new supercomputer hosted on Azure, Microsoft's cloud computing network. The supercomputer was created in collaboration with OpenAI to train AI models, producing substantial AI models and related infrastructure for programmers and other businesses. In October, Microsoft released Microsoft Designer, a graphic design tool that makes original social media posts, invitations, and other graphics using AI technology. Microsoft, the tech giant, is expected to earn a market worth of $49.73 billion. And with that, we have come to the end of this list of the top 10 artificial intelligence companies of 2023.
Opportunities in AI have increased significantly in recent years. The surge in jobs related to AI is legitimate due to its widespread involvement in crucial fields. According to Indeed, the pay range for jobs involving artificial intelligence is between $160,000 to $350,000 and can go even higher. So we have come up with a list of leading career opportunities in artificial intelligence along with companies hiring for those roles. But before we begin, here is a question for you. Who do you think is currently leading the AI market? Let us know in the comment section below. So without any further delay, let's get started. Starting with our list, we have robotics engineer. An engineer in robotics creates prototypes, constructs and tests machines and updates the software that manages them. Additionally, they investigate the most affordable and secure way to make their robotic system. Aspirants should have a bachelor degree in computer science and pursue a career in robotics with additional training or certification in automation is advantageous. Robotics engineers are in high demand with 9,000 plus job openings in India and 8,000 plus openings in the US. Top companies like Amazon, Bosch and Flybase are hiring robotics engineers with salaries as high as $160,000 in the US and Rs 27 lakhs in India. Next up on our list, we have product manager. The role of a product manager is to recognize and express user requirements, market research, and creating competitive evaluations. And also creating a product's vision and putting emphasis on a product's strengths and qualities. Freshers cannot join as a product manager. It requires basic experience of 2 to 3 years in the field of product and software development. According to Indeed.com, an average of 2,000 plus jobs are currently available in India and 20,000 plus job vacancies are there in the US with top companies hiring are Tesla, Amazon, TCS, Sprinklr, Cognizant, etc. with a salary as high as $160,000 per year in the US and Rs 20 lakhs per annum in India. Up next we have data scientists. They mainly deal with lots of data. Extraction of knowledge from all collected data is the subject matter of data science. It was also voted the sexiest job of the 21st century. Good news is there is no need for any special degree. As a data scientist, you need to have knowledge of machine learning, programming in Python, R, Java, and mathematical modeling. Being a fresher, you can join as a data scientist too. Data scientists are in demand with 17,000 plus vacancies in the US and 3,000 plus vacancies in India. And big businesses like Accenture, TCS, IBM, Google, JP Morgan, Deloitte, Bank of America recruiting data employees with salary going as high as $200,000 per year in the US and Rs 15 lakhs per annum in India. Moving forward in our list, we have AI data analyst. Data mining, data cleaning, data interpretation are the three main tasks of an AI data analyst. Data cleaning allows for the gathering of the necessary information for data analysis. An AI data analyst makes inferences from the data using statistical tools and techniques. You need a bachelor degree in computer science or mathematics to work as an AI data analyst. To get this job, you must have a thorough understanding of regression and be able to use MS Excel. According to Indeed.com, there are currently 700 plus AI data analyst jobs available in the United States and 16,000 plus job vacancies in India with top companies like Accenture, IBM, Wipro, TCS and Capgemini recruiting them and salaries going as high as $100,000 per year in the US and rupees 8.5 lakhs per annum in India. The next job opportunity in AI is business intelligence engineer. A business intelligence developer's main duty is to take both business sense and AI into account. They evaluate complex data sets to identify various business trends. They assist in boosting a company's earnings by planning, creating, and sustaining business intelligence solutions. To become a business intelligence engineer, you are required to have a bachelor degree in mathematics and computer science. According to Indeed.com, there are 8,000 plus jobs available in India and 5,000 plus job vacancies in United States. Companies hiring are Amazon Development Center, IBM, AWS, etc. With this, salary going as high as $100,000 per year in the USA and rupees 15 lakhs per year in India. Coming to the top 3 jobs available in AI, at number 3, we have machine learning engineer. Artificial intelligence is known to include machine learning. It runs simulations using the varied data provided and produces precise results. They are constantly in demand from the businesses and their position seldom goes unfilled. They handle enormous amount of data and have exceptional data management skills. The ability to code, use computers, and understand mathematics are requirement for success as a machine learning engineer. A master's degree in computer science or mathematics is highly preferred. The necessary technological stacks include Python, R, Scala, and Java. A deep understanding of neural networks, deep learning, and machine learning algorithm is very helpful. Coming to job opportunities, Glassdoor.com predicts 13,000 plus job vacancies in the US and 27,000 plus jobs available in India, with companies like MathWork, Google, Amazon, Microsoft Azure, IBM, etc. hiring them with salary going as high as 150,000 per annum in the US and rupees 10 lakhs per annum in India. Coming at runner-up position, we have data architect. Data architects are IT specialists who utilize their knowledge of computer science and database architecture to assess and analyze an organization's data infrastructure. Fresher graduates cannot become data architects. A bachelor degree in computer science and computer engineering or related subject is the absolute minimum requirement to become a data architect. Data architects are in high demand with 52,000 job vacancies in the United States and 7,000 plus jobs in India, and top companies hiring data architects are Amazon, IBM, Tesla, Intel, Wipro, with the average salary quite high as $200,000 per year in the United States and rupees 21 lakhs per annum in India. And topping our list of job opportunities in AI is AI engineer. AI engineers are problem solvers who create, test and use various artificial intelligence models. They manage the AI infrastructure well. To create practical AI models, they use neural network knowledge and machine learning methods. These models enable one to gain business insights which aids the organization in making wise business decisions. UG or PG degree in the field of AI or computer science is required. In addition to that, you can hold certifications from any reputed organization which will add up to your resume. Please check out and enroll to the AI program by Simplilearn in collaboration with Purdue University. The link is provided in the description below. Job openings for an AI engineer are quite high with 35,000 plus job vacancies in the US and 4,000 plus jobs in India, and tech giants like Accenture, TCS, IBM, Google, JP Morgan, Deloitte, Bank of America recruiting them with salary going as high as $200,000 per year in the US and rupees 10 lakhs per annum in India.
That's a wrap on our introduction to the AI engineer course. If you are excited to embark on this thrilling AI journey, don't forget to like this video, subscribe to our channel, and hit the bell icon. Enroll now, and let's dive into the exciting world of AI together. Until next time, keep exploring, keep innovating, and let AI take you to the new horizons. Thanks for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.